All right, so I don't know if you can see me. Um, Assalamu alaikum, everyone. It's 4, so I guess now is as good a time as any to start. My name is Khaled. Khaled, only Khaled, not Dr. Khaled, not Dr. Khaled MD, not Khaled MD, not anything like that, just Dr. Khaled. Feel free to always call me Khaled. If I see one person calling me Dr. Khaled, I will literally leave the freaking conference, okay? Um, I think there are still people joining. So before we actually start with the entire lecture, I just want to give you a little introduction as to what we're actually going to be doing. First off, we're not going to be doing all the lectures today. We're going to be doing 4 lectures, and then the last 2 Peter lectures, we're going to do them tomorrow. If there's also confidence interval, I'm not sure if you guys took it, we'll also do it tomorrow. So if someone could just let me know in the chat that if we took confidence interval or not, and you know, I can also squeeze it in tomorrow. It's not that big of a lecture, and we can probably find some time for it. Now, this is the 4th year in a row of doing biostats, the crash course and everything. So I'm incredibly proud that, you know, oh no, it's not included, that's good. We took it, but it's not, okay, that's perfect. So we're just gonna do the 4 lectures and then, you know, the 2 lectures tomorrow. So this is the 4th year doing, you know, the biostats crash course. I'm incredibly proud that, you know, we managed to, you know, do this sort of thing. It became almost a traditional Faisal. Every year there has to be a crash course, and alhamdulillah, I'm happy that despite being in a pandemic and everything, we're still doing it. Everyone who has heard about this crash course knows that inshallah it will hopefully benefit them. Usually I do a survey at the beginning where I ask them, hey guys, whoever understands biostats, raise your hand. Whoever, you know, is 50-50, raise your hand, and whoever doesn't understand anything, raise your hand. I'm afraid I won't be able to do it now, but I'm just going to assume that the majority of people are having trouble with biostats. At the end of this lecture, at the end of this entire crash course, inshallah, by tomorrow, the end of everything, you will be confident for your midterm, inshallah. I assure you of that. But it's not going to happen through magic. I need your help as much as you need mine. So for that, I need 2, you know, promises from you guys. They're more like rules, guidelines, but basically, rule number 1, 24/7, I need you with me, right? Now, it's only going to be 4 hours, and I understand that 4 hours can be quite a toll on the person. So if you ever need a break, stop me. If you ever think I'm going too fast, stop me. If you ever think that I just, you know, brushed over a concept, didn't give it didn't give you the chance to appreciate the concepts behind it, stop me. If you think we just need a break, not even between lectures, just within the middle of the lecture, stop me. We can all just take a 5-minute break and just relax. So I need you basically to be always with me, and the only way you can do that is that I need your mind to be relaxed at all times. If you're at any point stressed, just stop me. So that goes for everyone, not just, you know, I don't want it to be feel like for example, I don't want to feel this sort of pressure that, oh, if I tell this person to stop and, you know, have a break, then khalas, we're going to stop everything and everything. No, it's fine. Even if it's one person, if you want a break, just stop me. It's fine. So that's rule number 1. Rule number 2, someone asked me, do you want me to take questions, for example, in the middle of the lecture or at the end or so on? Whenever you have a question, just ask me at any point. And the reason I say that, every year the same problem happens of too many questions get asked, but every single year I keep doing the same thing. The reason I do it is because biostats is one of those things where if you don't understand point number 1, you're not going to understand point number 2. If you don't understand point number 2, you're not going to understand point number 3. So for that reason, I need you all to tolerate, you know, as much as I'm going to tolerate the questions, because everyone needs to understand. If one person misses one point in the beginning, they're not going to understand anything for the rest of the crash course. So I don't mind staying here till, you know, 10 p.m. or something. We're not going to stay until that long, inshallah, but just get into the habit of asking me questions if you don't understand. I used to be very shy. Shy is not the word. It's more like I didn't want to ask to slow down the lecture. No, this is the exact opposite. Ask and ask and ask and ask, because if you don't understand anything now, it's going to bite you later. So with that said, if you just give me those 2 things, your attention and asking me questions, inshallah, you will find a lot of benefit from this crash course. So with that said, let's just start. So this is the first lecture. It's called Basics of Biostatistics. It basically has a lot of definitions, and you pretty much just need to know them. For example, a population is the total amount of data in a certain, for example, group. So for example, let's say we want to study the US population. There are whatever 300 million people, so on and so forth. a population is every single piece of data that you can possibly collect within a given, for example, group for a particular study. Now, this lecture in particular, there's not really much for me to explain because the majority of it is just basically definitions. As we keep going to the later lectures, you're going to notice that there are some concepts that require a lot more thinking. But for this lecture, just really, like, a lot of the people in my batch personally, they skipped this lecture just because it's full of definitions. But a lot of questions came from it, and it's just easy questions that you can answer. It's just definitions, and you can just answer them very easily just by knowing the definition. So again, population, the totality of information, every single thing within a given group. A sample is just a small sort of nugget of that group, a small sort of part of that group. So one of the very important things when it comes to sample and population is that a sample has to be representative. What does representative mean? I think he has a picture about this. I'm going to skip ahead to it. So a sample that has to be representative means that it has to sort of give the qualities of a population and represent those qualities in a very, very adequate way. It has to sort of show all the proportions and how sort of that population can be studied at a much smaller group. And that can be very, very useful, but sometimes you end up with problems where you get a sort of group like this. Now, I don't know if you guys can see my mouse. I just like to ask you guys quickly if you can see my mouse or not, because I'm going to be pointing a lot. I'm going to be drawing a lot. All right, good, perfect, you can. So you sometimes get problems where people think this is the sample to this population. Now, obviously, here it looks very obvious to us that, hey, this group doesn't look representative to this sample, to this population, and this group, this sample doesn't look representative to this population. But that's just because we see the overarching picture. How about you use the pointer? Sure. But yeah, the basic idea is that, we don't really, in real life, we don't really get this glamour of being able to see all these samples and easily knowing that, hey, this is the sample that's representative. The whole idea of this is just to put this idea in your mind that a sample has to represent the population. So let's go back and actually continue. That's what he says here by a representative sample. It has to always represent to avoid any, for example, bias happening. A variable is, from its name, something that can vary, a particular piece of data that can vary. For example, gender. Gender could be either male or female, it can vary. For example, age. Age could be from, for example, 0 to 90, whatever. It could be many different ages, right? So it's something that can vary. The target population is the ideal population that we're studying. For example, let's say we want to study the population of Africa. So we're going to take a sample that's representative of that population because we're interested in that target population, that specific group of people. The study accessible population is everyone who you can actually reach, who you can reasonably reach. For example, let's say you want to do a study in Saudi Arabia. If you want to do a study in Saudi Arabia, maybe you might not be able to access people or reach people who are in the villages, who don't have Wi-Fi, so on and so forth. So although your target population is KSA in its entirety, the actual study population has to be people that you can actually reach. And this is completely normal. These are some of the obstacles when it comes to collecting data, and it's absolutely fine. So for example, target population, Saudi medical students, but the only really accessible population that you have that you can actually study are, for example, Al Faisal University medical students, and so on and so forth. All right. Some more definitions. What are statistics? It's the collection, organization, the analyzing and interpretation of numerical data. And preferably in that order. You want to collect data, you want to organize it so you can actually come up with meaningful analysis on it, and then you want to interpret it in order to come with an actual conclusion. And he loves this, and you just have to memorize it. Whenever we talk about a piece of data, can we consider study population as an example? The study population, from its name, is a population. For example, let's go back to here. All the university medical students in Al Faisal, that's a population. Now, you probably don't want to go through every single Al Faisal medical student, so instead you just take a sample of them. So a study population is still considered a population. It's not a sample because they're going to be way too much. So again, a study population is a population. Yeah, so he loves this. A statistic is always going to be a characteristic of a sample, always of a sample. So statistic, sample. When you talk about a population, no, it's no longer statistic. It's now you deal with parameters. He loves this because when it comes to biostats, the wording is incredibly important. Even when it comes to outside of biostats, like for example, your step 1 or step 2 exams, the wording of questions can sometimes go down to literally, just a word that changes an answer from being right or wrong. So being able to know that a statistic is what, is a characteristic of a sample is important to differentiate it between a parameter. And there are different statistics, different parameters, and they're given different letters, and we'll see those letters. Some are Greek letters, some are Roman letters. For example, usually parameters take the Greek letters, statistics take the Roman letters, and now they're kind of changing it to just using regular letters. Like for example, they might change standard error, and we'll see what standard error is later on. But they might change it from a Roman letter to now a SE, which in my opinion is much better. But the idea stands that a statistic, sample, parameter, population. Just keep that engraved in your skull, because you probably will get a question on it. We saw this, so basically just to recap, these samples are biased. They don't really represent this population, but this sample sort of perfectly shows the proportions of the different aspects and characteristics of this population. And it's only then that we can actually make an inference from them. So notice how you can't really make an inference of this sample, because this sample is actually for a completely different population, a population that's not this, an actual different population. So maybe you can make an inference of this sample on a different population, but not this one. This one is completely different. All right, so again, back to definitions. Biostatistics, basically applying statistical techniques onto scientific work, like for example, biology, medicine, agriculture, and public health. Medicine is the most important one, because obviously for us, we're sort of biased because we are medical students. And it's really important to have biostatistics, because I'll give you some examples, but one of the most famous examples is beta blockers and heart failure. 10 years ago, 20 years ago, if you told the consultant that, hey, we're going to use beta blockers to treat heart failure, chronic heart failure, they would laugh in your face. Now it's the standard of care. And who told us it's the standard of care? It's Biostats. Is it slow from, well, you're going to have to know with other people. Let me know if that's your internet. Okay, perfect. Biostatisticians. So what is the role of biostatisticians? They help tell you how to design your study. They help tell you how to manage the data, how to analyze, and how to, for example, spread out the results, how to put, for example, in which, what would they call it, which journals, for example, Nature or that. So, biostatisticians, they're really important. They are one of the pillars of medicine, modern medicine at least. They help tell us what is happening, what is new. Like, for example, a lot of the things that you're learning now in medicine, a lot of it was found because of biostats. Biostats helps find associations, even if there's no real, discussion as to how it happens. We just know that there is an association, and that we have to thank biostatisticians for that. So why study biostats? Now, yeah, if you're a physician, you might make the argument that, hey, if we have biostatisticians, let them do everything and it's fine. Why do we need to know biostats? Well, it's because you as a physician, you might be sitting in your clinic and you might have a patient come to you and tell you, doctor, I saw this study on the internet, especially now with this internet culture and everything, and how patients and doctors are sort of merging together in order to come up with a informed decision for the patient's treatment and so on and so forth. They're going to come with you, and they're going to come to you, and they're educated, and they're going to show you studies, and they're going to tell you, I found this study, I tried to read it, and I think I understood. What do you think, doctor? So you're going to be on the spot. You're going to have to read the study and sort of come up with an actual understanding as to what the study is trying to say. So physicians, you don't need to know every single thing about biostats, but you need to know a bit of basic biostats to understand what this study is trying to say, and that's really important. So you can decide when to consult a biostatistician. Like, if it's too complicated, then you can maybe consult a biostatistician. But a biostatistician who sees that you can't even understand what standard deviation and what this means or what that means or what the results are trying to say, they're not really going to be thrilled that you're consulting them for this, when you can very easily just learn it and sort of understand it by yourself. And that's why you're here doing the biostats course in second year. So that's the importance of biostats for just a regular physician, not even a biostatistician. More definitions. So we have descriptive statistics and inferential statistics. Now, for today, we're actually going to be covering descriptive statistics. So what are descriptive statistics? From their name, you describe data. So for example, when you say the mean of this population, or not population, the mean of the sample, for example, is 5. That's a form of descriptive statistics. You collected data and you organize it, and you are displaying it in a form of telling me a certain characteristic of that data. That's called descriptive statistics. You are describing a statistic. Inferential statistics are much more important. They actually help us come up with actual conclusions. For example, whether a drug is better than the standard of therapy or better than a placebo, so on and so forth. Those are incredibly important because they help us make predictions and conclusions, and they can help alter a person's standard of care, and that's incredibly important. Just like how I mentioned earlier about beta blockers and how no one used to use them, but thanks to inferential statistics, now we actually use them as a standard of care for chronic heart failure patients. Could you repeat evidence-based medicine? It's coming along. But just to give you a little brief idea, evidence-based medicine, like back in what was it? Back in like Hippocrates' time, it was like 1500 BC or something. Point is, how did they diagnose diabetes? Yeah, they just put their finger in the urine and they taste it, and then, oh look, it tastes like sugar, so he has diabetes. Now, thankfully, we don't do that because that's disgusting. But point is that because we have people who did biostats and they agreed that, hey, having a cutoff of 200 for your glucose levels or whatever, random blood sugar, that's going to diagnose diabetes. You don't need to put your finger in the urine. So thanks to evidence-based medicine, we're able to actually quantify not just how much glucose needs to be in the blood in order to diagnose it, but we don't need to do the acts that our ancestors used to do to actually diagnose diabetes. So that's the importance of evidence-based medicine. We're sort of removing this tradition of teach me medicine, where the consultant sits down and teaches his, for example, residents or fellows, and instead, no, the consultant tells them, here's the study proved that this happened, and that's incredible. I don't know why everyone's just gone crazy over me saying that 3,000 years ago they used to diagnose diabetes using tasting it. It's a real thing. Thankfully we don't do it now. Point is, that's what evidence-based medicine is. And I had another question. Can we have descriptive inferential statistics? Yeah, of course. You can have, in fact, you can't even reach inferential statistics without having descriptive statistics. So usually with inferential statistics, you start collecting data, you organize it, and then you build your inferential statistics on top of it. Some studies just stop at this descriptive part of it. Some studies go a bit further and they do inferential part of it. But basically, if you decide to do the inferential part of it, it's no longer called a descriptive study. It's basically called an inferential statistic. Or inferential study. So data, what's data? It's basically anything that you can collect. For example, information like age or gender or whatever, facts, anything like that. Data is essential because we're going to use data in order to actually find out whether this can, for example, help us or not help us, so on and so forth. All right, and I think we talked about this. Perfect. So what are sources of data? These are all sources of data, research studies, and he says research studies is one line, like two words, but it's an incredible amount of like sources. Like for example, you have not millions, but like thousands of medical journals, like Nature. I can't really think of anyone other than Nature, but PubMed is not a medical journal. There's one that had the vaccine autism one that I keep forgetting its name. It's like with an L or something. Point is, research studies are an incredible source of data for example, physicians. Government agencies that tell us, for example, how many cases of syphilis there are, or so on and so forth. Yeah, Lancet, thank you very much. Government agencies can also help, like, for example, the WHO. Right now, everyone's listening to the WHO because of, or actually, no, governmental agencies are separate from the national, from WHO. But governmental agencies, for example, if there are cases of tuberculosis, you have to report them to the government. You have to report them to, there are certain diseases that you just have to report to the government. WHO is something different. It's more of an international organization rather than just a governmental organization. But the point still stands that these are all sources of data. Okay. Now I had a question: does inferential have to be directed to the population while descriptive is directed to the sample? Okay. Both take a sample and then they, for example, can happen after descriptive. All right. I'll just tackle quickly all the questions. So we're going to start from this one. Does inferential have to be directed to the population while descriptive is directed to the sample? It's basically both start with a sample and then they make their, for example, claims towards the population, assuming the sample is representative. It's not like one goes towards the sample and goes towards the population. Both of them goes towards the sample. Both of them, you have to start with a sample, but in inferential, it goes that extra step and it sort of puts a conclusion towards the population that it's studying based on the sample, if it's representative or not representative. Is inferential statistics more specific? more specific or less specific doesn't have anything to do with it. It's just that inferential statistics, they go one step further. They have the data that they collected, they organized it and everything, but now they want to actually come with a conclusion. For example, let's say we gave patients beta blockers, and then we just saw their ejection fraction. That's just descriptive statistics. We just gave them something, and then we're just seeing a specific piece of data. However, if we now actually give them beta blockers versus no beta blockers, and then see those ejection fraction versus those without the beta blockers, their ejection fraction, that's inferential statistics. You're actually trying to come up with a conclusion that then you can actually put onto a whole population. Inferential statistics happen after descriptive. If they choose to actually do inferential statistics, they have to collect some data. They have to organize that data. So yes, they have to go through a process of going or undergoing descriptive statistics in order to finally reach a conclusion and undergo inferential statistics. So I hope that answers the questions. Keep the questions coming. I'll just try and answer as many as I can. All right. Statistics is very important. However, there are some problems with it. It employs a reductionistic approach. In other words, it tries to find one small thing that might be the problem. For example, beta blockers, like I mentioned earlier, it tries to find one small thing and tries to see whether it versus placebo or something, or versus the standard of care, can actually solve or we can actually come up with a new piece of treatment that can be very useful for these patients who are undergoing heart failure, and so on and so forth. The problem with this is that maybe there is a problem beyond just beta blockers. Maybe there's a problem that heart failure patients are more likely to experience, or so on and so forth. For that reason, they made something called systems analysis, where they employ a holistic approach. Holistic approach means they take the entire system and try and see that maybe this part of the system is actually causing problems here. Maybe this part of the system is causing problems here. So all I need you to know from this slide: statistics, reductionistic approach; systems analysis, holistic approach. That's incredibly important, and you probably will get a question on it if he chooses to bring a question about the slide. But yeah, there are many different, for example, ideas where instead of just trying to focus, for example, on the let's take the yellow fever model. Instead of trying to focus on maybe the pathogen, just the pathogen, for example, where the symptoms it's causing. Instead, a systems analysis approach might take an approach of where the virus is coming from, or where it's staying, or how long the incubation period is. So a systems analysis helps answer a lot of questions. Can you repeat this, please? Sure. I'll do it with the example of the yellow fever model. Let's say, for example, we're studying the yellow fever model. It's the yellow fever. It's a disease, okay? Let's say we're only interested, statistics is only interested in, for example, the pathogen involved. That's it. We're just gonna study the pathogen. But a systems analysis would employ a more, overall, view, and like a sort of a bird's eye view of the whole pathogen, where it's actually staying, how long the incubation period is. For example, how long it takes until it's going to cause death, for example. Yeah, systems analysis is more generalized. It's not really focused on one single thing and trying to see if one single thing can change, for example, the symptoms or anything like that. All right. So I hope that is clear. Systems look into the problem and the context system. Exactly. So systems analysis, think of it as sort of this bird's eye view that's looking at the entire system altogether, trying to consider every single thing as a possible thing to study, while statistics really just focus on one thing in this huge map that we're actually focusing on. So, it's sort of a give and take, and that's why they have systems analysis. That's why they're statistical. Each one has its own good side or bad side. So there's no real one thing that's better than the other, but employed together, it can actually form a very, very good system. So thinking to systems is actually, solving problems as part of an overall system, as opposed to just looking to one thing, as opposed to just looking at it as to one thing in sort of isolation. You take it as a part of the whole problem, and that can be very helpful. Okay, so now we move on to statistical models. There's this quote that basically describes statistical models perfectly. Every single model is wrong, but some of them can be useful. Now, I'll explain this in a way you can remember. Think back to grade 8. You had this question where you had to, let me get a pen. There was usually this question. Can I not? Is it because it's editing? Yeah. I have no idea what happened, but let's share screen again. All right, and then just like that. I unfortunately lost the chat. Chat. Yeah, I lost the chat. I don't know if there's someone here who can help me, but I'll keep explaining until they help me.
Yeah, if you could look up, you can find, I think,
Yep.
3 dots, and then
Three
you can
dots.
find.
Yeah, I click it. Oh, there you go. Perfect. It's hiding behind the camera. Okay. There we go. Okay, so let me go to the pen. So remember back in grade 8 when you had this question in the word problem, and it would tell you that, I don't know, like little Timmy is going to throw a ball and it's going to go like this. So calculate the parabola, right? So here's why the model is wrong. This is a model. It's going to tell you the ball is going to land, for example, here, right? It's going to tell you it's going to land right in this area. But, you know, there are so many things that don't account, like, or so many things that account into the trajectory of a ball. There's air resistance, there's gravity, there's, a ball could be lighter than usual, heavier than usual. So although this model is useful, maybe it gives us an idea, okay, the ball's gonna generally go in this direction, it's not exact. And for that reason, every single model is wrong. There's not a single model out there that's right. Every single model is wrong, but they can be useful. They can give us an idea of for example, what this looks like. The simplest way to explain it, it kind of like is nitpicky, but you all know the model of Al Faisal in the ground floor, with the little buildings and little cars and everything. This model is technically wrong because the cars are still and everything, and the trees are not exactly there. So the models are wrong, but hey, it's useful. You can actually teach people where to go and everything, and it does have some use, but it's completely wrong, right? It's the cars aren't being still, the whatever. You get the picture. So all models are wrong, but you know, some models are useful. And the reason they're useful is because they simplify sort of, they give us a simplified version of reality. And that can be useful because if you want to explain to someone, having a visual sort of explanation is really good. So there are different types of models. There's a physical model, there's a mechanical model, there's a mathematical. The most important one that we're really focusing on here is probabilistic, right? Probabilistic is the most important one. It's the one we see most often with studies and everything. So why is it the most important? Because let's say, for example, you're in the clinic and you have a study that says that if you smoke, your chance of getting lung cancer is 20%. And if you don't smoke, your chance of getting lung cancer is 1%. These are probabilities. They found these using probabilistic models. But this is incredibly useful to, you know, convince someone to stop smoking, right? This is incredibly useful because you have numbers, you have cold hard evidence, you have an incredible study that can show you that, hey, if you smoke, you're going to develop lung cancer. So these types of models, they're great. Now, again, the models are not, you know, they're wrong, but they're useful. So if he smokes, maybe his chance is not exactly 20%. Maybe it's like 22, maybe it's 15%. But the general idea is that we can use this model in order to tell him or deter him from smoking. So probabilistic models are undoubtedly some of the most useful. Mathematical, like deterministic is like the one I showed you here, the little Timmy throwing a ball and it's going to be from a parabola. That's deterministic. You know exactly where the ball is going to land, assuming that, you know, there's no air resistance, no anything like that, nothing altering the ball. But probabilistic is incredibly important, and we have a full lecture on just probability, and it's really basic probability, but the idea stands that probability is incredibly important because a lot of the things in medicine, your risk of this, assuming that you have this, is 20%. Your risk of this, assuming you have this, is, for example, 15%. So a lot of medicine is that. A lot of medicine is just using percentages and trying to develop associations based on those percentages. And it's really important. Like, you guys took POD. I can't really think of an association being right. No, I can't think of an association. Do you guys take like Crohn's disease, or I don't know if you guys took Crohn's disease or something. The chat just disappeared again. Oh, there we go. All right, so you took Crohn's disease. So maybe you know that, hey, Crohn's disease is related to uveitis. They found that through studies. Uveitis is in the eye. So maybe if the patient has, you know, eye pain or like eye redness and so on, and then you see, oh, the eye like got uveitis, and then he tells you, oh, I also have abdominal pain, you might think, oh, there's Crohn's disease. And who helped you get that association? It's statistics. So that's just a little way to show you how useful probabilistic models are. So what is stochastic? Stochastic, even I don't know what stochastic is, to be honest. But I think it was in the systems analysis. Where did you even see it? I'm not sure where you saw it, but you know. Am I going insane? I remember seeing it as well. Yeah, I think in the last slide you explained. Just okay. I have no idea where it is, but oh, there you go, stochastic. Yeah, so stochastic relates to the theory of probability. Stochastic means that things are random, but you can study that random idea, right? So that's what stochastic means. The chat keeps disappearing. All right. I need someone to help me with this. Whoever is the second year. When I click on the slide, the chat disappears, and then when I click back on the slide, it just disappears. I have to keep clicking chat again to see if there's questions or not. I don't know if I can fix that.
If you want, maybe if you could stop sharing and then try again. But if that still doesn't work, I could read out the questions to you if you want.
All right, I'll just stop sharing and then let's just try one more time because it's kind of annoying. No, it's still the same thing. Oh, there we go. Oh, perfect. Now it's working. All right. So deterministic models, like I mentioned to you, they're, for example, here's the same one, by equations of motion-based, like, for example, the parabola to see where a ball will land. But we don't really care about them because there's nothing really deterministic in medicine. Like, you can't just tell someone you have a 100% chance of developing lung cancer because this doesn't work like that. Most of medicine just doesn't work like that. Instead, you use probabilities. And please remember that the yellow fever epidemic, it had a yellow fever model. And this model was used in order to find out, a percentage. And, he might ask this. Yeah, he might have asked this to the previous group. Stochastic relates to the random and how you can, for example, study randomness. I don't really know its exact definition, but like you can search it. But point is, stochastic relates to probability, right? Now, yellow fever model is important. He might just ask you this. This is just straight up memorization. Just know that the yellow fever model is probabilistic. It's the gold standard for explaining probabilistic models to students, but just understand that, hey, they tried to figure out what is the chance of people getting afflicted by yellow fever model, what's the chance of them losing it and then actually, getting it back, so on and so forth. So they did all of this by finding percentiles. All right, so this is where the person who asked evidence-based medicine, this is where it actually came up again. So again, we're going away from this tasting urine thing to find out if someone's diabetic, and we're moving away from it. We want to instead just, focus on trying to find ways to actually, number-proven ways, actually like science-proven ways in order to say that, for example, this is the best way to do this, this is the best way to do this, this is the best way to do this, and the best way that you can do that is with statistics. And that whole, paradigm where we shifted from traditional, like, hand-me-down, like, consultant give me information, instead we, switched over very gradually over to studies, and they, for example, give us the information. And this opens up the last principle in this entire lecture, which is lies. And remember how I told you that with this study where you, for example, convince someone that there's 20% chance versus 1% chance of developing lung cancer, he more often than not will probably stop, after learning this. I just made up the numbers, but the idea is that, hey, numbers can actually have a lot of convincing power. And if you sometimes use them in a way to actually, lie, you can probably convince a lot of people. Now, that's incredibly dishonest, and that's incredibly terrible. But you see it a lot. You see it a lot of the time. And, I can just give you a really easy example of how I can just misuse statistics. Let's say, for example, I have one population, and 50 people died in that population in the last year. And then another population where 50,000 people died in the last year. So which population do you want to be a part of, right? So the majority of you would say here. What if I told you that these people, there's only 100 people in this population, but in this population there's like 5 billion. Right? There's 5 billion here. I know it's like a crazy number, it's like 5 billion, right? So you're obviously going to now want to shift to this population because the rate of dying here is 50% once I reveal to you this number. But if I don't reveal this number, all of you will want to go to this population, right? And then there's the 50% chance of dying. So the entire idea is that you can use numbers however way you want. The only person who'll catch you is someone who's smart enough to read the actual studies and read what you're trying to present. So there are some tricks that people use, and I'll show you some of them. So here's one trick that people use. Like, let's say, for example, this was a a teacher in a high school, and the principal told him, if you pass the students, I'll give you a Ferrari. So he then presents the mean, because look, the mean is passing. Hey, the mean has a pass average. So then he gets the Ferrari. What if the next year he told them, I need you to fail all the students. If you fail all the students, I'll give you, for example, a Ferrari. So he'll just give him the median. It's the same exact piece of data. It's the same exact piece of data. But one average says 63, which is in the passing mark. Another average says 48. Now, people who don't know statistics, in other words, the general public, patients who come into your clinic, they won't be able to sort of pick out these sort of little tricks that people can use. You, as the physician, you're responsible to pick up these little tricks. And you know, when they get more complicated, it's the biostatistician's role to actually figure out that, hey, these people are putting these tricks up. Another trick that people have done, this is actually extremely applicable to the current situation with the current pandemic. I think around 2-3 months ago, Dr. Fauci was part of the, he's part of like the NIH, the medical infectious diseases thing. The point is, he was put sort of on this sort of trial where they're trying to ask him his advice and so on and so forth. And one person tells him that there are 5 case controls. All of them had patients taking hydroxychloroquine, and all of them had, for example, COVID, right? All of them had COVID, and a lot of them got better. Now, Dr. Fauci understands biostatistics, so he told them that, you know, a case control study is not as good as, for example, a random clinical trial. So for that reason, we can't really just jump to hydroxychloroquine. That was an absolutely beautiful answer, and it's the answer that every single physician watching that would have wanted to hear, because that is the actual answer that he should have said. Although case control studies were showing that hydroxychloroquine, and I'll explain to you why you can't just make this assumption. There were 5 case control studies, and they all showed that, hey, these patients that are taking hydroxychloroquine, they got better. But guess what? These patients were also taking glucocorticoids. These patients were also taking, they were on ventilation, on oxygen. So just attributing their improvement to hydroxychloroquine, it's dishonest. It's just dishonest. You know, you can't really say 100%, you know, it might help, but we can't jump and say that it definitely does help. And those are just some of the things that, you know, happens when it comes to statistics. People like to abuse the fact that people don't really understand statistics well, and then they can just make claims like that and people will believe them. But it's not as good if someone is savvy with statistics like Dr. Fauci, who came up with a brilliant answer, and it was an amazing answer. So again, people can lie however they want, using the same exact, you know, piece of data, presenting different things. Look at here, like this looks like a very drastic change, and here it looks like a very, you know, minimal, negligible change. But look, the y-axis has changed. So that's why the difference is very staggering here and not very staggering here. But otherwise, they're the same piece of data. They're the exact same piece of data. It's just presenting them. You can go either way. If your agenda is to prove that there's no difference, you can present this. And if your agenda is to prove there is a difference, you can present this. So the entire idea is that you can use statistics, and only people who actually, you know, understand what the person is trying to do will actually know that this person is misusing statistics. And that's pretty much the lecture. I will mention one thing. I think it was mentioned, but I glossed over it. But sometimes mistakes happen, but not because the person has an agenda, because the person is inexperienced. And that happens the majority of the time with medical students, which is absolutely fine. We're learning. We're not being held, you know, clinical trials, and we're going to determine the, you know, risk of thousands of nations dying or something. No, we're holding normal studies, just regular, you know, okay studies, then just trying to practice how to hone our skills in biostats and research and so on and so forth. So it's okay to actually learn like that. It's not that bad. But yeah, sometimes mistakes can happen due to people misusing statistics. Sometimes they can happen accidentally, and you know, it's your job as a physician to always pick up mistakes, regardless of whether it was, regardless of intent, and just point out that, hey, this is a mistake, and these are the reasons, and doing so in a very non-judgmental manner, just like how Dr. Fauci handled it. So yeah, there you go. A lot of examples, a lot of ways to understand statistics, but basically this entire lecture can be summed up with population, sample, statistic, parameter, and evidence-based medicine, how it's important and better than just tasting urine from, you know, to see if someone's diabetic. and how models are useful, but they're all wrong, and we can't really just determine. We can't use them as deterministic models because nothing in medicine is deterministic. So I hope that this lecture is good with everyone. If you have any more questions, I'd be happy to take them. Other than that, we'll probably move to the next lecture. So I'll get that ready. If you guys want to take like a break or something, I'd be more than happy to take one. All right. Discard. Could we? Yeah, I don't mind starting. I'm trying to share the screen. All right. So I think the majority. I think we all want to start just really quickly. So that's lecture 1. Just 1 sec because I have to take off the animations. All right. Yeah, maybe. All right. We'll see what happens. Maybe we finish this lecture pretty quickly. We'll see what happens. Can you repeat the whole thing about the yellow fever model? All right. So before we start, oh yeah, thank you for reminding me. Whoever said to enable editing. Oh, I can't enable editing because the thing's in the way. Oh, there we go. I can do it. Oh, well. To reopen it. Okay. So let's go back to the yellow fever model just for a second. I forgot exactly how it went, but the main purpose behind it is not understanding how they did it. It's just understanding that they are using a model to determine a probabilistic event. For example, they're using, I need to set up the animations again. For example, they're using, let's say, for example, we want to know, let's say someone got the yellow fever. And then I want to determine, after getting the yellow fever, what is the chance of getting yellow fever? Again, assuming you already got it. So that, let's say the percentage was, I don't know, like 30%, I don't know. So point is, that is a probabilistic model. I set up a certain event that I wanted to happen, and I set the conditions and everything, and then I would see how often would it happen. And once I get how often exactly it would happen, then basically I would report it as such, and that whole paradigm, that whole example, is just to give you the idea that, hey, this is what a probabilistic model looks like. So in the exam, he won't tell you what the yellow fever model is. He'll just tell you the yellow fever model is an example of, and then he'll tell you deterministic model, physical model, mathematical, and the answer should be probabilistic model. Okay, that's what it's mainly about. And I hope you got it. All right. Now let's start with the second lecture. Second lecture is actually pretty easy. It's not that hard. It's the last lecture for today, at least. It's a bit long and a bit difficult. But let's, so we talked about all of this. We talked about descriptive and inferential statistics. One describes, the other, needs to find the data, just like how descriptive statistics is, but it also needs to form a conclusion. It needs to form a sort of thing that we can generalize onto the population to sort of give them a better treatment, or come up with a piece of information to help, physicians in the clinic or something like that. So let me get the pen. All right. See if I can move this here. There we go. I can move this there. Perfect. Okay. Our estimation and testing hypothesis. Oh, what? So what? I'm assuming you're saying what are estimation. All right. So testing hypothesis is an entire lecture by itself. It's probably the first lecture you'll see after the midterm. It is a lecture by itself, and it's going to take like an hour and a half to explain. So we're not going to go over it. What testing hypothesis basically means is trying to figure out whether a drug works or not based on the data that you have. So that's what testing hypothesis is. Estimation is just trying to estimate certain aspects of, for example, a treatment or something to be able to predict future outcomes or something like that. So the entire idea is that you are actually using the data you have to come up with a generalizability, to come up with something that you can sort of predict the outcome of. So the main idea of inferential statistics is that you are forming an inference. In other words, you're forming a conclusion based on the data you have. You can't do that with descriptive statistics. Descriptive statistics, they're only like, hey, here's the mean, here's the median, here's a standard deviation. All right, work's done. And although that can be useful, the more inferential statistics are more useful than that. Yeah. So yeah. Estimation, like I mentioned earlier, estimation is just you try and estimate, for example, the prevalence of I don't know, COVID, yeah, COVID-19 among adults and living in Riyadh. So again, this is when you estimate the prevalence, for example, in a small sample. Like let's say in a sample of 100 people, you get 20 of them with COVID, all right? If you have 20 COVID in your sample of 100, that means probably if, for example, Riyadh was 10 million, then you'd have, for example, 20% of those having COVID. So notice how I didn't need to, analyze all of them, but what I could do is I could make a conclusion on all the population based on my small sample. So I can make a small estimation based on my sample. In other words, I can make a conclusion based on the sample that I have. Testing hypothesis is an extremely long concept, and I don't think we have time at all to go over it now. We have a full lecture for it after the midterm, inshallah. But basically, it's trying to see whether one medication can be better than another, right? Or one medication can be better than placebo, or one medication better than the standard of care, so on and so forth. And we do that by setting up hypotheses and seeing whether or not they're being, for example, extremely rare to get or not. And it's extremely complicated, and I don't think I can really explain it in just 1 hour, in just a few minutes, or rather. In fact, even in an hour, I can't explain it. That always takes me like 2 hours. Point is, we talked about this a lot. This is descriptive and differential statistics. Descriptive, you just describe, and differential, you make conclusions. Data, we talked about data. It's information that you can gather. Data is essential because we get information. Only when we provide information are we able to make a conclusion out of that information. All right, now, sometimes when you collect data, the data is going to be really unorganized. And that's what we call raw data, right? So he has an example here. It's the CAM study. We're using alternative medicine. Alternative medicine means like, we're going to do like psychic stuff, or we're going to give him like herbs and stuff. And that's all called, alternative medicine, like hypnosis or something like that. Point is, they did a study. This is a regular example, and he has this table. So you can already see there are some problems with this table. First off, it's not organized at all. This is still the first stage. He just collected the data, and he might organize it later on. But notice there are some spots that are just empty, right? Just some spots that are just absolutely empty. And there is, if you have a keen eye, I'm pretty sure everyone has a keen eye and notice this, 444. So someone is 444 years of age in this study. Now, this will be called something called an outlier. An outlier is like an extreme value that just differs from the entire data set. But there's an important concept I need to share with you right now, just because we're at this point. Now, it's not going to be helpful in your midterm, but it's extremely important you understand this now because it's going to be helpful in your final. All right, so this 444, there's two things that can happen, or a lot of things that can happen. Like, here's the thing: would you keep it, or would you say no, it's impossible, no one can be 444? I'm going to take it off. I'm going to take this entire I'm going to adjust it back to 44. So can you do that? Do you think that you can do that? I just want to see some people say yes or no. So if you say yes, that means you'll change it back to 44. A lot of you are saying no. I'm happy. I'm incredibly happy. You keep it, because the only way you can change it is that you provide justification. Saying that 444 is impossible, so we're gonna change it. That's not justification. That's just absolutely ridiculous. You can't just change it just because you think it's impossible. Which brings me to the thing that you need to know for your final. Can someone be 40 feet tall? All right. So do you think someone can be? Just say yes if you think you can be. All right. All of you are saying no. Now here's the important part. All right. Oh, hold on. All of you are saying no. I need to understand this. So it is possible for someone being 40 feet tall. It is possible for someone being 40 feet tall. So we can't just say, oh, I found, for example, let's say we're measuring height. If I have something, for example, 40 feet here, and everyone else is like, I don't know, like 6 feet, 5 feet, so on, I cannot say at all that, hey, the 40 feet tall, that's freaking stupid. No way on earth is someone going to be 40 feet tall. I'm going to remove it or I'm going to change it. No, this is not allowed. This is not allowed. You cannot justify things just because they seem outlandish. You justify things by, for example, having the contact information for this person, going and asking them, sir, how tall are you? And then they tell you 4 feet. And then you realize it's a mistake. Not by saying we'll remove it without justifying it just because we think it's outlandish. So again, remember, can someone be 60 feet tall? I want everyone to say yes. I want everyone to just spam the whole chat box with yes. Because hypothetically, someone can be 60 feet tall. You know, back in like grade 10 or grade, oh, when was they make the change? Back in like grade 9, we used to have, I mean, even you remember this, maybe if you were in grade 2 or something, we used to have our weekends on Thursday and Friday. And we started our weekday on Saturday. You all remember that, right? So, you know, I had a question in my probability lecture in my like grade 10 class, and it said something really stupid. It's like I answered it correctly, but the point is, it said Friday will never be a weekday. And I just sat there. I'm like, no, like you can't just say that. Like it might be a weekday. You don't know what's gonna happen. Like I get it that oh Friday prayer, so it has to be a weekend. No, you don't. You can't make that assumption. You know, look at how we all thought that it was gonna be Saturday to Wednesday forever, and now it changed from Sunday to Thursday. So the entire point of all of this is that if I ever ask you in the future, is it possible for something to happen? I always want you to say yes. Is it possible for something like this to happen? Yes. I never want to hear no for anything. Now, obviously, you're going to sit there and you'll be like, well, Khaled, I mean, I have a cat here next to me, and the chance of this cat turning into a demon and then eating my face is 0. I'm going to sit there and be like, okay, yeah, of course it's 0. But like, you get the point that I'm trying to say. For biostats only things, I always want you to answer yes when I ask you, is it possible? Right? Because you need to open your mind up to this concept because it's incredibly important. It's incredibly, incredibly important. Because when we get to testing hypothesis, you're going to see there's going to be like a 1% chance of something happening, and I need you to say yes. It can happen. Now look, just 1 second. Yeah, I saw some questions. So yeah, this is a good question. Is there, so that there's no such thing as outliers? There are outliers. This is an example of an outlier. My point is that this outlier doesn't mean that you have to remove it. It could be someone who's 444 years of age. You don't know. You don't know. I'll make it easier. Let's say, for example, it was 119. Someone, or 109. Let's say 109. It's more believable. So 109 is an outlier, but it could still be possible. It could absolutely be possible. So, but isn't this a typo? Look. Hold on. Let me just make sure. This more, 99% of the time it's going to be a typo, right? My point is you cannot remove it just because you think it's a typo. You have to actually provide justification. You have to say, hey, we have the contact information for this patient. We have to actually go back to the person and actually make sure that, hey, this is the thing. What most people do is they just look at it. They say, oh, this is 444. I'm going to change it to 44. And I mean, you can do that, but like, that's dishonest. You should not be doing that. You should be justifying why you changed an outlier. And yeah, this entire tangent was just because I wanted to mention to you guys that you can't really tell whether it's it might be true. You don't know, right? Now here, obviously, it kind of doesn't look true, but like my point is, you can't just remove it just because it looks outlandish. It might be true. Let's say it was 109. Are you going to remove it just because it's 109? No, someone can be 109 years of age. You don't know. So the entire idea is that things are possible, and you can't just remove things just because you think that it might not be possible. Everything is possible. In biostatistics, everything is possible. So the only way to fix this typo is by going to the contact information for this patient, which most studies have. Most studies usually, they get either an email or a phone number of the actual participant so they can follow up with him or her. And they confirm it. They go back and they say, hey, sir, we just wanted to confirm something. How old are you? And then he says, oh, 44. And then, okay, that's a good justification. You changed it because you made sure it's 44. But you don't just change it because you think, oh, 444, it doesn't make sense. You can't change it like that. So yeah, the entire point is that don't change things because you can't justify it until you justify it. And whenever I ask you in biostats, is something possible? I always want to hear you say yes, okay? In the exam, if he tells you, look, don't kill me for this. In the exam, if he tells you, what's the chance of Sunday coming after Monday, put 0, okay? Don't listen to me now, just put 0. Well, but during the classes, during the crash course, when I ask you, is something possible? Always say yes, all right? And we'll get to that. We'll get to the probability and everything. But I hope you understood this principle. I hope you understood, and I hope we're all on the same page when it comes to is this thing possible or not possible. All right, so he keeps showing you how there are, for example, empty spots and possible outlier that we probably need to deal with later on. And then they finally, analyze the study, they organize the study, so on and so forth, and they came up with conclusions. Now, we don't really care about the conclusions. What we care about is how do we organize the data. So there are different types, and this is our summary slide. They're actually missing one, which is like time to x, time to x. So we're going to start with the first one, which is called nominal. Nominal, basically, I'm going to give you just a quick little summary. Nominal basically means that, there's no order. There's absolutely no order. And it's just basically is, like, for example, categories, male and female, smokers and non-smokers. Nothing is more important than the other. Everything is equal. They're just different categories. Ordinal means that there is an order, right? Ordinal, there is an order. No. Okay, let's go back to the question I said. If he brings you a question, what's the probability of Monday coming before Sunday? What do? You press 0 because there's no chance of Monday coming, before Sunday, right? So the one I mentioned was that Sunday after Monday. Sunday's not going to come after Monday, so just put 0, right? He might ask you this. I'll show you more examples when we get to the probability lecture. Just forget about it now. So right now we're talking about how to organize data, right? How to organize any data. And don't worry, if you didn't get the 0 thing that I mentioned, we're going to come back to it in the probability lecture. Just forget about it. I'll give you an example. So let's just repeat all of this. Let's just refocus. Forget about probability. We'll cover it in the last lecture. So let's talk about nominal. Nominal, like I mentioned earlier, if we have, for example, different categories like male, female, like smoker, non-smoker, like blood types, for example, A, B, A, B, AB, and then O. Listen, if he asks about the 444, listen, I'm going to make it very easy for you. He's not going to ask about it because this is very, Dr. Hassan's questions are incredibly well written. He's not going to ask you this question. But if he asks you, yes, it is possible. It is possible. There's nothing called not possible. Absolutely nothing. But he won't ask you something like this. Instead, he'll keep, whether or not it's possible or not possible is not the main concern for this lecture. This principle is important for the final lectures, right? So just keep this idea in your mind that when you're in the crash course, whenever I ask if anything's possible, always answer yes, right? Always answer yes, because anything can be possible. In the exam, be more practical, right? Be more practical. He won't ask you is 444 possible. He won't ask you this. What he'll ask you is something very obvious. Like, for example, what's the chance that a person will die someday? Like, this is 100%. Like, this is very obvious. He just wants to see if you have the concept. He's not going to try and trick you or something like that. His questions are very, very well written. So forget about probability right now. Forget about probability. We'll talk about it when we get to it. But now let's just refocus again and talk about how to organize data. Let's talk about how to organize data. So the first one is nominal. This is our first one. Nominal means we have different categories, male, female, smokers, non-smokers. I mentioned this. Ordinal, from its name, ordinal, there is an order. So now the things actually matter where you put them from. Remember how I told you nominal, nothing is more important than each other? No, in ordinal, there are things that are more important than each other. For example, think of a race. First is better than second. Second is better than third. Third is better than fourth. But the important part is that, the difference between first and second is not the same as the difference between second and third. So although the order is important, the magnitude, in other words, the actual number, isn't that important. First to second, maybe first was like he finished in a minute. Second, he finished in 2 minutes. Maybe third finished in like 10 minutes. So notice how the difference between one and second was just like 1 minute. But for example, second and for example, third, it's like 8 minutes or something. So, ordinal, there is an order, but the difference between one order to another doesn't really matter. Now, stages of cancer, stages of cancer can actually be considered like stage 1, stage 2, and the difference between stage 1 and stage 2 is not the same as stage 2 and stage 3, stage 3 and stage 4. So yeah, that would be considered ordinal. So a level of pain, for example, yeah, you're 1 to 10, that is considered technically, or actually 1 to 10. Yeah, because for some people, 5 to 6 is not the same as 9 to 10. So, especially with a pain scale, it's very subjective and it's very different from one person to another. So a level of pain is an example of ordinal data. Another example is, when you do those surveys that every medical student does, where they put strongly agree, neutral, disagree, strongly disagree. That's an example of ordinal. You're organizing, and technically, you might argue that, hey, the difference between strongly agree and agree is the same as, strongly disagree and disagree. But what's the difference between agree, and neutral, right? That whole area is very, very ill-defined. What's an example of quantitative ordinal data? We'll talk about it. So sometimes you can quantify ordinal data, and we'll see it. So for example, let's say I have first, second, and third. My cats are going crazy. Let's say, for example, we have first, second, and third. I can actually give them numbers. I can give 1, 2, 3. I don't know what that means, but we'll talk about it. So you can actually quantify ordinal data. We'll discuss it. Look, I know you guys are not. I'm just giving you a little summary. We'll understand all of them what they mean. The basic idea is that nominal is just categories. There's no order. Ordinal, there is order, but there's no real importance between one to another. Discrete, there is order, and they're usually numbers, and there is an importance between the two numbers. And we'll see all of this when we get to it. So keep this idea in your mind. We'll still revisit nominal, ordinal, and discrete over and over and over again. Let's start with the first one, nominal. It's the easiest one to understand. You have different categories. For example, male and female. These are two different categories. No one's more important than the other. For example, smoking and non-smoking, no one's more important than the other. Blood types, no one's more important than the other. All of these are just different categories. Even like, I think he mentioned also marital status. Again, single versus married versus divorced. None of them take a certain order versus another. It's not like being single is better than being married, or vice versa. So the general idea is that when you have categories that fall into different, for example, groups, and the groups aren't really ordered in a specific fashion, then you want to organize that data into nominal. So does everyone understand nominal so far? He has different examples, such as, for example, smokers, non-smokers. For example, drug versus control. Age could be, age is not considered a nominal data. You see, age is considered discrete, and we'll get to discrete. But age is continuous. If you take age as years, it could be discrete. If you take, for example, age as, for example, you're going to say he's 6 years and 12 months and so on, or like 5 months or so on, and then it's continuous. It's the same thing with days. Like days, it can be continuous or it can be discrete. If you say, for example, if you say 11.5, true. Yeah, like honestly, if I say 11.5 in the hospital in front of a consultant, he'll laugh at me. But like, it's true. It's true. You can say 11.5. It's the same thing with days. I think days was the question that broke my batch. Like it broke the spine of my batch. Half of us put continuous and half of us put discrete. And the truth is, you can put days as continuous. You can say 6.5 days. There's nothing wrong with it. Even age, age you can say 11.5, 11 years and a half. It's fine. Like there's nothing wrong with saying it. I don't know why a consultant would laugh if I said it, but this is the truth of our world. Point is, nominal categories, right? So nominal, you have different categories. Like for example, smokers, non-smokers. You have, like here, blood types. You have A, B, and O. The most important thing is that no other group is more important than other. So age and days would be continuous, and years and discrete. I think age, all of them continuous. I think age, no matter what, is always continuous, right? So age, whether it's years or days or anything, it's always continuous. At least this was the answer that I put, and I got, it was right for us. So continuous, technically, days should be continuous, and age should be continuous. Now, but definitely don't put age as nominal. Age is not nominal, right? So nominal, let's just focus on it for now. Nominal, you have different categories. No one's more important than the other. And I hope everyone right now understands nominal. He gives you more examples, like for example, married, divorced, single. Again, no one is more important than the other. All right, analysis of nominal data. Now this is important. We'll actually talk about it when we reach mean, median, and mode in the next lecture. But the entire idea is that you can't really give a mean for nominal data. Now why is that? Let's say, for example, we give every single blood type a number. Let's say we give blood type A, for example, 1, blood type AB 2, and blood type B gets 3, and then O gets 4. Now, whoops. And now this having a mean doesn't make sense, because what if you get 1 plus 2 plus 3 plus 4 and then divide that by the number of terms you have? You're going to get 2.5. What on earth does 2.5 mean? It doesn't mean anything. So don't use mean for nominal data. Don't ever use mean for nominal data. That's what this slide is trying to say. And we'll revisit this in the next lecture. All right, so you can use mean only for one instance, one instance and one instance alone. let's say we have, for example, male and female. And let's say we have, for example, 2 male, so 1 and 1. And then we have, for example, 3, 4. So we have 8 females and then 2 guys. Now, if we give the 2 sort of groups, 1 and 0, now we can actually work with the mean. So what happens is, let's say we add them and find the mean. So it's going to be 1 plus 1, that's 2, and then plus all the zeros, that's going to be like 0. So 2 plus 0, that's going to be 2. If we divide it by the number of terms we have 10. We're going to get 2 over 10. So that helps us that tells us how many men we have out of the entire study. We have 20% of our study is men, and that makes sense. 20%. And that makes sense because if you look here, we only have 2 out of 10. So that's the only instance where you can actually use, the mean for nominal data. Only if you apply 0 to 1 to the categories that you have. Now, someone mentioned mode. Mode is actually one of the best things that you can do for nominal data, because the mode sees how frequent something is. So for example, if I have, let's say, blood groups. Let's say I have blood groups, and I have 1, 1, and then 2, 2, and then 3, 3, 3, and then 4. So using the mode basically sees which of the following is the most frequent to keep coming over and over again. So in this instance, it's 3. Look, 3 is apparent the most times. So finding out the mode is incredibly important because you find out the most common of all of them. We'll get to how you can arrange nominal data in ordinal. Just keep this idea in your out of your mind. The entire idea is that you can actually assign numbers, and the reason we assign numbers is because we want to actually calculate something, right? So when we have nominal data, when we have any piece of nominal data, we can actually assign numbers to certain categories. For example, all those who have blood type A, we can give them 1. All those who have blood type AB, we can give them 2. All those who have blood type B, we can give them 3. All those who have blood type O, we can give them 4. Now these numbers, although one is more than the other, we don't care about that. We don't care that 1 is less than 4 or 4 is more than 1. We don't care about this because at the end of the day, this is nominal data. We're only giving numbers so that we can calculate things. Calculate things like what? Like, for example, the mode. Mode is incredibly useful in nominal data because we can find the most common thing. Let's see. All right, let's just take a second and see the questions. How can you arrange nominal? All right, we'll see this in a second. If there were 7 females, then we divide 0 out of 10. It'll be 0%. So how does it help? Yes. So look, in this case, if you have 7 females, you flip it. You actually put the it depends on what you want. In this case, I wanted to find out how many men were in the study. If you want to find out how many females were in the study, you give females the 1 and men the 0. So let's say we have 7 females in the study and 3 men. I would give men the 0. So 0, you go for men, 3 zeros, and then 7 ones. That's 5, and then 6 and 7. All right, so basically, it's going to be 7 over 10. It's going to be 70. So the idea is that whatever you're interested in finding, you have to give it the 1, and whatever you're not interested in finding, you give it the 0. Right? So that's the only way where you can use mean and nominal data. Any other time, you just do it. Yeah, another way you can do it is just subtract it. But there are numerous ways to get the same answer. You can do it whichever way you want. You can give the females 1 or them 0, or you can do it the opposite way. It's completely up to you. You can't give birth to 0.1 baby. What is happening in the chat? Doctor, they say sustainable birth is 2.1. I know this isn't nominal. I don't really get your question. All right, it's easy to subtract. Yeah, we addressed this. You can't give birth to 0.1 baby. So far, the nominal is the only important way unless it's future. All right, I'm getting lost by all of your questions, guys. So, all right, let's start with the first one, the 2.1. So, doctor, they say sustainable birth rate is 2.1. I know this isn't nominal. What exactly do you mean? I think that's why we give natural numbers and assign numbers to nominal data. Guys, I think there's like a whole world happening in the chat, and I have no idea what's happening. Is there like a second year that can help me?
Yeah, I think we should continue because it'll make more sense to go on.
Yeah. So again, guys, a lot of your questions, like they're things that will come up later. So don't worry. ask, if you have a question about something that I mentioned that you think is misleading or you don't understand it, it's fine, ask. But I'm seeing a lot of the questions, there are things that are coming later on. So just like wait until those topics come. Point is, I hope the only things that I want you to come out understanding nominal. I don't get when exactly to use nominal. Okay, so I'm going to repeat nominal data completely to sort of explain to you. I just need a whiteboard. Okay, so look. Nominal data, we have categories. Now I'm going to take one example. I'm going to show you two examples so we can compare them. First off, we're going to take male and female, right? You can all agree with me that this is a form of nominal data, right? Because you have two different categories and none of them are more superior to each other, correct? When it comes to, for example, blood types, we have four different. So there's A, B, there's B, and there's O. These are both considered nominal data, okay? Now, one is given the term binary. Now, this is something new that I'm opening up with you guys. Binary means we only have two groups. When we have more than two groups, like for example, 3, 4, 5, 6, like for example, here we have 4, then this is given the term as, 3 or 4. It doesn't really have a term. So it's binary versus, 3 or more. Now, let's try and analyze this. Let's say we have, for example, 4 females and 6 male, for example. So now I'm interested in finding how many males there are, so I'm going to give them the 1. It doesn't matter which one you give the 1 because you can find it out regardless. But let's say I'm interested in finding the males. I'm just going to make it easier for myself. I'm going to start by giving them the 1. So I have, for example, male, 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 and then female, 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 female. So what I do is I give them the 1. I give these guys the 1, and I give these guys, or gals rather, the 0. So it becomes like this: 1, 1, 1, 1, 1, 1, and then 0, 0, 0, 0. Now these are all 10 terms. So if you find the average, if you find the mean to be exact, you will get 6 over 10 because you're going to add all of these. So 6 over 10, that means 60% of our study is going to be male. Now if I find the mode, what do you guys think is the mode in this case? Is it 1 or is it 0? I just want to see if everyone can agree with me. The mode, remember, it's the thing that gets repeated the most often. So all of you agree that it's 1. Perfect. So that means in this study, who is more common, males or females? Males. Perfect. So now notice how in this example, we're not going to be able to use the mean because the mean is just so useless. Let's say here we have one person who has blood type A. So we have one person, or we're going to use this. We're going to use this. One person with blood type A, one person with blood type AB, one person with blood type B, and one person with blood type O. Okay? Now, unfortunately, I wanted to use the mode, but all right. Let's say there was one person blood type A, one person blood type AB, 2 people blood type B. So I'm going to write this down for you. A, and then AB, and then B. Let me move the chat bits. B. So we have 2 people who are B, and then we have O. All right. So this is going to translate to, I'm going to give A 1, right? I'm going to give AB 2. I'm going to give, the 2 people who are B 3, and then 3, and then the last person is going to be 4. Now I could choose any numbers. It doesn't have to be these numbers. I could give any numbers, but I just chose these to make the math simple. So if I divide by 5, what's the mean going to be? 1 plus 2. Let me see what I got. Kind of embarrassing that I have to use a calculator, but 1 plus 2 plus 3 plus 4. So it's 13 divided by 5. All right, so the mean, guess what? The mean is 2.6. Now, what on earth does 2.6 mean? It means nothing because it just doesn't make any sense. 2.6 means absolutely nothing. We only have 1, 2, 3, 3, and 4. So the average is 2.6. 2.6 means absolutely nothing. It doesn't make any sense. So 2.6, unfortunately, can't be used. The only time where you can use mean, notice how here mean, we did use it. It was very useful. The only time where you can use mean is if you have a binary piece of data, binary piece of nominal data, which is like male, female, smoker, non-smoker, only 2 categories, and you set them up in such a way where it's 1 and 0. 1 and 0, only 1 and 0. You can't use 1 and 2, you can't use 3 and 4, only 1 and 0, okay? Unfortunately here, the rule isn't there. We're not using 0 and 1, and we don't have binary data. We have data where we have 3 or more groups, right? In this case, we have 4. However, the mode is still very useful. The mode actually is incredibly useful because we can find out what's very common. What if you give females 2 rather than 0? Also doesn't work, because then it's going to say basically, let's say we gave females 2 and then males got 0. It's going to be 2 plus 2 plus 2 plus 2. It's going to be 8 out of 10, which is wrong. It's not 8 out of 10. It's 4 out of 10. So again, you can only give 1 and 0. Can give 2 and 0, can give 3 and 0, can give 4 and 0, can give 1 and 2, only 0 and 1. I hope that's clear. With this example where we have, for example, A, B, and the blood groups, we can't really use mean because the mean is not going to help us. The mean can only help us if it's 1 and 0 and binary data. The mode here can help us. So what do you guys think is the mode here? In this example, the blood types. Remember, we have one who's A, one who's AB, and then 2 guys who are B, and then 1 guy who's O. So 3 or B, I think. So B, so blood type B is the most common in this study. That's why mode is incredibly useful. Now median, it's not mentioned here, but median can also be used. Median doesn't really help us much because it just finds the middle value. So whatever number you put, for example, if I put here 3, it's gonna be a debate between these two. But if I put B as 4 and then this as, for example, O as 3, it's basically going to be O that gets the median. And I'll explain this to you. Let's say, for example, instead of putting 1, 2, 3, and 4 the way I made it, let's say I put it A as 1, AB as 2, and B as 3, and then O as 4. And then we have 2 guys who are B. Now, if I just changed it up, if I just put these guys as 4, and this person is 3, then he's going to be right here, and these guys are going to be right here. So the median, I made it O. I made it O. But here, it gets made into, for example, B, because B just happens to be the number I picked to be in the middle. So, median doesn't really have a role here because you alter it. It's not something that, you can really help. So I hope this really just cements nominal data. Once again, nominal data is categories, like, for example, male, female. It could be binary, which you have, only 2, like, for example, male and female, or smoking, non-smoking. Or it could be more than 2, which are, for example, blood types or marital status, like, for example, married, single, smoker, married, single, or divorced. So these are all not binary. They're the opposite of binary. And the only really useful measurement tool that we can use is mode, because it helps us find out what's the most common thing in our data set. But with binary data that is specifically geared towards 0 and 1, we can actually use the mean. So did everyone actually understand this? We can't use median because we can't order the categories, right? Yeah, exactly. Like, this is what I'm saying. Like, there's no true order. You are making the order by making the numbers. Like, there's no real order. The way you fix the numbers, you're kind of giving the numbers meaning, and you're kind of manipulating the median. Because maybe I want to start by giving A and AB 4 and 3. Now I'm going to alter everything. I'm going to change everything. So again, median doesn't really have much of a role. Mode has the best role, and mean only has a role if it's 0 and 1 and they're binary data. I hope everyone understood this. And yeah. We're going to move on to ordinal. If you don't understand, now's your chance to really stop me and ask me about nominal. So just random number, right? Yeah, it doesn't mean anything. Because look, it's just a random number. I could have chose 3,000, 1 million, and then, for example, these two get 3 and 3, and then this becomes 4,000. At the end of the day, the mode is still 3, right? It doesn't matter what these numbers are. It absolutely doesn't matter. I'm just giving them numbers because it makes it easier for me to find the mode using numbers as opposed to just, using a specific name or a blood type or so on and so forth. So I hope this is clear so far. Nominal data is the easiest to understand, hopefully, and kind of forebodes worse. Can you explain by example why you use only 0 and 1 and not 2 and 1? Okay, so look, if we use, let's say we use 2 and 1. I need kind of a new board. Let's erase all the ink. Okay, let's use 2 and 1. I'll show you how it doesn't work. Let's say males are, for example, 1. Let's say I have 3 males and then 2 females. So 2 for the females. Now, if you add all of these, and then divide by 5, you're going to get a number much larger than 5, which makes no sense. Like, I don't know. Like, it just doesn't make any sense, So 3 plus, for example, 4, you get what? Like, it's going to be more than 5. Like, it doesn't just, I hope you got what I'm trying to say. If these numbers were 0, however, then it makes up for a much more understandable equation. It becomes 3 out of 5, which just makes absolutely sense, as opposed to it being, for example, 7 out of 5. Like, this number doesn't make sense. But this number makes sense. This is 60%. So whoever asked, did you understand this principle? Yeah, okay, perfect. So this is why we use 1 and 0, right? Some people alter the denominator. Just don't. This is too complex. It's going to take me like an hour just to explain this. Don't. Okay, so yeah, analysis of nominal data. We talked about this. We explained all of this. That, you know, the only way you can really use the mean is by putting, for example, 0 and 1. Oops. Yes, by putting 0 and 1. Now we're finally moving on to ordinal data. All right. So what is ordinal data? Remember how we said that men, males are not better than females, or vice versa, so on and so forth. Smoking versus not smoking, nothing's better or worse. They're all just different groups. The same can be said when it comes to the opposite can be said when it comes to ordinal. So when we talk about ordinal, we're actually talking about different groups, and different groups that are ordered in such a way where one is different from the other, and the difference actually sort of matters. Because, for example, let's say first, second, and third. Let's take an actual example. Let's say first, second, and third. Now first, let's say he finished at the 1 minute mark. So let me just, I don't know why my mouse is doing this, but 1 minute mark. And then second, he finished at the 2 minute mark. And third, he finished at the 10 minute mark. Notice how the raw number, the actual raw number, the actual difference between the first and second place is not even close to the difference between the second and third place. They're still, altered as first, second, and third. So we don't care about the number that actually made them different. We just care that, hey, this person is first, this person is second, this person is third. I don't care if first and second were neck and neck, and third came like a day after. I don't care about that. The difference between first and second doesn't need to be the same difference as second to third, right? But what just matters is that there's an order. There's an order, right? First gets awarded the gold medal because he came first. The order actually matters, right? Someone sent an image. I have no idea what this is. All right. So I hope some of you understood what ordinal is. Now let's actually see some examples. For example, the injury. It could be a fatal injury, a severe injury, a moderate, or a minor. Notice how we're going down in the level of severity. So there is an order. There is an actual order to everything. It's not just like blood types where you have different things and nothing is better than the other. No, here there's an actual order. We have a very severe, and we're going to the least severe, right? All right, so this is an important point. You all understand why this is ordinal data, correct? I just need to see some yeses. I just absolutely need to see them. All right, perfect. All of you are understanding ordinal data. If one person doesn't, I don't mind repeating. But the important point, and here's where some of you might get lost. When let's say a fatal injury, let's compare a fatal injury and a severe injury. The difference between them doesn't necessarily, let me use this slide. The difference between them doesn't necessarily have to equal the difference between a severe and a moderate injury, nor the difference between a moderate and a minor injury. In other words, the difference between different types of injury, they could be different. For example, maybe a fatal injury could be like getting your neck chopped off. I don't know. But severe injury could be just getting your leg chopped off. These are completely different. A moderate injury could be just, an injury where you can, for example, a laceration where you get to see the bone. And a minor injury could just be a small little abrasion, just literally cutting your skin enough for just a little blood to come out. So the minor injury, when you compare it to the moderate injury, it's definitely not the same as a severe injury compared to a fatal injury. So the difference between a group to another, they're not equal. It's not like I have a set point where exactly this number is different from this number, and this number is different from the exact same number, and this. There's no numbers. It's just they're ordered, but there's no real magnitude between the two groups that actually says which one group is much different from the other. One group could be much different from the other, and the other could just have a slight difference. Just like how I showed you first and second. These guys were very close to each other. One came at minute 1, one came at minute 2. Third came like a day later. So the difference between first and second is not the same as first and second and third. Same thing with fatal injuries. Fatal injury and severe injury is not the same difference as severe injury to a moderate injury. So this is the main point of ordinal data. You have an order, but the difference between one group from another is not the same as the different group from another. All right? This is incredibly important. So like they mentioned here, the smaller the number is, it represents a more serious injury. So the smaller number gets a more serious injury. The bigger number gets, and you could flip it. You could have the higher number, but in this case, they just kept it like this, which is fine. And the difference between 1 and 2, so fatal injury and severe injury, is not necessarily the same as the difference between 2 and 3, which is a severe and moderate injury. This is the take-home points between ordinal and nominal, or ordinal and we'll see discrete later on, but this is the main take-home point. Is there a type of data where the difference is equal? Yes, there is a type of data where let's take, for example, I'm really skipping ahead, I'm really sorry, but like, let's take discrete data. So let's take day 3, day, I'm gonna write day 2 and day 1. The difference between day 3 and to day 2 is the same exact the difference between day 2 and day 1, right? So here you have an order, but the actual magnitude, the actual difference between one to the other is the same as one to the other. So, the entire idea is that the only way you can differentiate between ordinal and discrete data is the fact that you're using your own, intuition to figure out whether the differences between the groups is equal as you keep going from one group to another. So I hope you understand this right now. All right, so more examples. I told you the Likert scale, quantitative ordinal data. I'll show you. For example, quantitative ordinal data. Strongly agree. Let's say I put it as 1. Agree 2. Neutral 3. Disagree 4. Strongly disagree 5. Notice I'm using actual numbers to represent each one, but it's still but it's still ordinal data. I thought you said nominal data, but it's still ordinal data. So notice I can actually set these up in such a way where you're answering numbers, but you understand what every number means, right? So in ordinal data, the magnitude doesn't matter yet. The magnitude, it's not that it doesn't matter. The magnitude, here's the point. It's not that the magnitude doesn't matter, it's that the magnitude between one group to another is not the same as from one group to another, right? With discrete, from one group to another, there is, the difference is equal as you keep going from a different group to another. That's the thing. Yeah, there's no fixed magnitude between two groups, and that's a beautiful way to put it. Exactly. Magnitude in ordinal isn't equal. Exactly. This is incredibly important. You have to appreciate this difference because, he might just bring you an example and might just ask you, for example, using the example of what type of data is this? Is this ordinal or whatever? But he might also ask you, this could be, for example, he might just ask you just theory. He might just tell you ordinal data is, and then tells you, for example, has fixed quantities or magnitudes between different groups, and that's obviously wrong. So it's not. Don't just focus on trying. Don't anticipate him to only put questions in a way that he'll show you an example, and then you have to say what type of data it is. It could be completely different. He could just surprise you and just show you something different. He could tell you or ask you in a more theoretical sense. He tells you ordinal data and then asks you about the rules of ordinal data. That's why I'm really harping on the fact that the magnitude between one group to another is not the same as one group to another, because that might be the answer choice and that should be the right answer and you should pick it. But if you don't focus on that, if instead you just focus on the examples, you might not get it. So keep that point in your mind. So once again, nominal data, categories, we don't really care. There's no order. We can just give them numbers and we can use mean mode, yada, yada, yada. But here there is an order, and that order, although it's important, the difference between different groups is not the same, right? All right. Now, this is what someone was asking about, how to quantify ordinal data. And this is how you do it. You just let's say, for example, here, you have this data set, right? You have numbers, and you could argue that, hey, this is pretty much discrete, yada, yada, yada. Point is, they're giving their value of what they consider their anxiety before an exam. It's just like the pain scale. The pain scale is the exact same. The difference between a pain scale of 5 to a pain scale of 7 is not the same as 7 to 9. So this is considered technically ordinal data. So what you can do is you can actually rank it. So for example, you can assign each one a number. You can do it this way or the opposite way. I don't know why he did it this way, but you can do it the opposite way. So 1, for example, could be, or this could be 0, and this could be, for example, 3, and this could be, for example, 5, and then 7. 7 is going to be in the same place. And then this would be, for example, 8, and 9, and 10. You can do it either way. Doesn't matter. But here, in this case, he did it with 10 being the smallest number. Oops. What's happening? Can you guys hear that? Oh, that's so annoying. Okay, there we go. I have no idea what that was, but okay. How do I get back to keep? How do I go back to Zoom? It's not letting me go back in. Oh, there we go. Okay, share screen. My earbuds just like developed white noise, and it was really loud. I don't know what that was. But yeah, so all of you now understand ordinal and nominal data, right? So ordinal, again, this is a perfect example. Notice how if I go to pen, I go to chat. Dear Lord, I absolutely hate Zoom. All right, we'll take a break. Just give me 1 more minute to explain this. So you remember how we talked about how the magnitude isn't the same? So notice, between 1 and 2, we have 1 point of difference, right? And between 2 and 3, we still have a point of difference, right? We still have, this one. And between 3 and 4, okay, we got lucky again. We got a 1 point difference. But notice, from 4 to 5, notice, we have 2 points of difference. So this is what they mean by saying ordinal data. The quantity is not the same every single time. From going from between one group to another, the magnitude is not always fixed. It's going to be possibly different. So yeah, with that point mentioned, I hope you all understand so far ordinal and data. Scales are always ordinal. I mean, scales, no, depends on what scale you mean. Like if it's a weight scale is technically continuous data, right? Because it could be 67.5 kilos, 67.7 kilos, so on and so forth, right? So scales are not technically always ordinal, but there could be a scale, like for example, the 5-point Likert scale, where it says strongly agree, and neutral, so on and so forth. It could be considered an ordinal data. Now with that, someone asked for a break. I hope you all agree with them, because we finished ordinal and nominal data, and now we have discrete and the rest. So let's take like a 5-minute break. Just a 5-minute break. Continuous has decimal points. Yeah, we'll talk about it. We'll talk about it. Don't worry. Like you guys are jumping ahead. We still have discrete and continuous and another point, and then we're gonna talk more about it. Okay, 10 minutes. 10 minutes. All right, make it 10 minutes. All right, 10 minutes. So we'll be back here at 5:45. Okay, just 5:45. All right, 13 minutes. All right, I'll see you then. His courses, because they're so direct, a lot of people, and since there's like not that much content, generally a lot of people do well. So the A usually is 95. At least it was, I think it was for us. I'm not really exactly sure, but I remember there was a curve down, or whatever they call it, curve down or curve up. But the A was the A was much harder to get. Right, let me share screen here, because we're about to start. I hope everyone's back. Where is it? There we go. All right. So before we move on, I'm just going to quickly recap. We're going to go back to the summary slide. Remember, nominal data. Nominal data is basically, we're not ordering anything. It's just males, females, things like that. Mean can only be used with 0, 1, and mode is the best overall, no matter what. If you have only 2 categories, we call it binary. If it's not, there's no real name for that. It's just 3 or more groups. So that's nominal. Ordinal, you can have order. There's an order to the groups, and the group could be, for example, whatever you pretty much want it to be: level of severity, level of pain, level of whatever, how much you agree or disagree, so on and so forth. But the most important thing is that the magnitude, when you go from one group to another, does not necessarily have to be the same as going from one group to another. This is important. It could be the same, but that's just by coincidence. Usually it's not the same. It doesn't necessarily have to be the same. Now, so since we talked about all of that, sometimes you can rank it in order to give numbers, and the way you do that is by organizing the numbers first and then assigning the numbers. And then you can pretty much analyze these numbers. And I didn't mention this, but the beauty of this, like you probably look at it and say, why on earth why don't we just like analyze the numbers like as is? Like why do we turn them into these numbers, and then we analyze this sec here. So the reason is because this makes the numbers and in turn the statistics a lot easier. This makes the numbers easier, and for that reason the statistics becomes easier. In fact, there is a specific lecture about this where the statistics, there's two types. There's something called parametric statistics and non-parametric statistics, or parametric techniques, non-parametric techniques, parametric methods, non-parametric methods. So the entire idea is that if you work with easier numbers, that's just a layman term, but if you work with easier numbers, you can just use the easier numbers. You can just use the regular numbers and non-parametric methods. That's why he mentioned here, I think it was in somewhere in the slides. Yeah. So you can use these ranks as the new data set for analysis instead of the original data used in non-parametric data analysis. You don't need to know what it is. It's going to come in your final lectures. So just forget about it now, but just know that it could be used in non-parametric methods. That's what I want you to know. Okay. So now we finished nominal, ordinal. Now we have discrete. So what is discrete? Discrete data is when you have, for example, you want to describe numbers, but those numbers can't be half or 0.5 or 0.3 or 0.2 or 0.1 or anything like that. They need to be whole numbers, and they need to be integers. Okay, so integers means, for example, like +1, +2. Now integers can also be negative, but we don't want the negative either, because it doesn't make sense to say that the prevalence of a disease is, I don't know, -1 out of 100. It doesn't make sense. So the point is that we want to use integers because those are the numbers that describe discrete data. Discrete data means that you have integers and there should be non-negative. So for example, the number of motor vehicle accidents, you can't have 20.5 accidents. They have to be either 20 or 21. And the number of new cases of COVID, they can't be 20.5 cases. They have to be like 20 or 21. So the entire idea is that you can't really use discrete data to identify statistics that are, for example, using data that's like 0.5 or something. You have to use the data that can be described using integers only. So whole numbers, exactly. So whole numbers. So yeah. But notice the order and magnitude are both important, right? So the numbers are actual measurable quantities, or so on and so forth. No intermediate values are possible. By intermediate values, they mean, for example, when you go to 20 to 21, there's nothing in between. There's absolutely nothing in between. It's either 20, 21. You can't have 20.5, you can't have 20.7, you can't have 20.3, nothing like that. You can't use negative values. Yes, you cannot use negative values either. I think it was mentioned, but it's not here. Yeah, it is here. So the number of accidents restricted to non-negative integers. So yeah, so it'll make no sense. So you can't have -2 accidents, and you can't have fractions, because fractions ultimately will lead to decimals and so on and so forth. Like, why even mention that it's 120 over 60 accidents? Just say just 2 accidents and that's it. So you get the picture. Like, you don't need to use fractions. The only time we use fractions is when it's going to be a decimal, which you obviously can't use in discrete data. Discrete data, you can only use you can only use numbers that do not have decimals. They can't have ratios, nothing like that. Then we move on to continuous data. So continuous data, it is your best friend in the world. It can be anything you want it to be. So it can be time, it could be length, it could be anything. It can be absolutely anything. It can be represented with a fraction or represented with a number, like blood pressure. It could be a height, could be age, could be many different things. So sometimes you can, now I'm not going to explain further than that, like continuous is, I hope it's very obvious to all of you. And regardless of whether, like, if you change from, let's say, 59.5 to 58.5 and then 58.5 to 57.5, though, going 1 mark and 1 mark, they're all the same magnitude. How can you, okay. So someone's asking, how is the magnitude important in discrete data? Let's say we have 56 days, and then 55 days. and then 54 days. Now, the difference between 56 to 55 is always going to be the same as 55 to 54. In other words, the magnitude that you differ between from going from one piece of data to the other is always going to be the same, right? So it gives you an idea, especially, look, you might say, hey, what if we have data that's like, for example, 56 and 54 and then 53? You still get an idea. You might argue, hey, we're going from here to here, we're going 2, and we're going here and we're going 1. This doesn't mean that it's nominal. This doesn't mean that it's ordinal or nominal or whatever. This still means it's discrete, because for the simple fact that you understand that this is twice as much when you compare the difference as this. The numbers still mean something. The numbers actually tell you something. So the entire idea is that if there were to be a value in the middle here called 55, it would make complete sense to you. So the reason it makes complete sense to you is because the magnitude is always fixed between 1 point to 1 point. That's why they mention here a 1 unit change, a 1 unit change. For example, if there was 55 here, a 1 unit change in the value means the same thing regardless of what value you pick. So try not to confuse yourself by saying, hey, this is 56, this is 54, that means this is 2 and this is 1. No, doesn't make any, this is not how you want to think about it. How you want to think about it is that if you take any value and you minus it from like you minus 1 from it, you subtract 1 from it, and then you check another value and subtract 1 from it, that one that you subtracted is the exact same, it has the same exact meaning. Compare this to, you know, our first place winner and our second place winner who were neck and neck, and you compare it to a third place who came like a day after. It just doesn't make any sense. You know, it doesn't make sense to consider that the magnitude is same or fixed across all the different groups. So I hope this makes sense. Now, continuous data like blood pressure, weight, for example, serum cholesterol, these are all, for example, maybe serum cholesterol is like, I don't know, like 109.7. I don't know, like it could be anything, right? So it's not necessary, you know, it could just happen to be 109.0, but still, it's considered continuous data because it has the possibility of being 109.1, 109.2, 109.3. So can I say all the discrete data is ordinal data and not vice? No. Look, technically, no. Discrete data is not ordinal data, right? Discrete data, I mean, if you want to just think about it, but don't like understand it like this. Discrete data, you can consider it as ordinal data where the magnitude is fixed between all the points. Then yeah, you could think of it like that, but just try not to confuse yourself. Try to just keep it simple. Try to just understand that, hey, discrete, you have a fixed amount between the 2 different, you know, pieces of data. When you compare them with another 2 different pieces of data. When you have ordinal data, the difference between group 1 and group 2 is not the same as the difference between group 2 and group 3. So you have to appreciate this difference, but try and not go through this, you know, mental hurdle of, for example, discrete can be the same as ordinal, but the magnitude is important. Try not to confuse yourself like that. Just try and memorize each one as it is. I guess it is discrete for depth numbers because we don't have decimal places, right? Yeah. So exactly, I'm happy that you guys are answering. You guys are helping me. I feel so proud. So yeah, now we covered nominal, ordinal, discrete, and continuous. The last one we have is time to event. So time to event, it's sort of mixing continuous with binary nominal. All right, so this is our continuous, this is our time, and this is our binary. Now, it could be multiple events, but usually in most statistics, it's usually binary. So for example, time to death. So time is a continuous variable, continuous data, piece of continuous data. And death, well, it's a binary data. It's binary nominal data. It's either you died or you didn't. Same thing with recurrence. Either it recurred or it didn't. Same with remission. Either you know, it comes back or it doesn't. So it's the exact same thing. So I hope you know, you understand that the difference between continuous and you know, time to event, because time to event is just a mix of continuous as well as nominal data. It's sort of a mix between them. And for example, he might tell you there's a study that found the time to recurrence of breast cancer is, for example, 5 years if you have this surgery, so on and so forth. So what type of data is this? And then you have to pick time to event. So can you please repeat this part? Sure, no problem. Time to event. Remember how we talked about the 4 data that we just talked about, the nominal, ordinal, discrete, and continuous? Time to event is a mix of the first one, nominal, and a specific type of nominal that we agreed is 2 groups, which is binary, and continuous, which is you know, continuous data. So what is the continuous part? It's time. This is the continuous parts. And then the event is usually nominal, but it's usually binary. Most studies usually make it as binary. For example, time could be like 5 years and 3 days, whatever, and to death. So it's either death or no death. This is a form of binary nominal. Time to recurrence, again, time is continuous. Recurrence is, for example, nominal, binary nominal. And time here is, again, continuous. Remission is nominal, binary nominal. So I hope you understand time to event. Usually they like using it in cohort studies. Now, if I have to explain what cohort studies are, we're gonna spend another hour here. But basically just memorize that when you talk about cohort studies, and in these cohort studies, they like following up people. So like they'll interview them today, and then they might see them again in like 20 years. So it would be nice to have a piece of data that checks the time and checks to see whether they developed something in that time. That's why they like using time to event and cohort studies, because cohort studies follow people for a period of time. So I hope you guys understood this. If not, feel free to ask at any point. This data also arises in cohort studies where we follow observations. This is the same thing that we talked about. All right, now data transformation. Remember how we talked, this is probably the most confusing part, but just try to keep it as simple as possible. Don't try to confuse yourself with more information. Basically, if we have continuous data, let's say I have age, right? So I have age. What if I just say, I want everyone from 60, I don't know why my mouse keeps doing this, 60 to 40. I want to name all of these guys elderly, for example. So I'll give them a big E. And then everyone from, for example, 39 to 20, all right? They all get the name, for example, middle-aged. Now I somehow transformed continuous data, all the way to nominal data. We have two groups. We have elderly, we have middle-aged. So I can't help you during the exam and tell you exactly how to understand the question, but you have to sort of use your intuition. If he took continuous data, which is age, and then put them into two different groups, and these groups are organized into elderly and middle-aged, then that's most likely going to be data transformation, turning continuous data into nominal data. Let's say, for example, BMI. Let's take BMI. BMI is continuous data. It can be 18.5, it can be 18.2, so on and so forth. But there are certain categories for BMI. So this would be an example of turning continuous data to ordinal data. Get it? Because ordinal data will become basically, it's like, I forgot the exact orders, but it's like, was it overweight and then obese? And it's obese, morbidly obese, and there's like multiple obesities. Then there's like overweight, then normal, then underweight. So this is ordinal data. Even though the BMI, it's actually a piece of continuous data. The BMI can be 18.5, 18.2, so on and so forth. But when you categorize it in the standard categorization for the BMI, it turns itself from continuous data to ordinal data. So you just have to read the question and understand what the question is saying. And I hope this is clear. Isn't it ordinal? Yeah. So BMI technically is ordinal if you consider the categories it's in. So if, for example, if someone's BMI is considered 18 or 20, you would give him for example, classification of normal, right? So you give him normal because we use the ordinal system. We don't just use the continuous system. Can you repeat this, please? All right, so data transformation, it's very simple. It's when you transform the data from one type to another. So let's say, for example, we started with continuous data. The best example is BMI. BMI is a form of continuous data. BMI is literally just a number and then has a decimal place. So let's say, for example, someone's BMI is 20.4. Now, this 20.4, people used to use it, but then they realized that 20.4 doesn't really say much unless we categorize everything. So then they started categorizing BMI. They started putting BMI, for example, 18.5 to 25, and this is normal. Under 18.5, that's underweight. More than 25, this is going to be like overweight. So we actually turned this continuous piece of data, BMI, and we now currently use it as ordinal data because we want to order everything. We want to order everything based on how BMI is going to basically predict whether they're going to be, for example, obese, overweight, so on and so forth. Order is important. For after analyzing continuous data, it will turn into ordinal data to us organizing it, right? No, it depends. It depends. I just showed you an example of me turning continuous data into nominal data. I just have two groups, and no one is more important than the other, elderly and middle-aged, right? If I were to continue this graph even further, if I was to say, for example, 20 to 1 is going to be, for example, I don't know, like a young adults. I don't know, like I don't know how a 1-year-old infant is going to be considered a young adult, but you get the picture. Now notice there is technically an order. Elderly are more, are higher, have a higher age than people who are middle-aged. People who are middle-aged have a higher age than those who are young adults. So the idea is that you just have to read the question, just try to understand the question when you get to it. This example, when you only have elderly and middle-aged, this is an example of turning continuous data into nominal data. When you have, for example, a third group and they somehow do have an order, like elderly, middle-aged, young adult, this technically does have an order, then basically you're going to turn it into ordinal data. So I hope this, yeah, you can change it to ordinal, you can change it to nominal, so you can change it to suit your needs. I don't want to make it seem like one is more important than the other, but basically every single study has its own design, its own purpose. So you basically transform the data based on what you want to change it. Now, the reason people do this is because sometimes working with continuous data, like I told you earlier, when we work with ordinal data, sometimes working with the actual numbers is not, preferable. Sometimes you want to work with easier numbers. And so when you have, for example, continuous data and you don't like it, you think it's pretty much tough to work with, you want to use a non-parametric technique and so on and so forth, you turn it into ordinal data. And now the ordinal data is much easier to work with. So this is why most people use it. And I hope you guys understood what data transformation is. But isn't the difference between the different categories known? Technically, no. I can make the difference unknown. For example, I can make whatever I literally want. So I can do 60 to 40. Or BMI is actually perfect. I don't have a BMI. Look, 18.5 to 25. So the point difference is like around 6.5. Take that and go up a class. Go to overweight. Overweight is from 25 to 30. So look how 5 points of difference is not the same as 6.5 points of difference. That's why whenever we have, for example, a piece of like ordinal data, the magnitude doesn't really make much, like, I don't know, how on earth do I explain this? Like in one group, we have a point difference of 5. In the other group, we have a point difference of 6.5. So the magnitude is changing from one group to the other. If we take, for example, overweight and obese, you'll find that obese is going to be, for example, 30 to 35. It's still a 5-point difference. But when you compare it to the normal versus overweight, this is really difficult without showing you the BMI. But I'm assuming that you all got that. Basically, it's ordinal because the magnitude is not the same when you go from one class, one category to another. So it's about if the numbers are known or not. It's about the numbers being exactly equal. Yeah, I mean, in here I sort of made the numbers kind of equal, but like let's ignore that. Let's say I made it from, for example, 75 to 60, and then 60 to 30, and then, for example, 30 to 10. Look, I'm all over the place. So this would, let's say these are elderly, and these, for example, are going to be like young, middle-aged adults, and this is going to be like young adults. So this would be a form of, ordinal data, because since there is an order, elderly are, more, they have a higher age, middle-aged are less, and young adults are even less. So there is technically an order, but that order, the magnitude between differences isn't really all that clear. So because of that, we subject it to the data that is nominal, or sorry, ordinal, sorry. So I hope that, I think the BMI is coming up. I think it's coming up in the later slides, not in this lecture. So yeah, I hope, look, I swear to God, you guys, I knew that once I started with data transformation, people would get confused because they would be like, how would that be considered ordinal? How would that be considered nominal? Look, he's not gonna, most likely, he's not gonna be trying to trick you like this. You guys are really taking it way too many steps forward. So my humble advice to you guys is that really, all you need to know is that data transformation, you're turning one piece of data into another, and that's completely feasible. That's completely possible, and you're more than likely to be able to do that. It's completely fine, and you can do that. The reason you can do that is because sometimes some statisticians don't want to work with the continuous data that they have. They want to actually work with a non-parametric method. Maybe they feel more comfortable with ordinal data, so on and so forth. So they opt to change the data into a different sort of piece of data. That's all you really need to know about data transformation. Yeah, so get the data, classify them into groups. Yeah, if you classify them into groups, you get ordered data, and basically you get an ordinal piece of data. It could be nominal, depending on the situation, depending on exactly what you have. So that's the entire idea behind it. So the example of CAM, okay, so people are understanding, but someone's mentioning the example of the CAM. I don't want to move until we actually all understand. Right, so a lot of people are getting it. Nominal equal order and magnitude unimportant. Ordinal equal order is important but magnitude is unimportant. Discrete continuous, order and magnitude important. Yep, beautiful. If you can all know that, you're more than good for the exam. At least when it comes to nominal, ordinal, and discrete continuous. So again, there's still a bit more like time to event. We all know it's a mix between continuous and nominal data. And then data transformation, just transforming one piece of data into another. Continuous, for example, into ordinal, or continuous into nominal, so on and so, or yeah, continuous into nominal, so on and so forth. So there you go. All right, let's move on. If you have any more questions, feel free to ask. Chris, we listen to watch it. Yeah, I'm really sorry. I'm really sorry, Yusuf. But like, I prefer. All right, just 1 second. I'm really sorry for stopping the lecture for 1 second. But whoever asks, I need to address the problem, because if that person doesn't understand that point, he's not going to understand the things that are coming after. So I feel like it's a disservice to not really answer that question. And I'd rather just answer that question right now, just so we can deal with it and then move on. You know, we'll see what happens. Then maybe I'll stop taking questions. All right, in the example, we transfer continuous to nominal or ordinal in the CAM. And you mean in this example? All right, let's do this example, I guess. In the CAM data, we took, yeah, the age is a continuous variable. This variable will be categorized into groups. For example, age less than 30, age 30 and 40, age more than 40. In this case, we're only interested in the number of patients who fall into each category. So in this case, look, personally, I would call this ordinal, because you know, each different category, there is an order to them. One group is more elderly than the other. One group is younger than the other. So this is turning continuous data, which is age, into a form of ordinal data. Now, he doesn't give the answer, because honestly, he's not going to ask you this, but this is what data transformation looks like. We're turning age into, for example, putting them in different categories and seeing how, for example, we can turn continuous data into a certain different type of data, like in this case, ordinal. Cancer fighting. All right. Now, at this point, I'm not really sure if he went past this. I think the safer option is just to go over it. Do you guys want to go over the lab and self-study? There's only really one piece of information, which is how to draw the box plot. I really doubt he'll ask you it, but if you want me to go over it, all right. Do you guys mean yes, go over it, or yes, like just skip it? All right, yes, please. I'm gonna assume that you want me to go over it. All right. So look, this part has a lot of information, but none of it is really important. They're just showing you the graph. There are different types of graphs, for example, bar charts, histograms. The most important, because he spent a lot of time, just box plots, because they're really important, and he really stressed on how you can draw them and how you should understand them. Now, this is just what a bar chart looks like. He brings you this and asks you what it is. Just be able to identify what a box plot is. Now, he's explaining to you what outliers are, and outlier is just basically a point that's really different from the other. You shouldn't really routinely remove them without justification, just like how we talked about earlier. You can just remove it just because, oh, hey, you know, 444, just like we saw earlier, it's really outlandish, so I was going to remove it. No, you need to justify it, and usually you justify it generally in practical, and in practice, how people do it is they just go to the actual contact information that they collected from the data when they usually follow the patients or the participants rather, and then they just see if, you know, they're going to pretty much if they had that age or did not have that age. And if they didn't, they usually correct it. And that's a good way to justify it. But just justifying it because, you know, it's not that important, then no. And I am seeing someone say that, you know, he didn't explain this, but just to be safe, look, there's really nothing here. We're going to talk about all of this in the next slide, or next lecture, I mean. So this is what outliers look like. This is what outliers look like. This is what outliers look like. Right? This is not important. We'll see this in the next slide. This is what an outlier looks like. Notice how this looks like an outlier, but notice here it doesn't look like an outlier. I know the y-axis is different, but notice they're just showing you that when all the points are down here and one point's up here, it's an outlier. But when the points are everywhere and then this point's here, it's like, it's fine. It's not an outlier. So it's important to know. Now for this part, you need to know the median. So we're just going to skip ahead a little. We're going to, you know, talk about the median very slightly, just very slightly, and then we're going to discuss it more in the next lecture. So now what is the median? The median is exactly the middle point. So the easiest way to find the median, in my opinion, is just by ordering the entire numbers and then just doing the cross technique, which is just crossing one value here, crossing one value here, crossing one value here, and then you keep doing that over and over again until you get the middle value, which is in this case 29. All right, so 29 here was the median. Now, why is this important? Is because when you draw a box plot, the box plot has 3 important points. One of them is the median, the 50th percentile. Then you take the median of the other 2 areas that the median bisects, which are the 25th percentile and the 75th percentile. I'll show you what I mean. So we need some points here. Let's take these points. So this is the median. So in other words, if we had a box, if we had like a time frame, or like points on a specific line, and let's say this was 29, then I would draw a point up here, and this would be the 50th percentile. This right here would be the 50th percentile. Then I would find the median in this group and this group, all right? And basically, the median is going to be this one and this one, right? You don't like, I don't have to cross, but it's the same thing, right? It's going to be 22. So I'll find 22 on the line. I'm just going to make it here because this is not a real line. But that's the 25th percentile. And then we have 34. So 34, we're going to find it here. I just made it, but 34 is here. Then you connect all the lines together. All right. And that's the box plot. Now, the box plot has whiskers at the end. They're like these little lines that go out. Now, how you know where they stop is very simple. You take this number that was your 75th percentile, which is this value right here, and you take this value, which was your 25th percentile, which is right here. You minus them from each other. So this is going to be like, I don't know, 12. I actually don't want to just make a mistake. So 34 minus 22. All right, 12. So 12, this is called your interquartile range, which makes sense. It's inter between the 2 quartiles, and it's a range. It's a range of values from here all the way to here. So all the values from here to here are 12. The way you find this point and this point is very simple. You do 1.5 times this value. So this is going to be 18, right? Times that, yeah, 18. So what then you do is you add 18 to this side, and that will get you this whisker, and you minus 18 from this side, and that'll give you this whisker. Now, what are the whiskers for? The whiskers, they highlight 99% of the data. 99, not 95, not 90, not 99. Only if you multiply by 1.5. I'm sorry if this 1.5 just looks decrepit, but okay, 1.5, right? This graph, this is wrong. This is wrong. Do not follow this. Look, the whisker should go all the way out here if you're using 1.5. I'll repeat it all, not just the last part, don't worry. All right, so again, this is your 75th percentile, this is your median, this is the 50th percentile, otherwise known as the 50th percentile. Sure, 50th percentile. And then this is the 25th percentile. And this is your whisker for, you know, finding out the 99th percentile. So this, from this point to this point, this encompasses 99% of the data, right? So we're going to repeat all of it right now. And yeah, there's no whiteboard that I can really use. We're gonna do it again here. So we're going to do it again. It's really simple, really, really, really simple. The first thing you want to do, all right, please repeat the last part. And from after you to the 25th and 75th, I'll repeat the whole thing, no worries. If the sample is even, how do we find the 20th? Oh, yeah, so I'll guide you through it. All right, so just so that we don't repeat it exactly the way it is, I'm going to make this sample even, okay? I'm going to make this sample, let's add another point here. Let's add 63. So now we're doing the same puzzle again. We're doing the same puzzle again. But the difference is that we have an even data set, not an odd data set. It made the numbers very easy. Now the numbers are not as easy, but it's still simple. So let's do, the first step is to find the middle point, the median. Okay, how do you find the median? You just do the crisscross technique that I did, or in the second lecture, we'll learn the formula. It's like n/2, blah, blah, blah. We'll learn it. Just forget about it now. Just learn the crisscross technique for now. So we'll do we'll cross this, 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 we'll cross this. Eventually, we'll be stuck with 2 points, right? And these are our 2 points that we're stuck in, right? So these 2 points, you see these 2 points, we can't really pick one over the other. So what we do is very, very simple. We find the mean between them. So what's the mean? 29 plus 31, which is 60, divided by 2, which is 30. So the mean here is going to be 30. That's not only, you know, not the mean, but the mean of these two values. But that's our median. 30 is our median. Okay, 30 is our median. Now, we can go back to our line plot, and I'll take the questions in just a second, just 1 second. So we know that the median, this number here, is going to correspond to point number 3, right? Now, wasn't this the median? So now we need to take this group by itself and this group by, sorry, with 63 by itself. And we need to find the median in this area and this area. And we'll find the 25th and the 75th percentile respectively. I'm not going to do the crisscross, but like you get the picture. It'll be between these 2 points, which is going to be 22.5. So this will be 22.5. And then we'll draw the point here on 22.5. That's our 25th percentile. And then if we do it here, it's going to be 34 and 47. I'm just going to do it right now. 34 plus 47, and then equal divided by 2. 40.5. All right, so we got 40.5. Yes, you include these. When it's an even data set, you include these. You don't just get rid of them. You include these, right? When it's an odd, you don't include it because it was exactly in the set, or you can't really include it. But when it's even, you do include it. So this is going to be 40.5, and that's going to be our 75th percentile. Then we do the interquartile range, which is going to be 40.5 minus 22.5. It's going to be 18. So our interquartile range going from this value all the way to this value is going to be 18. If you subtract this from this, it's going to be 18. Then you multiply it by 1.5. And then it'll give you the whiskers. And let me just complete the box plot. Sorry. Complete the box plot. And then it'll give you the whiskers. I'm actually too lazy to do the math. And if you add 18.5 to this way, you'll get the point here, which is 40.5 plus 18.5, 68 something. I don't know. So, I don't know. Point is, you subtract it from this side, you get, I don't know, like 5. Point is, that's how you do the box plot, right? And that's the whiskers, the most important part. Now the whiskers, they're set to include most outliers, right? So if you take, for example, the interquartile range, they'll try their best not to include any outliers. Now I'll explain why they use 1.5. The reason they use 1.5 is to make it 99% of the data. If they use any number less, it'll be, for example, less than that. So it'll cover 95% of the data, 90% of the data, so on and so forth. The reason they picked 1.5 is so that when you check all the data that's from here all the way to here, it covers 99% of the data, right? After subtracting 40 from 22.5, 18, what do? You take this 18 and you multiply it by 1.5. You will get an answer. I'll just do it in front of you. 18 times 1.5. 27. You get 27. Then what you do is very simple. You will basically add 27 to this side. You'll get a value. That's your, the end of this whisker. And then you'll subtract 28 from this value, and you'll get a point at this whisker. From the end of this whisker to the end of this whisker, you'll get the 99% of the data. That's why they use 1.5. If you multiply by less than that, you'll get less of the data covered by the whiskers. Now, since they cover 99% of the data, most likely they'll try their best to cover most outliers, but they won't cover much. When you take the interquartile range, only this point to this point, they'll try their best not to include outliers. So it's good, in the sense that it depends on what you really want. If you want to try and include more data, then you use the whiskers. If you want to include less data, you use the interquartile range. So again, this point, the thing's in the way. Okay. This point is your median. This is the 50th percentile. This is your 75th percentile. This is your 25th percentile. And these are your whiskers. Once you're done with your whiskers, you're done with everything. You're done with the box plot. You are done with the box plot. You're absolutely ready for any interpretation of the box plot. But you don't have to interpret the box plot. You just have to know how to draw it. All right. So I hope all of you understood how to draw the box plot. All right. So is everyone all right with this? Look, yeah, I agree with you, but it's mentioned here. If you look, just one thing. I know all of you got it. Just one second. I'll repeat it. I'll repeat it. Just 1 second. One person mentioned something important. Isn't it 98th percentile? Because if you go to this graph, if you take first and 99, it should be 98. Look, this is what I'm telling you. Forget this graph. Forget this graph. It's so misleading. Just forget this graph. Look, this point is really important. In symmetric data sets, the adjacent values should contain about 99% of the measurements. This is what the adjacent values are covered by the whiskers. So this, I'm following this because this is actually what's correct. So I hope this is clear. yeah, outside the whiskers, look, there could be an outlier within the whiskers, but more likely anything outside the whiskers is most likely an outlier. This is how you probably sort of understand the whiskers. If there's a point outside the whiskers, then it's most likely an outlier. That's how you understand outliers. But still, there could be, I don't want to confuse you a lot, but it's not just as clear cut and simple. But the general rule, I agree with you. This is how the general rule is understood, that after, the whiskers, beyond the whiskers, not just after, beyond the whiskers, outside of the whiskers, you generally have the outliers there. So for example, if the sample space, if there is a number 100 that's higher than 99 percentile, how do you annotate this? I'm assuming how do I draw it on the box plot? Is that your question for Noura? So you're asking if interquartile range. So you're asking, what if there's a point outside of the whiskers? How do we know? Yeah. Are you asking if there is a point outside of the whiskers? How do we know? How do we draw it? Yeah. How do you annotate it? This is the thing. You don't draw it, because you see, the box plot, it just helps give you information quickly. It helps tell you what's the 50th percentile, what's the 75th percentile, what's the 25th percentile, and then helps give you the whiskers that say, hey, anything outside of this value is most likely a sort of outlier. All right, we won't have time for the other two lectures. All right, guys, if you didn't get this part, I will repeat it one more time. Don't worry, we have plenty of time. Yeah, we have plenty of time. Actually, I mean, kind of don't, but we will do this. Don't worry. So look, you can do one of two things, and I think having you guys vote is a lot better. Either we move on, and then you guys who would like me to repeat can just see the recording and can just see how I did it with odd or even, and then we can just move on to the next lecture. Yeah, okay, so a lot of people want me to move on. Basically, I'll just do it really, all right. All right, well, a lot of people want me to move on. Whoever didn't get this part, you're more than welcome to just see the recording. I'm sure you'll understand it the more times you see it. So yeah, with that said, let's move on to the next lecture. There's actually nothing left. He gives you some questions so we can actually solve these. I want everyone to at least try. He does give you the answers in the next lecture, but let's just try. So injuries classified as fatal injury, severe, moderate, minor. What is this? Move on, please. Attention span is running out. So what do you guys think? Yeah, so this is ordinal, right? Because there's an order, but the difference between fatal injury to severe is not the same as severe to moderate. So that's going to be ordinal. So gender data is a form of what? Is it nominal, ordinal? Right. All right, so it's nominal. We all agree that male and female, nothing superior. Both categories are the same. So you're not really going to be, ordinal or ranked or continuous. It's basically nominal data. Number of car accidents, we can all agree that you can't have 2.5 or something like that, so it's going to be discrete. All right, so that's the references, and let's move on to the next lecture. Guys, I really have to stress how much I like it. Believe me, if we stay here till 9, I do not have a problem. I know some people wanted to finish at 8, but I think it's more important that we focus on, actually having everyone understand. It's a tough one. It's a tough one to balance out. I assure you that. All right, let me actually save. All right, and share screen. It's not picking it up for some reason. Oh, there we go. Okay. All right, and set up slideshow without animation. All right, and now we're going to talk about numerical summing measures. Basically, to sum this up, there are two main things that I want to know when I think of a curve: where its center is and how variable it is. So we have two main ways to describe that. There are measures of its center, in other words, measures of its central tendency, or measures of variability. So one second, I need to get the chat next to me. All right. All right, so He is giving you some reviews here. So for example, months to relapse, this is time to event, length of hospital, this is continuous because in days. This is numerical summary measures. This is when we talk about mean, median, mode in more detail, as well as variance and standard deviation and all that. Hair color is nominal because none of these are more important than the other. Smoking status, none, light or heavy. This is ordered, heavy, light, none. So basically, this is going to be ordinal. It gives you all the answers here. Yeah, length of hospital. So days is considered continuous. So that's cool. All right. He repeats this to you because he really wants to emphasize it that, sample, statistic, population, parameter. And he talks about how we can infer that the sample average is very close to the population average. It could be close. It can only be assumed as such if the actual sample represents the population, so on and so forth. He gives us this that we've seen like a million times already. We're going to skip it. Descriptive statistics, all the Greek letters that I talked about earlier. We use Greek letters for populations. We use Roman letters for samples, so on and so forth. But they're kind of diverging from this. They don't really want to use this anymore. Here we are. This is the summary of the lecture. I'm not going to make the same mistake of just summarizing everything on the spot. I want you we're going to talk about every single one. So don't worry. So the measures of central tendency, they help check if, they help us. Like for example, if we have this distribution, right? The measures of central tendency help explain to us where this center is. It helps give us an idea where this center is. Think of it like chest leads on an ECG, chest leads on an ECG, you don't just have one lead, you have like 12 different leads with like 6 on the limbs and like 6 on the chest, so on and so forth. The reason we do that is because we need multiple angles because one doesn't tell us enough. The same exact thing can be understood here. We need multiple measures of central tendency and multiple measures of variability to fully understand what this population or what this distribution is trying to tell us. So we have different measures of central tendency, for example, mean, median, and mode. We kind of saw some of them and how we use or how we calculate some of them previously in the previous lecture, but right now we're going to delve into them with some more detail. With measures of data variability, there's one that's not really useful, it's called range, and one that's incredibly useful, it's called standard deviation. There's also one called variance, but basically variance is extremely related to standard deviation, and we'll see more about it as we get to it. For now, let's start with the measures of central tendency. Basically, as we get a distribution, many of the points tend to clump in the center. So they found ways to actually identify the center and sort of see where the center is. So for example, if they see an observation that, for example, at the age of 5, people are, children are more likely to be 43 inches of average, most of the points will land here at for example, 43. Right? Some will be higher than that, some will be lower than that, but the general average, most of them will land somewhere here. So they found that it's pretty important, since it's very common for them to land here in the middle, it's very important to be able to define that middle point. And again, they give you the distribution. Okay, so in any sample, we need to make sure that it's representative. He talks about this over and over again. But the reason for that is because we need to be sure that we can make a generalization. Now, making a generalization is often seen as seen in a negative connotation, usually seen as something bad that we need to do. Here, no, it's not that bad. Here we have to do it because we don't have the time, nor the money, nor the effort to actually interview every single person in the population to determine whether a medication could be good for them or not good for them. Here we have to make generalizations, and there are several ways to make generalizations. And the reason he's talking about them now is because when we have a sample, we're going to calculate the mean of that sample, the median of that sample, the mode of that sample, and we're assuming that they're going to be very close to the population's mean and population's median and mode, respectively, because we are making the generalizability that the sample is very similar to the actual population. All right, so let's start with the first one, mode. Mode is the easiest one. You don't even have to sweat too much about it. It's the most frequently repeated thing. If there's nothing that's being frequently repeated, then basically there's no mode. All right. If there's 2 terms or even more terms that are being repeated equally, then basically they're all going to be the mode. So for example, we'll take some examples. You notice how we have 2.1, 3.4, 4.4, 6.1, and 11.2. None of these values repeat, right? None of these values repeat at all. So for that reason, there's no mode here. Here we have 5 1s and 3 0s. Since the 1s outnumber the 0s, the mode here is 1. We have 2 2s and the rest are all the same. So, rest are all repeated once. So 2 here is going to be the mode. And here we have 2 and 2 and 11 and 11. So for this reason, since 11 and 2 are being repeated at the same, increment, for that reason, it's going to be considered 2 and 11. We're going to have 2 modes. And he gives you all the answers here. So notice 1 mode, 1 mode, which is 2 mode, which is 2 and 11. So that's mode. Don't make it too complicated. Don't make it too twisted. It's very simple. What gets repeated the most amount of times? Median. Median is, like you saw with the box plot, we're trying to find the middle value. We don't care what the value is per se, but we're just trying to find the middle value. So, for example, if I have here 1 million, right? Then the median might just get shifted to these two, right? Which just happens to be 5, the average of these two. But basically, look, we have 1 million in this data set, but the median is still the same. It's going to be 5. Because the median doesn't care if there's a million in the data set. It just cares that, hey, we just care what the value in the middle is. In this case, it's 5, right? So the mode here is 5, and the median is also 5, right? The mode here is 5 because 5 gets repeated 3 times. It gets repeated the most often in this data set, which means that 5 is the mode. And also the median, the middle value, also happens to be 5, just out of coincidence in this specific, example. Now, listen, put a big just red flag, because I really need to explain this. Whenever you start with a median, it is the easiest mistake to make, because it is something so easy to forget. Let's say we start with 7, 3, 2, 1, and 0. How do you find the median here? Or let's change the numbers a bit. Let's say this is 8 and this is 0. Do not say this. Do not do crisscross, sorry, and then criss, and then cross, and then say the median is 2. First off, what you need to do is you need to order these values. So you need to do 0, 2, 3, 7, 8, right? And then you do the crisscross thing, right? And it doesn't matter if you order them like someone said in ascending or descending order. Usually, it's better to do it in ascending order just because it makes these numbers easy. And because if you go in descending order, you're probably going to make a mistake. You might do like 8, 7 or something, and you might flip it, make 7, 8. It's prone to mistakes. Just do ascending order. It's a lot easier. But yeah, so first thing you do is you got to order them. Don't forget to order them, because that's how the majority of my friends made the mistake. They just forgot to order it, and then they lost the point. This is actually incredibly hilarious. Sometimes people get this question in step 1. So step 1, imagine like this is supposed to be the hardest exam ever, yada yada yada, and they tell you calculate the mean or the median, and then people just forget to actually like order it. It's just, I don't know, like that's like a gimme question. It's like, just give it to me. It's a free point, and so on and so forth. And you just got to remember, just order it, and then it's going to be easy. So yeah, don't forget to order. Don't forget to order. Don't forget to order. Don't forget to order. So now, let's say he brings you 100 values. What are you going to do then? Like, are you just going to keep doing crisscross? No, there's a much easier way. There's a much easier way, and we'll get back to this point in a second. Basically, if it's an even number of observations, here's what you do. If you have, for example, let's say 10 values, then you do 10 over 2, which is going to be 5. You go to the fifth value, whatever that value is, you go to it. And you find the value after it, which is going to be what here they put the formula of, for example, n over 2 plus 1, which is going to be like basically the value after that value that you found, after the fifth value. And you find the average between them, right? Because if you do the crisscross technique, let's say we have, for example, 1, 2, 3, 4, 5, and then 6, 7, 8, 9, 10. This is really important. If you do the crisscross, and it's an even number, or it's an even number of things in the data set, you're going to notice that at some point, I crossed this, but at some point, you're going to be stuck with 2 numbers. So you take the mean. Same thing here. You're going to be stuck with the 5th and the 6th value. The only difference is that if he brings you 100, pieces of data inside the data set, don't just do crisscross and just waste all your time. No, just put 100 over 2, and it says 50th. So just go to the 50th piece of the 50th place in the organized data set, and then find the place after that, and then find the mean between those two. And that's going to be your median. You don't have to do the crisscross technique that I showed you. I just do it really quickly because I can't be asked to calculate. But that's the whole idea of median. Can you kindly repeat the concept? Okay, so we're going to repeat median as a whole. We're going to take an example. All right, so let's take this example. So notice, I know they have that. Just forget the answer. Forget the answer. Notice we have here a number of an even ranked sample, yada yada yada. So they ranked it for us, they ordered it for us. It's perfect and everything. Okay. Now I'm going to do the median my way, and then the way in the slides. So let's find if they get the same answer or not. So my way is just crisscross. So you just keep doing it until you end up with either 1 or 2. Right now we're done with 2, so we have 21 and 22. Find the average between them, which is going to be 21.5. If you find the average, so just add them, divide them by 2. You're going to get 21.5. That's our median. Now the way in the slides, it's better because if he brings you 100 pieces of data, you can still find it very easily without having to waste time doing the crisscross. So his way is this: n over 2. So we have 6 pieces of the data, so it's going to be third. So find the third piece of data in the data set, which is this one. And then find the one after that, which they put it as a formula as n over 2 plus 1, which is 3 plus 1, which is 4th. I just memorized it as third, and then the one after that, which is 22. So we have 21 and 22. Divide them, add them and divide them by 2. You're going to get the median. And in this case, if I erase all the ink, hey, there you go, 21.5, right? So that's how you find the median, either crisscross or you do his way where you do n over 2. You find that it's they want the third value, so this is 1, 2, and then third value, this one, and then find the one after that as well because it's an even data set. If it's an odd data set, now that just kind of makes things even easier. Crisscross until you get one number left. So let's do this one. So you just keep crossing until you get one number left. In this case, the median is 22, right? Now, if you're going to do his way, his formula is slightly different. It's n plus 1 all over 2. So for example, here we have how many pieces? We have 1, 2, 3, 4, 5, 6, 7. So 7 plus 1, 8. 8 over 2 is going to be 4. So they want the 4th spot. 1, 2, 3, 4. So the median is 22. So you just have to memorize these formulas, memorize this formula for even, and then either memorize this formula or just remember that it's the one after. And then for an odd number, just remember this formula. Or you can just use crisscross if the data set is just very small and you can just do it very quickly. But never forget to organize the data. Always organize the data. You see median, the first thing that should come to your mind, organize the data. All right? Now, he goes over this point. Remember how I told you here, if I have a million here, if I have a million, it doesn't care, the median is still the same. He put the same point. Notice how here the median is 22. If this point was not 38, it was 388. Notice how it's still going to be 22. The median is still 22 because it doesn't care what this value is. You immediately cross it. You just care that, hey, this value is in the middle. That's all we care about. Hey, 22 is in the middle. All right, now let's see if there's some questions because we're done with median. There's a morning fly. All right, can we use n over 2, and if we get a decimal, we just round? No, you're going to round up. I mean, yeah, you could round up, but you're gonna confuse yourself because during the exam you might just forget, well, do I round up or do I round down? Like let's say you get let's say you do n over 2, and then you see, oh, it's going to be, I have 7 pieces, 7 over 2. That's going to be 7.5, 3.5. So you might be in the exam, you might say, oh, I'm gonna round it down, round it up. You should round it up, but like don't confuse yourself. If you want to follow that way, you can definitely follow that way. You don't have to follow the formula. It's not like a formula written in stone. You can just make your own formula. The formula basically says that, find the middle value. How do you find the middle value? If it's an even number, just do n over 2. That's the value that you want, and then just go the one ahead of it, and then find the average. Here, just do n plus 1 over 2. Or if you want to just make it a bit more complicated, you can just, do n over 2 and then just round it up. However way you want to do it. So yeah, can you just repeat the even number slides way? Sure thing. So in the slides, here's what they say, right? Here's what they say. They say n over 2, and then, the other value, which is n over 2 plus 1. So I don't really write this. What I just say is just find n over 2 and then the value after it. So in this case, what's the how many pieces of data do we have? We have 6. 1, 2, 3, 4, 5, 6, right? So 6 over 2. Meaning that they want the third value, right? Where's the third value? They want the third value and the value after it. So where's the third value? 1, 2, 3, 4. So they want this value and this value. So 21 plus 22 over 2, you'll get 21.5, which is the exact answer here. That's the even way. You're more than welcome. All right, so everyone's good with median. N plus 1 over 2. So n in this case is 22. No, n is the number. N in this case is how many pieces of data you have. So N here is 7. N here is, for example, 1, 2, 3, 4, 5, 6, 7. All right, N here is 6, sorry. Yeah, number of observations. 1, 2, 3, 4, 5, 6. N here is 6, N here is 7. It's the number of observations, right? N is the number of observations. So I hope that's clear. All right, perfect. All right, so we're done with mode, we're done with median. Remember, median can be used to do the box plots. So if he asks you to draw the box plot, or, I mean, it's an online exam, so I don't think he's gonna ask you to draw the box plot, but just in case, you know, now you know how to draw the box plot. So that's for mode, that's for median. Now we get to mean. Now mean is even simpler. Mean, you just add all the values, divide them by how many observations you have. So for example, you just add this to 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 this, and then divide them by 1, 2, 3, 4, 5, 6, 7, 8. That's why they did adding all of these and then divide them by 8. Now notice with median, all we did was pretty much just crisscross, right? Where we just did crisscross, crisscross. So we didn't care what these values were. We didn't care at all what these values were. But when it comes to the mean, no, this value is contributing, and this value is contributing to the actual mean. So if you get, for example, an outlier, notice how if it's 388, look at how the outlier is being severe, how the outlier is changing the mean severely. It used to be 23.25 when it was just 38. But once it's 388, now it's 67. It changed all of that just because of one typo. So the mean is heavily affected by outliers. This is why, if we go back, you saw this that I just skipped. This is why if you have a lot of outliers over here, pulling the curve this way, we call this positively skewed because you're pulling it towards the positive side. The mean gets pulled the most. The median gets pulled slightly. And the reason the median gets pulled slightly, I'll explain this to you. Notice how here, I'll just quickly explain it. If you add values, does he mention it? Yeah, here we go. So notice, if here we only stopped at 24, the outlier here was added onto the actual data set. When outliers are added onto it, they are changing the position very slightly. Notice how here the median was going to be between these two numbers, 21 and 22, which is 21.5. But with the outlier, the median is actually changed very slightly, very, very, very slightly, which is 22. This is only if you actually add outliers, not if there was already 38 here, but then it just became a typo, the median wouldn't change because a number changed. A number wasn't added to create a new position, right? So keep that in mind. Keep that in mind that the median can change only if you really add values. So again, mean gets pulled the most, median gets pulled, you know, a bit less, but mode stays true to one value because no matter how many outliers you add, you'll only have one number that's being frequently added, unless if like let's say 1 was being repeated 3 times. If you have 1,000 or being repeated 4 times, okay, then yeah, the outlier would be it, but it's very unlikely for that to happen. So the point is that the mode gets affected the least by outliers. Mean will always get affected, and will be the most that gets affected, but the median will be the one that's sort of like in the middle, doesn't get really affected that much, but it does get affected more than mode. So I hope that is clear. Now, since mode is not really that useful, generally when you have outliers, what they prefer to use is median. You just got to memorize that. You don't really need to memorize it, you can kind of understand it. So mode doesn't really have much use, but median can help you understand the middle value. It's of more use, and since median gets affected less by outliers, then it's pretty easy to remember that median is probably the most useful in the case of outliers. So yeah, we stopped here where we talked about the mean, and now you understand why outliers affect the mean the most. Now you understand why median doesn't get affected that much, unless if the outliers were added on, in which case they would change the position. What are the x and y in this sample? What do you mean x and y? So while you type, I will. I'm not understanding. You mean these, like these? In these graphs. You mean this one? Yeah, so in these graphs. I'm really sorry, everyone. All right, in these graphs, like the y, there's no y, but like the idea is that, hey, 30 is being repeated 3 times, so technically the y is 3, so it's the most common, so that's the mode. And then, like there's no real no, the skewed graphs. Oh, okay. Yeah, so there's no real x and y. Like we can make our own x and y. So for example, this could be like height, or not height, like I can't really explain. Like let's say this is height, and this is the number of people. So for example, we have a lot of people who are, for example, at the value of a height of 180 centimeters, for example. All right, and they're all in the center here. But then here you have less people, 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 less people, less people, right? So in general, the mode is the highest, right? And you don't really have to worry what the x and y value is. The idea, the concept is that when you pull the values this way by putting a lot of outliers here, you pull the mean the most, right? And by doing the opposite, by putting outliers here on the negative side, you're negatively skewing it, sorry. You're negatively skewing it. So basically, you're pulling the mean the opposite way, the median, so on and so forth, in the mode least. In B, a lot of people are short. Why is mean high? Shouldn't be closer to the peak. Oh, I get you. No. Okay. You know what? This graph is terrible. Look, I'm really sorry. The mode isn't changing to here. All right. Look, I'll draw you an actual graph of what they're trying to say. All right. This is our irregular. This is our A. All right. And this is mode. I'm going to draw it down all the way here. All right, and then this is positively skewed. It looks terrible as positively skewed, but the mode is still the same. And in here, this will be negatively skewed. So it'll be like this, and then negatively skewed, right? So the mode, I get what you're saying. I get what you're saying. That why is the mode going to the left here, and why is the mode going to the right here? No. They're all the same point. They're all always at the same point because the mode doesn't change. Don't relate the figures to each other. The figures are not related at all. All right. So I hope that's what you're asking about. So not mean mode. Yeah, the mode isn't changing. It looks like it's changing from here to the left and here to the right. Let me erase all the ink. The mode doesn't change. Here they're just exaggerating the look of the distribution to make it look, all right, I'm talking about mean. All right, yeah. So okay, so when you add a lot of outliers this way, the mean, it cares about outliers. It likes outliers. It'll be like, oh, look, there's 1,000 here. Now I'm going to be 1,000. So it just pulls the graph this way. The mean likes to be here and follow the outliers. The mean is affected by outliers, exactly. And the opposite happens if you add outliers this way, right? The mean is going to be like, oh, boy, look, there's like a 0.1 here. I love that. I'm going to also be that. And then negatively skewed. So that's the idea. Yeah, the mean is closer to the outliers. The mean moves to the outliers, right? If you have outliers here in the positive direction, it's going to positively skew the distribution. The mean will go closer to it, as opposed to them all being in the same direction if they're in a normal distribution, in the same point. So does that make sense? I hope that makes sense. If not, yeah, if not, you can always we can leave it till the last part. So mean is positive. No, the distribution is positively skewed. The mean just moves more towards it. It's not the mean is like this wording wise. No, the distribution is positively skewed. The distribution gets negatively skewed. The mean goes towards that direction. It's not that the mean gets positively skewed. It's the distribution. That's just wording and grammar and stuff. So yeah, I hope that it's clear. Yeah, the difference is that where the outliers are. So if the outliers are on the positive side, the distribution gets positively skewed. It's sort of like you're pulling this tail. You're pulling this tail all the way to this side. But with a negatively skewed distribution, all the outliers are on the negative side, on the left side of the distribution, and they get pulled all the way. It's like you're pulling this tail of the distribution all the way to the left side. So I hope that makes sense. So right now we know mean, we know median, we know mode, we know all the measures of central tendency, right? At least the ones that a second year medical student should know. And we now understand why the mean is affected by outliers, why the median is not as affected by outliers, and it kind of makes sense. They go back to this CAM study to show you how they do the mean. So for example, if they check the mean of this, they'll get a certain value, they'll get 37.1. Just more examples of how you can practice mean. We're not going to really wasting any time on that. And here, remember when we talked about how we can find mean when it's binary and it's 0 and 1? This is exactly what they mean. It has to be, for example, dichotomous. Dichotomous means like 0 and 1. It's two different categories, but it has to be 0 and 1. So dichotomous binary data means that you have two different categories and you assign one 1 and 0 in order to find the mean. Remember that the mean we don't like it for the nominal data. And there's one exception when we have dichotomous binary data, which is 0 and 1. So yeah, this is an example. Male is 1. So basically there's 2 out of 10 who are male because I add the 1 plus all the zeros and divided by the number of observations, which is 10. This equals 20%, or rather 2 over 10, whichever one you like to report. So 2 over 10 is 20%, all the same. That means that 20% of the study is male. And yeah, so that's basically what he wanted to explain using this slide. That you can use mean for nominal data in one exception, which is the 0, 1 binary nominal data. All right, now selecting the appropriate measures. Now, like I mentioned earlier, the median is usually preferred when there are outliers. I'm sure that he'll bring this as a question. He'll say, choose which of the following statement is correct or something like that. And then he'll tell you, for example, the median is preferred to the mean, or the mean is preferred to the median. When there are outliers, the mean is better than the median. And then just, cross out the answers that are wrong and try and look for the answer that is most truthful, that is the best answer. Try and look for something that says the median is preferred when there are outliers. The median is the best, for example, central tendency measure when there are outliers, so on and so forth. Or even he could make it even twisted. He could say, he could bring you, this is possibly the worst way to, or not the worst way, like it's the most complicated way to put it. He could give you a skewed distribution, right? A skewed distribution, and it's going in this direction. And then he can tell you what's the best measure of central tendency. And in this case, it will be median, right? Because median is probably the most useful. It will probably be somewhere like here. The median is the most useful, but at the same time, median is, it doesn't get affected by outliers. So that median would be the best answer in that sort of scenario. So, that's probably the hardest way he could make the question. But, it's not that hard when you think about it. It's just positively skewed. So there are outliers. So what's the best measure of central tendency when there are outliers? Median. So I hope that makes sense. But overall, if there is no outliers at all, if it's a perfect normal distribution, which is like never going to happen ever in your entire life, but if that were to happen, then the best measure of central tendency is the actual mean. So careful if there are outliers or not outliers. Why wouldn't it be the mode? Because look, the mode is not that useful when it comes to a distribution. It's not that useful at all. It just tells us what's the most frequent. That doesn't really tell us the center. The center is not technically the most useful. I personally would prefer having the median, and that's what, yeah, I'll use that. So, all right, perfect. Yeah, so median for ordinal, mean for continuous, mode for nominal. Yeah, I mean, that's pretty good. Median for ordinal, mean for continuous, mode for nominal. And for just a regular distribution, if you have a regular normal distribution, the mean's the best. The mean's absolutely the best. If you have a positively skewed or a negatively skewed, the best one to have is the best one to have is probably going to be, not probably, definitely going to be the median, right? Because the mode, although it tells you the most common one, and although it's going to be technically the least affected by outliers, it doesn't give us that much information. Median gives us the best information. It tells us the exact center of specific distribution, which is to every biostatistician, this is their dream. They want to know the exact center of a distribution. And mean would be less useful in this case because it's going to be affected by outliers. So I hope that that makes sense, and I hope that you guys pick the right answer in that case. So yeah, mean or median. Notice how here the outlier heavily affected the median. Here in this case, the mean actually got like absolutely destroyed, or it got like increased technically. But basically, the mean got shifted heavily into a or severely shifted into a completely different number. But the median, however, would still stay 22, right? The median here in this case, if you crisscross, it doesn't matter how you do it, there are the same number of values either way. So you're going to end up with this value in the center, and it's already organized, so this is your median. So I hope you understand why the median doesn't get affected by outliers. This is just another point. This is again just hammering home, talking about it. All right, the numerical value of the mode is close to that of the mean and median in a symmetric normal distribution. They tend to have different values in a highly, this is the exact same thing that we mentioned. Mode is always going to be the most frequent one, but again, we don't care about the most frequent one. They're called measures of central tendency. We want to know the center. So the median tells us where the exact center is, despite where, if it's skewed or not skewed, But if it's not skewed, the mean is probably much, much, much better. Not probably, is definitely much, much better. So yeah. And again, don't forget, this is called positively skewed. This is positively skewed towards the positive side. This is negatively, sorry. This is negatively skewed going to the negative side, right? All right. Now we go to measures of dispersion, which, so we finished all the measures of central tendency for this lecture, the mean, median, and mode. Right now we're going to go over variability, and the measures of dispersion are important because let's say that both graphs, let's say this graph and this graph, they both have the same, for example, center, but this one is more wide, like it's wider and more variable than this one. So for that reason, you need another sort of principle to follow when you consider the characteristics of a curve, which are first its center. We talked about all that a lot, but now we need to know how variable points are. In other words, how are the points going away from the mean? Are they going very gradually, and very gradually, or are they being drastically, decreased? So that is given the term as variability, and there are numerous different ways. First off, they checked something called range. Now, what is range? It's very simple. We're just going to skip this. This is an example that he shows you of how this, for example, is narrow, but this is wider, despite having the same mean. This is wider, despite having the same mean, right? So they tried different ways to sort of discuss what variability should entail. They started with range. Now, range is absolutely useless. What range does is it basically takes the lowest point and the highest point, and then it basically subtracts them, and says that's the range. Now, that doesn't tell us much. That only tells us the first value and the last value, and how many, technically values are in between in terms of the magnitude between those values. So, for example, if we have 1 here and then 40, right? 40, and then there's 1 here. The range is 39. Now, does 39 tell us what's happening in the middle here? It tells us nothing, absolutely nothing. It doesn't tell us if there are a million ones, or if they're going from 1 to 40 in a very, very gradual manner. For example, 1, 2, 3, 4, 5, 6, so on and so forth. We have no idea what's happening in the middle. Moreover, if there is an outlier, well, your range is going to be shot, because if there's an outlier like 1,000, then your range is going to be like 999. So, this is absolutely useless. A range is absolutely useless because outliers affect it, and we don't get to know what happens in the middle of the actual data set. So here are examples. The range here, for example, is 21. Since you just minus these values, you get 21. And if we have an extreme value, notice how the range is just completely shot. It's absolutely destroyed, right? The range is now 221, and it doesn't really signify exactly what the distribution should look like. Now, another example is that if you take 45 and 0, and if you have all these numbers in between, it doesn't really, you don't really know what's happening in the middle because you're just focusing on this number and this number. Same thing how I explained earlier, but notice how these two are completely different. Notice how here it's 0, then 1, 1, 1, 1, 1, 1. Here it's 0, then 5, 10, so on and so forth. And the range is the exact same. So this range idea tells us nothing. You get it? So carry the cat, please, and Mrs. You. Oh, no, I'll do it at the end. I'll do it at the end. Okay, just ignore that. Guys, focus. Focus. Okay. And now we talked about range, right? And how it's affected by outliers, right? Now, I lost my train of thought. All right, when you talk about range, you're seeing the first value, right? You're seeing the first value and the last value. So now they decided, okay, so how about we just take a value in the middle here and the value in the middle here? That way, just in case an outlier did appear, we wouldn't catch it. We'd catch this value and this value only. So then they made the interquartile range, which is the exact same, range that we talked about. This is range, interquartile range, which is basically the 75th percentile minus the 25th percentile. How do you find these? We talked about it in our box plot. You find the median of all the values. So for example, you find the, let's say we have 1, 2, 3, 4, 5, 6. We're going to take a break right now. Just let me finish this last point. 9 and 10. You find the median. It's going to be between these 2 points. It's 5.5. And then you take the median of this side. So 5, and then boom, this, and this. And you're going to have 3. And then you're going to have this part, all of this part. You're going to have like 8 or something. Point is, you guys remember this, right? And then 8 minus 3 is going to be your interquartile range, which is 5. Now, if you had an outlier here in this case, it's not going to affect anything because you're taking this value and this value. You're not taking the lowest and the highest value. Get it? So yeah, we took it in the box plot, just revising it before I should play it. So yeah, Now look, I'm gonna be honest. We are not gonna finish on time. All right, so take a break. It's fine. And then we might finish around 8:30, 8:45, something like that. So make your, you know, if you wanted to eat or anything, just take a break. It's fine. So do you guys want to be back by 7:15? 7:15. Is everyone okay with that? Just to agree with it? All right, so 7:15, go pray, go do everything. And if you want to eat 7:20. All right, 7:20. But look, guys, don't like kill me if we stay a bit longer than usual, right? If we, I think by 9 we'll be finished, but you know, it's fine. It's fine. All right, so 7:20. Quick question, the doctor. I have no idea. Ask you guys. All right, yeah, you are fine. Yeah, Mr. Mabab, I like that. All right. So I'm gonna go pray and maybe like get a snack or something, and I'll be right back. 7:15. All right, I'll be back by 7:15. All right, 7:15. So here's how, on an even number. Is this even? 4 and 4. Yeah. So this is even. So let's do it. Now the median is going to be, if you crisscross, it's going to be between 22 and 23, right? Yes, so the median here is going to be 22.5, right? If you take it between these two values, if you take the mean of these two values. Now, if you have that value, that is considered your 50th percentile, right? That's considered your 50th percentile. So on the number line, or not percentile. So if you take your number line, and this value was, for example, 22.5. Let's put 22.5 here. You'll actually have a number line with like 1, 2, 3, but I'm just, you know, making it quickly by doing the 22.5. This will be your 50th percentile, which is at 22.5. Then you take the median of this group, including the 22, and you take the median of this group, including 23. The median will be here between 23 and 23, which is going to be basically 23. All right, so 23. So the median of the 70, so the 70th percentile is going to be basically 23. So if we have 23 here, it's going to be right there. And if here, that's going to be 20. So if we have 20 here, it's going to be here, right? So this is our 50th percentile at 22.5, this value here. This is our 75th percentile, which is this value right here, 23, sorry. And here it's going to be 20, which is this value right here. This is 75th percentile, which is this one. This is 50th percentile, which is this one. This is 25th percentile, which is this one. Then you do the whiskers. The whiskers are easy. You just do the interquartile range. So it's 23 minus 20. Actually being really annoying. Just one sec. All right, sorry, little family thing. Okay, so yeah, what I was saying is if you take the interquartile range, which is 23, the 75th percentile minus 25th percentile, you're gonna have 3. You multiply this by 1.5, and basically you're gonna get, what is it, 3 times 1.5. I need a calculator for this. 4.5, is it 4.5? 3 times 4.5. No, bring it back, please. You guys are caring too much about the cats. You need to focus on the actual like exam. All right, so yeah, it's gonna be 4. Is it gonna be 4? 3 times 1.5. Yeah, it's 4.5. So then you do this area plus 4.5, which is gonna be like 27.5. That's the end of this whisker at 27.5, and then this 20 minus 4.5, which is gonna be basically 15.5. Right, 15.5. So that's going to be the end of this whisker. From this whisker to this whisker, you cover 99% of the data. This share screen thing is out of the way. Okay, that's going to cover 99%. So will 38 be an outlier? Yes, that's an astute. That's quite the. Where did you get 1.5 from? Is it rule? Yeah, 1.5 is a constant. Yeah. So see, this is why I told you that. Yeah, the whiskers do cover 99% of the data. So technically, anything outside of it should be an outlier. But like, I mean, like this is not, to me, this doesn't seem like an outlier, even though on paper with a box plot, it is an outlier. So, do with that what you want to understand. I feel like this topic is confusing because the box plot says it's an outlier, but it's not really that much. When you look at it, it kind of does look like an outlier. Like, look, you have 17. All these points are really close to 20, and then you have a point that's just 38. So, yeah, box plots. And if we were asked in the exam, we say 38 is an outlier. Oh no, I don't think that you'll be asked in the exam. But according to the box plot, yeah, it's an outlier, right? But it's not really an outlier. Yeah, it's not really an outlier when you compare it to 388. He'll give you an extremely obvious example. He won't like try and trick you or something, right? So it could still be considered part of the data. I mean, yeah. I did not even consider this being an outlier, just because I don't follow the box plot thing. I just don't consider it as an outlier. But yeah, but it's still out of the 27.5. Again, you guys, I will kill someone. My main point is that it's not 100% rule. It's something that just isn't a rule that you can rely on 100% of the time. You get it? So, yeah. Again, he'll make the numbers easy for you, and he won't give you. I don't think he'll even waste time giving you a question that's like, "Is this an outlier or not?" He won't bother with something like that because he only has like 40 questions that he can give you. So it has to be something that's actually a concept that's worth remembering. So he's going to give you a concept that is worth. He's not going to give you a point and tell you, "Oh, is that an outlier?" He could, but it's not a Dr. Hassan question. Dr. Hassan's questions are extremely direct. They check, do you know the concept? Do you understand the concept? I'm not trying to trick you. I just want to see if you understand the concept. And usually, really, the only person that is your enemy in the exam is yourself, honestly, because you will complicate the question. It'll be an extremely easy question, but you will be the one to complicate it. You'll be the one to actually mess up the question. Now, I don't know if it's, right now it's 7:15, so we're going to continue. So if we have one median, do we count it? What do you mean one median? I don't understand what one median means exactly. Just 1 second, let me get my glasses. All right. Wait a minute. I just want to wait. I just want a minute from you guys, just so I can show you something. All right. All right. Just 1 second, because I recognized your name right now, and I can tell already that I know about Keith. Oh, there was a Farah Barakat. Just 1 sec. Oh my God. Twitter. All right. And who was it? Yeah, I think it was Ijaz. Ijaz. Ijaz Khan, Ijaz. Right. No, I'm doing this. I'm sorry. I'm doing this. 1 sec. Because it was you, wasn't it? Look, this is incredible. This is incredible advertising right here. All right. No. This is the right Ijaz. Don't tell me wrong Ijaz. Yeah, Farah, I am doing this. I'm going to do this. Wait a second. Where is it? Whoever's editing the video for the recording, just edit this part out. Where was it? We were talking about range and interquartile range lastly. I think everyone is no, I'm not blaming you. I'm just poking fun. Point is, let's go back to the actual go here. What is this, like this Love Island or something? You get to vote people out? What? Okay. So yeah, we stopped here, right? We stopped at interquartile range. Okay. And we talked about it. This is the same thing about the box plot. We finished it. I'm not really going to repeat it. You can go see the recording if you'd like to repeat it. It doesn't really ruin anything you might know in the or any new concepts that you're going to know. Now, since interquartile range and range just don't help us, they're pretty much useless. They don't tell us what's happening in the middle of the distribution, just what's happening from one end to another, and that's it. We just know the one end and another, and pretty much no understanding of what's happening in between. They're not really that useful. So instead, we have There's a long list of how to calculate interquartile ranges. Just ignore it. This is all we talked about. All of this, okay? Instead of just trying to figure out the 25th percentile, 27th percentile, he's like, how can you know what is the 50th percentile? How can you know what the 70th percentile? It's all the exact same thing that we talked about, all right? And his formula, his formula is it's all the exact same things. I don't know if you guys want us to do this or not. It's the interquartile range all over again and 75th and 25th. Do you guys want us to do this, or we did this? Yeah, no need. We did this a lot of times, right? And it's always the same thing. So we're not gonna do it. You can do it by yourself and then see the actual answers. This is an example of the box plot again, all the same. So now we get to the big boy, variance. This is the last important concept in this lecture. Variance is incredibly important, right? It's so important that the way I like to teach variance, and I've been teaching this for the past 4 years this way. I like to give a story. Basically, forget anything on the slide right now. Forget everything. We're gonna do it, live, okay? Let's say we go to this example that he has. He already answered it, but whatever, it's fine. Let's do this example. Now, the way variance works out, people were really struggling. They only had range, and they thought, well, range doesn't really help us that much. We want to know what's happening at every single point. We want to know how the distribution is looking like. We want to know, does it look like this, or does it, for example, look like this, or so on and so forth. So we want to know. We want to get some good detail. So one person thought of a very smart idea. He said, if this is, for example, the mean, and we know that this is the mean. Let's say we have a point here, and 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 a point here. Right now, obviously, there are more points than just that, but just for the simplicity, let's just say it's 1 point here, and 1 point here, and 1 point here. Let's say it's comprised of just these 7 points, which are, for example, the mean, then 1, 2, and 3, then 1, 2, and 3, all right? Now, he thought, how about we find the mean? So we found it, it's right here in the center. And how about we minus this value from the mean, and then this value from the mean, and then this value from the mean. And then we do the same thing this side, this value from the mean. Let me just lower it. And then this value from the mean, and this value from the mean. If we do like this for every single point, we're going to get a pretty clear idea of how far every single point is away from the mean. That if they're all very close to the mean, that means it looks something like this. And if it looks, if they're very far away from the mean, we're getting large numbers, then it looks something like this. And this was an incredible idea. The problem is that if you take these values, and let's say they all became -5, and you take all of these values, they're going to be 5. And these two are going to cancel each other out. And they're going to be eventually 0. If you take all the values, it doesn't matter. It doesn't matter what planet you're on. If you have a distribution, all right? If you have a distribution, and then you take all the points on this side of the mean, and you add them all together, and you take all the points this side of the mean, and you add them all together, and then you basically add this portion of the points to this portion of the points, they always have to pretty much cancel each other out. Because these points in relation to the mean will all be negative, and these points in relation to the mean will all be positive. When you cancel them, when you add them together, they're going to cancel each other out because the negative cancels the positive. So now they thought they got the actual solution. They thought they really understood everything about it. They thought, hey, we're going to put positive and negative on this side and find all the different points and everything. But then all their hopes and dreams were ruined when they found out that when you add everything, no matter what, this formula will always be 0, because when you add every single thing in the mean, and then take every point and minus it from the mean, take every point, minus it from the mean, and then do the same thing on the opposite side. When you come to add all the points together that you got from the right side and the left side, it'll always be 0. So now they were stuck. They were like, gosh darn it, we have positive values on this side, we have negative values on this side. What can we do? Well, in math, there's this rule. There's this rule that whenever you have a negative value that you don't want to work with it, you have 2 options. Either you use absolute value, or you use square. Now, absolute value, it's an absolute pain in the ass, so just forget it. Absolute value is terrible. And you might think, oh, absolute value is simple. We did it in high school. It's just like if you have -2, you just put 2 lines and then, hey, it's 2. Nope. This is baby absolute value. Absolute value, for anyone who's done calculus, he'll know or she'll know that it's not just this simple. You got complex numbers, you get terrible, terrible numbers. So the entire idea is that since we only have 2 ways of getting rid of this negative, and absolute value is a terrible way, the other way is to just be squared. So when you square a value, you'll get rid of the positive, right? You'll get rid of the negative, and it'll become positive. So that's what they did. They said, hey, how about this? How about we do this? How about we get a distribution? We find its mean, all right, from the specific data that we have. And then we find all the values here in relation to the mean, and this will form some sort of positive number. And then we'll get, for example, all the values here in relation to the mean, and this will form some sort of negative number because the mean's more than those values. And then they said, let's square this value, and let's square this value, and let's add everything together. When you do that, you create an actual number that's never going to be 0, because a positive value plus a positive value will be a positive value, right? So you'll get a value that actually signifies how good the variance is. And here's the general rule. As you get a higher variance, the distribution starts to look something like this, right? Something like this, where it's really wide. When you get a distribution like this indicates that the variance is lower. So remember, whenever the variance is high, then basically the distribution is going to be, very wide. But if the variance is low, if it's a low number, then the distribution is going to be very narrow. So that's the entire story of how they finally came up with variance. Now, they said, let's go one step further, and we don't want the square, because now who on earth measures people in 6-inch squares? We measure people in inches, not inch squares. So they said, let's square root it. So they said that when we square root the variance, we create something called standard deviation, SD. And that is the story of how they finally got standard deviation. Now, obviously, it's just an anecdotal story. I don't know if that's exactly how it happened, but this is the way I like to teach it, because that's the logic that these slides are following. He's showing you how if you try to do the means and everything, you get 0. But then they decided to square it, and when they square it, they actually get the values. And when they square it, they actually get the values. All right, and that's how we find the variance. Now we're going to do one example, and I urge you all to concentrate with me, because we're only going to do it once. It's quite long, a bit. It's not that long, but it's a bit long. But before we do that, notice how he actually surprised you a bit. See how this formula, the only thing that changed is not just the square. He also did something else. He also did -1. Now, look, I'm going to be honest. You do not need to know why there's n-1, all right? But please, when you're calculating variance, don't forget to put it. Now, for that reason, I'm just going to give you a reason, or it's actually 2 reasons, why n-1 exists, all right? Now, you don't need to know these reasons, so you don't need to ask me to please repeat them or something. These are just for you to know. And when you know these reasons, you're less likely to forget that you use n-1. So what's the deal behind n-1? Right? Remember that this x bar, it signifies mean, right? So this means that we want to minus every value from the mean, and then we're going to square it, and then we're going to divide the entire thing by n-1. Now, we're using the mean in this formula, which means the mean has to stay the same. The mean always needs to stay the same if we're using it in the formula, right? We can't just have a mean that's like 70, and then halfway through the formula, it just changes to like 60. It has to be 70. So here's the first reason why we have n-1. Now let's say we have, for example, 50, 60, there's not enough space here, I'm going to put 70, 80, and 90. Now if we add all these numbers and we divide them by 5, we're going to get a mean, an x bar, equals 70. Now look, I know a lot of you maybe have not heard of the word degrees of freedom, but I want to make it very simple for you. All right, and this is, again, you don't really need to know for the midterm, but you need to just, I feel like by telling you this reason, you will never forget to put n-1, because some people just put over n and they just get the wrong answer. So if you have, for example, the mean of 70, and then you start using the 70 in this formula, that means that these values should not be able to change, right? These values, when you think about it, these values shouldn't be able to change. But the truth is, these values can change. Let's say we change this value, and we change this value, and we change this value, and we change this value. This last value, you don't have control over it. Because you change these, you don't have control over this last value. It will change by itself to accommodate for all the changes you made here in order to keep the mean 70. Therefore, you don't divide just by the number of observations, because not all of them are free to control. There's 1 degree of freedom lost. So for that reason, you don't just divide by 5. You divide by 5 minus 1. Because you can change these values. Now, we're not going to change them. This is a hypothetical sort of scenario where you can change them, but only 4 of them, because the last one can't change, because we agreed that the mean has to stay 70. If the mean is not 70, okay, yeah, you can change, put whatever numbers you want. We'll find the mean, but once we pick a mean, once we calculated the mean, then you can only change n minus 1 observations. You can't change all of them because the last one has to accommodate and change itself to find all, to basically change the whole value back into the 70 mean that we agreed on, right? So if this became 10, 10, 10, and 10, this last value, I can't change it. It'll change itself to something like 1000 or something just so that this stays 70. That's why you use n minus 1, not just n. So please, I urge you, for the love of God, during the exam, when you're calculating variance, and we're gonna do an example now where we calculate variance, don't forget n minus 1. Don't forget n minus 1. The other reason is because biostatisticians generally prefer a more conservative approach. Conservative means that we generally like to keep graphs wider, just in case to basically make the margin of error less. Now, generally, we like to have graphs. This is gonna contradict everything that I'm gonna say, but generally, we like graphs to become as narrow as possible because they're gonna be very precise. However, sometimes we do want them just a little bit narrower because when they're very precise, then it's very easy to miss things, right? When you have a big estimation, then yeah, you're more than likely to grab it. So what's that supposed to mean exactly? Let's say, for example, we have a variance of 70. If we divide it by, or let's say, for example, at the end of the formula, it became 70 divided by n. If we did 70 divided by n minus 1, then this overall value would be higher. That means that the overall graph, it will be wider. So it'll give us less margin for error. So that's just another reason why we do n minus 1. But again, you don't need to know any of this. The only thing that you need to know is just that do n minus 1, dude. Just do n minus 1. Don't do divide by n when you're doing the variance. When you're doing the mean, do over n. It's fine. Do over n and it's all right. When you're doing the actual variance, no, you got to do n minus 1 because you lost 1 degree of freedom since you already put the mean in the formula. Therefore, the mean can't change. Therefore, the number of observations, all of them can change except for 1. It'll change itself. I hope that's clear. Again, just remember n minus 1. So let's do this example. Let me erase all the ink. And although the answer is on the slide, we'll just remove everything and whatever, we'll just keep everything. So basically, we have 72, 73, 76, 76, 78. We find the mean. So we add all of these together. We add all of these together, and then you divide them by 5. If you do that, I'll just double check just in case. So 72 plus 73 plus 76 plus 76 plus 78, right? And then divide that by 5, and you get 75. So that's how you get the mean. Now what you do is you take this mean and you minus it from each one. So minus 75, minus 75, minus 75, so on and so forth. And then you'll get these values. So you get minus 3. So 73 minus 75, you get minus 2. 76 minus 75, you'll get 1. 76 minus 75, you'll get 1. And 78 minus 3, it'll be 76. 78 minus 75 will be 3. Now look, if you take all the negatives, which are negative 5, and you just straight away add them to all the positives, you're going to get 0. So 5 minus 5 and plus 5, you're going to get 0. So the reason we square is because we don't want to avoid this. We want to avoid this 0. So when you square them, you're going to get 9 here, 4 here, 1 here, 1 here, and 9 here. Now we got rid of the negatives. Now you just add them all. So 9 plus 4 is 13. Plus 1 is going to be 14. Plus another 1 is going to be 15. And then plus 9 is going to be 24. So there you go. Now we're not done yet. Remember, we have to divide by n minus 1. So 24 divided by n minus 1, it's 5 minus 1 since we have 1, 2, 3, 4, 5. So it's going to be 24 over 4, which is going to be 6. Now 6 is the variance. Please be careful. If he asks you for the standard deviation, do not put 6. Do not put 6. All right? Instead, do the square root of 6, right? And this is going to be 6, whatever, inches squared. This is going to be 6 radical 6 inches, right? Not inches squared because we already got the square root there. So there you go. That's the answer. That's how they got the standard deviation. And I think this is a good time to just give you one small tip about the exam. And this is not just for biostat. This is for any exam. Step 1, step 2, anything. Okay. So if at any point you need to calculate something, my number 1 tip: once you realize you need to calculate something, flag the question. Just immediately flag the question, solve it, pick an answer, and then move on. Solve the other questions, then go back to it, because you're going to see it's flagged and you're going to go back to it. The reason you don't want to check your work again as you're doing the question, and avoid flagging it, is because your mind is in the same mindset. So if you made a mistake, if you immediately see the question again, you're probably going to make the same calculation mistake. Instead, I urge you to solve it, flag it, solve it, and just leave it for a bit, refresh your mind on some other questions, then go back to it. If you made a mistake, you're more likely to see it, given that you've already, relaxed a bit, saw some other questions, then got back to it. If you just made the mistake and then you're seeing it again immediately, you're probably going to miss the same mistake again. So any calculation question, doesn't matter if it's step 1, step 2, biostat, doesn't matter anything. Solve the question by calculating, and then flag it, go back to it later. Don't try and check your work again, because you're just going to waste time and you might not pick it up, and you're less likely to pick it up. My second tip, and this is the last tip, is that just because the answer that you found is available in the choices, someone is in the chat, just because an answer is in the choices doesn't mean it's right. This isn't back in grade 10. Grade 10, the teacher didn't have much time to make clever choices, so he just didn't care. But step 1 and step 2, they are extremely meticulous. They write questions so clearly and so cleanly that they really are harping on one major concept that you're not possibly getting. So usually people complain that the question's bad, but no, the question's incredibly good. So, they will anticipate you, for example, stopping at the variance and thinking this is your answer. So they'll ask you standard deviation and they'll keep 6 as the answer. And you'll think, oh, I got 6, so that's the answer. So rule number 1, solve, flag, move on, go back to it. Don't just check immediately. The second one is, if you see the answer that you get, don't try and think that that's the answer. Because sometimes Dr. Hassan would do it. Like Dr. Hassan would actually sit down and think of the ways you would wrongly solve it. And he would find the answers and put them as choices. So he's really checking whether you're able to understand what exactly he wants, not just checking if, like back in grade 10 where, oh, I didn't see the answer, so obviously that's not the answer, I did something wrong. No, you will see the answer. At that point, you have to think about it. So there you go. Just those 2 quick advices about calculations, because you might make a mistake. Out of all of you, I'm sure one of you might make a mistake. So please try and pick it up. All right, so this is the same thing again. We're not going to do it, but basically the same principle. Find the mean, minus the mean from each of the points, square all of these. This is your value. Divide by n minus 1. You're going to get your variance. Square root that, you're going to get your standard deviation. Now this is your variance, but if you square root that, you get the standard deviation. All right, so this is the same idea, is that we usually like to have our units the same as the units of the data set. So for example, if the units are centimeters, we don't like having it centimeters squared. We like having it as centimeters. That's why we do standard deviation and why we square root it. All right. Now, standard deviation has the same unit as measurements, which makes it more ideal. So that, everything that we're talking about here is the same. In comparing 2 groups of data, the group of the larger S exhibits a greater amount of variability. This makes sense. I told you that, if you have this distribution versus this distribution, this will have a higher variance, i.e. a higher standard deviation, than if you compare it to this one. This has a lower standard deviation, lower variance. Right. Now, usually, remember when I told you that the chest leads, you need like multiple ones in order to know? Generally speaking, it's true. Like, it's better to have the mode, median, and mean all accessible if they're meaningful, not like with nominal cases like we saw. If they're meaningful, put them all. And give us range, give us interquartile range, give us box, give us everything. It's fine. If it's meaningful, give us everything. But generally, the 2 things that are the most important to understand what a curve looks like are the mean and the standard deviation. If there are outliers, then usually it's the median and the standard deviation. But the general idea is just that the mean and standard deviation are usually enough to describe a distribution. Now, coefficient of variation, there's really not much you need to know about it. It's basically, it's dividing the standard deviation over the sample mean. And, the higher the number is, it's basically not only a link between being able to find out whether one distribution is narrower or less or wider than another, but also a good relationship between the standard deviation and mean. Are the numbers closely linked to each other? For example, is the mean 2 and the standard deviation is also 2, or is the mean 200 and the standard deviation is 2? So it not only gives us a link between 2 different distributions, but also a link of the distribution's mean and standard deviation together. So that's all you really need to know about it. It's useful for comparing the variability among 2 or more data sets, and it has no units. The answer is simple. It's because this, for example, will be centimeters. This will be centimeters. When you divide centimeters and centimeters, just like back in physics class, you get no units. And it's usually, represented by a percentage. So, for example, the coefficient of variation could be, for example, 70% or 50%. And you don't need to interpret them. You just need to know that, hey, this is, for example, this is how we calculate it, and its use is to just compare two different variabilities of two different data sets. So we kind of finished. This is just some like closing points. Basically, with any piece of data, you can, if they keep repeating often enough, you can just group them. So instead of saying 12 and 12 again, you can just say there are 2 12s, there are 3 11s, known as 3 11s, 3 5s, then 1 6 and 1 8, right? So can we calculate this CV on the previous data set? Yeah, we can, sure. So the mean is 67, so it's over 67. And the standard deviation is radical 2.5. I'm not going to find what this actually is, but then just find it and then times 100. And that is your coefficient of variation. Again, you don't need to really know what this number means. Just know that its purpose, right? This is a bit too like complicated. Like if I go into really what it exactly uses, I'm going to stay here like an extra hour, I think. But yeah, all you need to really know that it just compares the two different variabilities between two different data sets. And group data, basically just showing you, he might give you an example of, he might give you this. Honestly, he might give you the same exact data set and just tell you which of the following is the correct grouped version. And he might just, put some mistakes in it and then just one of them is correct. So just, go over it. No, like try not to have your coffee in the morning and just try and actually get the right choice. These are just like simple. There's really no other way I can explain it. All right, mean and median, we talked about this several times. In a symmetric distribution, usually the mean is of greater value, but in a positively skewed or negatively skewed, usually the mean will be off-put. Usually in a positively skewed, it'll be greater than the mean, but in a negatively skewed, it'll be less than the mean. It'll be to the left of the mean. It's left of the median, sorry. And basically, we talked about this numerous times, and this just harps on it more. For a skewed distribution, I mentioned this to you again. The median is a better representation of central tendency. Why? Because the mean is sensitive to extreme values, because the mean gets affected heavily by outliers. So that's the reason why. And we are seeing again, sometimes they call it right skewed, positively skewed, same thing. It's all the same, positive or negative, it's all the same. Left skewed, it's all the same. All right, and then he has a distribution. All right, this is bimodal. Bimodal means there are two different populations. Here, for instance, a disease, a classic disease that has this sort of distribution is Hodgkin's lymphoma. Don't need to know that, just a random fact, but just know that it does exist. This isn't just a random distribution that no one uses. No, there are diseases that follow this. The Hodgkin's lymphoma affects the very young and the very old. So it should be natural for you to understand that, hey, it should have a bimodal distribution. Yeah, bimodal means two peaks. There are two peaks in the actual distribution, So this, for example, is the peak, and this is the peak here. And it suggests that there are two modes, Sometimes, the distribution looks like this. Now, I know this is confusing. Just ignore it. We also call this bimodal, even though this is the mode, right? Because this gets repeated more often. But usually in statistics, when we say bimodal, what we are trying to tell others isn't that there are two modes. It's more of telling people that, hey, there are two different populations. Like, for example, Hodgkin's lymphoma, young and old, right? And in Hodgkin's lymphoma, I think it looks more like this, where it's more common in elderly. So despite that, you'll find textbooks saying that Hodgkin's lymphoma is a bimodal distribution. So, but that's just too, I don't know why I'm opening this. Point is, the entire idea is that bimodal, you have two modes, right? So it's going to make sense that you should have two peaks, because these peaks represent the value. For example, -2 is being repeated the most, and 1.5 is being also repeated the most. So they are bimodal. So I hope that makes sense. This one's wider, higher standard deviation. This one's narrower. This one has a lower standard deviation. That's, again, just giving the same principles again and again. All right, now we can apply the mean and standard deviation to summarize characteristics. This is basically, he's telling you why are we learning all of this, because when you know the mean and the standard deviation, you're going to be able to understand a lot of characteristics of the actual data set, of the actual distribution. So that's why we use it. And now finally, we reach to the final concept, two medians as well. Nope, all right, hold on. The median is here. Median is here. right? Because again, remember, what are you going to do when you do the median? You're going to do crisscross. You're going to do crisscross, crisscross until you reach the 50th percentile. So you don't have two medians in this case. You have one median, but two modes, right? So I hope that makes sense, right? You're not going to be doing crisscross and then ending up here and here. All right. So if you did or did not complete it with a doctor, this part I will still explain it. It's very simple. Basically, the empirical rule. Look, even if you didn't complete it with the doctor, it's important for step one. So just know it just in case. So let me just get comfortable here. All right. Look. See. Okay. So he doesn't have the. Where was the distribution? Yeah. So look, the empirical rule, it says this: between one standard deviation and minus one standard deviation, minus one basically means going to the left, and one means going to the right, you have 67% of the data. Now, this is an empirical rule, which means it is a theoretical rule, which means basically this only happens in like theory and books and textbooks, because you're never going to have a distribution that's so beautiful and symmetric as this. Unfortunately, you're like, it's more practical, and I'll show you what you should use when it's more practical. But if it's a perfectly normal distribution, you use the empirical rule, which says that one standard deviation this way, one standard deviation this way, you'll have 67% of the data. If you have two standard deviations this way and two standard deviations this way, you'll have 95% of the data. 2/3 basically. I have no idea what 2/3 you're trying to say. But if you have three standard deviations this way and three standard deviations this way, you'll have 99% of the data. So between these 2 points, 67%. Between these 2 points, sorry, this here and here, you'll have 95% of the data encompassed in these 2 points. Between three standard deviations this way and three standard deviations this way, all of this is going to be 99% of the data, right? So you need to memorize those three areas. You need to memorize standard deviation. If you go one side this way, 67. Two sides, it becomes 95. And three sides, it becomes 99. You have to memorize them. It's not like an option. So yeah. But what if the distribution looks like something like this? What if it's like that? So it's very weird. It's positively skewed. It has like three modes. I have no idea. Point is, you can't really use the empirical rule. So instead, you have Chebyshev's inequality, and this is the formula. Memorize the formula. It's basically 1 minus 1 over k squared, and that's the whole formula, right? So k has to be either 1 or more, and it can only be integers, right? It can only be integers. And yeah, and if you want to, okay, so one standard deviation left and right, 67%. Two standard deviation left and right, 95%. Three standard deviations, 99.7. They have the exact numbers here, so I'll just go back to it. 67 or 68. It's because it's 67.7, so it's 68 sometimes. Some textbooks say it. 95.5 for the two standard deviations and 99.7 for the three standard deviations. All right. This is for the empirical rule. For Chebyshev's inequality, it's used for things that are not as symmetric, not as normal, so on and so forth. So we use this formula where k has to be 1, 2, 3, 4, so on, integers only. It can't be 0 or minus 1. It can't be anything like that. It has to be, for example, 1 or more. So let's for example say we have 1. So 1 would mean like 1 minus 1. 1 over 1 is 2. So 1 minus 1, you have 0. Well, 0 kind of doesn't make sense that much. Let's forget 1. Let's just forget 1. Do you have it over here? Yeah, he doesn't even start with 1. So forget 1. 1 doesn't make that much sense. Just let's focus on 2. So if you have 2, it'll be 1 over, he does it here for you, but 1 over 2 squared, and then k is the number of standard deviations. I forgot to mention that, sorry. K is the number of standard deviations. So 1 minus 1 over 2 squared. So here it will be 1 minus 1 over 4. So the answer would be 3 out of 4. Yeah, an integer that is greater than 1, but I think he has a typo in his slide. This should be just greater than 1, not greater than or equal. So I think it's a typo, because if you have it as 1, it's going to be 1 minus 0, which just makes no sense. It's going to be 1, which just doesn't make any sense. So yeah, I think it's just k greater than 1. Just make sure with him, either on Sunday, because if it's 1, it doesn't really make that much sense. Yeah, okay, never mind. It's right down here. Note only k greater than 1 provides useful information. So yeah, 1 really doesn't give you that much. It has to be more than 1. So let's say we did 2 standard deviations to the right, 2 standard deviations to the left in an abnormal distribution. For example, distribution that looks like this. And we have 2 standard deviations this way, 2 standard deviations this way. This is, for example, the mean, all right? Or the median, whatever you want to call it. Let's say the mean. Point is, how do we do it? We do Chebyshev inequality. We do 1 minus 1 over 2, and we square that, this fraction. It's going to be 1 minus 1 over 4. It's going to be 3 over 4. That means within 2 standard deviations, in 2 standard deviations, we cover 75% of the data. We cover less data because the distribution is very weird. We can only cover 95 and be very precise and be very accurate when the distribution is normal and when the distribution is actually very symmetric and nice. But when the distribution is not that normal, notice how 2 standard deviations now is not 95%, it's 75%. If we did 3 standard deviations, it would be 1 minus 1 over 3 squared. It would be 1 minus 1 over 9, 8 over 9, which is around 88% of the data. So if we went 3 standard deviations this way and 3 standard deviations this way in this abnormal distribution, then it would look like it would cover 88.9% of the data. I don't know if the doctor covered for you, but I'm covering for you just in case. All right. So if he asks you, he asks you. With that said, basically we covered the entire lecture. This is just an example, and yeah. So we have one lecture left, and yeah. I don't know if you guys want us to do it now or take a break. Let me close the Twitter page. Also, shameless plug, in case anyone wants to follow me, I am, I'll just put this thing in here. There we go. Just a little shameless plug, just in case you want to follow me. I'm sorry. All right, so Doctor, is it possible to do the last lecture tomorrow with the last 2? Yeah, if you guys want to do that, but like, I'd rather we finish it now to give you more time to study tomorrow. But if you guys want to do that, it's up to you. So for instance, he gives us a graph and we choose whether it's Chebyshev's. Yeah, he could do that. So he could give you an abnormal distribution and ask you, would it be more practical to use Chebyshev's inequality or that? That would be more of a theory question, not really asking you to calculate, more of just a theory question. Or he can ask you a memorization question, just tell you in a normal distribution, if we go 2 standard deviations to the right and to the left, how much of the data would be covered, and you have to say 95% of the data. So it really depends on you. Coffee, I don't know what you think. Bahaha. All right, now break. Some of us have English tomorrow, or tomorrow if possible. No, please, no, today. All right. I don't know why you guys are making like a very big deal about it. It's recorded, so like even if you like want to go, just go and just see the recording tomorrow if you want. But yeah. So, oh Lord, now we're getting some follows. All right. So it's up to you guys, English mid guys. Whoever has an English midterm, you can go. Like you can just watch the recording some other time. And yeah, but let me just get the other lecture up. It is a long lecture. I don't think I think we'll be finishing it by like 9, possibly maybe 9:30. But yeah, so let me just check the questions. One question: standard deviation is assuming that this is a normal distribution. Is that why? No. It's fine. It's fine. Standard deviation can be used whether the population, whether the distribution you have is normal or abnormal. I just sometimes say median to not confuse you, but just keep it mean. Just keep it mean for all the times, because you're going to use mean in order to find the standard deviation. You can't use the median to find standard deviation. Remember, the formula was that you use the mean. So always remember, mean is standard deviation. So don't try and confuse you. I know it kind of contradicts what we said earlier. Oh, if it's an abnormal distribution, if it's positively skewed, don't we use median? It's conflicting and it's kind of confused. It'll confuse you more than it'll help you. So just try and keep the concepts separately. When we talk about standard deviation variance, yeah, always use mean. But when we talk about the other concepts separately, like for example, if it's positively skewed, we report median as opposed to the mean. We still find the mean. It's not like we ignore the mean. We still find the mean, but the median is of more importance. No, it's okay. We can do it today. Now, please. Yeah, we'll do it. We'll do it. No, today, please. It's recorded for those who are having English midterm. It was a suggestion. Yeah, okay. Yeah. It's like we're all okay with it. I have a question. So basically, we use the mean standard deviation to draw the normal. No. Look again. Mean and standard deviation can be used for any population. Okay. It's just that when it comes time to report things, you have to accept the idea that a median is better than a mean. So just keep that idea in mind. All right, let's make it today. All right. I think we covered everything in the chat. All right. Now we're gonna do the last lecture. If you guys want to break because it's quite long, if you want to break halfway through it, I also don't mind. Enable editing and. All right, so yes, can we have a break now? Sure. Okay, so again, the more breaks you take, it just means that we have to finish later. So I'm fine staying here till 10. That's not a problem. Like I said today, like I'm not going to study anything, so it's fine. Good question. Okay, so since it's a break, there's no prayer or anything. I'm just gonna be here taking questions. No, look. This lecture is the hardest. So if you need a break, it's fine. We can wait 10 minutes. It's fine. So. If you have any questions, you're more than likely to ask. Yeah, I won't forget this time. Just one sec. There we go. All right, there we go. If you have any questions, feel free to ask them now. Can I unmute? Yeah, sure. Go for it. Can you unmute? Should I like give you the ability to unmute? I don't know how to give you the ability. Yeah.
Oh, no.
Yeah, there you go. Yeah, I can hear you.
All right. I have a bunch of questions from each lecture that I have.
All right.
I want to understand a little bit more. So when you're done with everything, can we touch on them, or do you want to like touch on them tomorrow?
Look, how about we start? We start 8:05, and you can ask me some of them now. And if there are any other questions, it's fine. We can. If there are a lot, it's fine. We can just finish some of them, and then by the end we can finish more. So ask some now.
Sure. Okay. Mainly they're about the implications of certain concepts on the exam and how they would come. Mainly. Should I just do questions for that and see how that happens? Then I could maybe contact you or just get to understand them more, or should I?
Yeah. If there's any question like Biostats wise, just I promise you guys don't have my number. I'm not. Okay, never mind. Just email me. I'll leave my email. Or you can follow me on Twitter and message me there.
All right. What's your Twitter handle?
It's
what's your Twitter handle?
Cal Eternal. That's Khal Eternal. Like Khaled, like yeah. Eternal.
There you go.
Just shout out. Sorry, just crazy there. I'll just leave it in the chat. I'm not like Ijaz. I don't tweet every second. And you can tell myself.
But
Farah can tell him. She's still active on Twitter as well. All right. So yeah, you guys have past questions. You guys can do past questions and like use them to understand, use them to know, see how he'd ask. Because look, like although biostats is simple, it's simple. Like when you enter there and you actually understand all the concepts, you're gonna notice that the exam is all right. The problem is that there's very little room for error. If you make 5 mistakes, that's probably like 5 marks right there off. So you probably already lost the A if you make 5 mistakes. So I don't know if this was addressed, but this was a problem for us because if someone made 5 mistakes, cost.
how many questions is it?
It's that's something for you.
How many questions is the midterm?
For us, it was 40 and maybe even less, like 40, and it was 40 marks. But you guys need to know. Yeah, it's for you guys. I'm saying 30. Yeah. I don't like. I'm a person who likes a lot of questions. Like even people say that step 1 and step 2, 280, 220 questions. That's actually a good thing. That's obviously it drains you, but like imagine your entire score is just based on 40 questions. That'd just be ridiculous. So the more questions, I think, no matter what, is always the better. Unless it's something like crazy, like 800 questions, but no. So yeah, it's up to you. By the way, we're taking a break until 8:05. So just in case anyone is staying here for any reason, you can go and grab a snack or something or water if you want. And if you have any questions, it's fine. Bye. Yeah, the next one is probability. It's the hardest lecture of today, but it's not that hard. It's just, we finished 3, we have 1 more left, and it's going to be good. I used to do all of these in one go, like the entire midterm content all in one day. So I'm kind of happy that, that kind of sounds crazy, but I'm kind of happy we're doing it online. So that, we can spread it out over 2 days. We don't have to get everyone to come. Also, yeah, when you do it, like this was a big problem. When you do it like in person, no one ever comes on time, except for some reason for the past 3 years, the girls always come on time. The guys are always, I don't know why, it's always 30 minutes. It's exactly 30 minutes until every single person comes. I don't know why. It's just like, I don't know. Here, no, we don't have that problem. Like we can just have anyone join the second that we come. Yeah. Another thing that I kind of appreciate is the fact that, like, usually I would hide the fact that we'd recorded for the previous batches, because then no one would come and no one would ask questions. So then I would just be talking to the wall and I'd just be explaining, and I don't know if people are getting or not. I'm getting like, you can make the argument that I don't understand what you guys are. I don't understand if you guys are getting me or not getting me, because I can't see any of your faces. I can't see anything, but the chat does help me a lot. And the fact that a lot of you are here asking questions is good. But yeah, previously I used to lie, always tell them, no, I don't want to be recorded, I'm shy or something. But at the end of the day, I'd secretly text one person to bring a camera, and then we just recorded, because I don't know, like I just wanted people to come, but at the same time, I didn't want to make it seem like if they had something urgent, they couldn't show up. Because it helps you guys more than me to have a lot of people. You guys ask questions and everything. We have 4 more minutes left, and we can start.
Hi, I have a question, please.
Sure, go ahead.
So during the box plots, when we only have one median, okay, and then we do calculate to make another median, the
75th and the 25th.
Yeah. So
yeah.
do we conclude the median that we get, the first median?
Yeah, the first median is the actual median. It's the actual median of the data set. It's the 50th percentile, which is the definition of the median. The other 2 values, they are the 75th and the 25th. The idea is that if you start from here and go 0 to 50, right? The 50th percentile of this region is the 25th percentile. That's why I say do the median for this region, right? And then for this region, it's from 50 to 100, right? So if you take the median of this region only, 50 to 100, then the median is 75 in this region, right? So that's why I say take the median, which is the 50th percentile, and do this median and do this median to find the actual 75th and 25th percentiles. But this is the actual median. Like this middle line here in the box plot, it's actually termed as median. So it's the median of the actual whole data set.
Oh, okay, yeah, I get it. Thank you.
You're welcome. Yeah, and an even data set, yeah, the median will be between 2 numbers. So you take the average of those 2 numbers.
Assalamu alaikum, Khaled. I have a question.
Alaikum assalam.
Just regarding like your midterms and your old finals, like did you, when you did when the previous batches, the old midterms and old finals, did they help you? Or like were the questions similar?
It's not that I honestly can't remember, to be honest, but I did them, and I remember like doing them helped me because I got a lot more reassured that, hey, the questions are going to be all right. Because it was the first time we saw Dr. Hassan's questions. We didn't know how they were going to be, like, and you spend so little time with him. Like 4 lectures is not enough to know like who he is and everything. And he's actually an amazing dude. But like the point is that I was nervous to know what his questions were, because if you write a question, you can make it as complex or as simple as you want. And his questions, in my opinion, are extremely, not simple, but you know what he's testing you. You know what he's testing you. The only person that makes the question complex is yourself. So doing the questions helped reassure to me that, hey, the questions are going to be inshallah simple. And yeah, that's why
Okay.
I did them.
Thank you so much.
You're welcome. All right, I'm just going to need 1 minute. I'll be right back. All right, we're back. Sorry about that. Let me take this off. So we're going to start with the last lecture, sorry, the last lecture. And it's the hardest one. Where's the, okay, there we go, share. And slideshow, setup, slideshow, show information, and that's, there we go. All right. Now, this lecture is the most important because it has a lot of principles and a lot of rules, and you know, the beginning part of it is all right. It's not. You guys can hear me? Okay. I'm not muted. Okay. Let me just bring up the chat. All right. So look. So remember how we talked about descriptive and inferential statistics, yada yada yada. We can use probabilities to sometimes make generalizations. Blah blah blah. This is all like stuff we already talked about. We saw this graph a million times. Yada yada yada. Just forget about it. Now everything is subject to random variation. For example, let's say I want to toss a coin. That's random variation. Now, a lot of the things in medicine, again, they're subject to random variation. For example, if we have, let's say, for example, the probability of getting lung cancer, assuming you're a smoker, that's random chance. There are ways you can study random chance. So it's important that since a big portion of medicine is random, like there are random things that can happen, we need a way to quantify them. We need a way to understand how to approach them. So for that reason, we develop probability, which is trying to study the theory of probability and the probabilistic model. So he gives you a lot of examples. Let's just ignore them. He gives you a model. Again, you really don't need to go over it because basically what he's trying to say is that, let's say, for example, the chance of staying in a hospital is Y, for example, or the how long you'll stay in a hospital is Y. And then different things could take into consideration of changing your how long you stay in a hospital. For example, this type of surgery, the surgeon's proficiency, for example, the exact severity of the tumor, yada yada yada, blah, blah, blah. The point is, a lot of things you can account for and you can calculate for, but there's always this thing where even if you have two people with the exact same age, exact same disease, exact same surgery, exact same surgeon, at the end of the day, they might have slightly different stays in the hospital just due to random error, just due to things that are out of our control, things that we can't really calculate. And that's important because despite them being the same, we still get different things happening. And for that reason, we really need to understand what probability is and how we can best quantify it, how we can best study it. So here it gives you the length of stay, just like the example I gave you. Some different things, but there's always this little piece of error that we talked about. All right, now we begin with the actual lecture. We have, just 1 second, because the chat keeps disappearing every single time I think we took only the first 20 slides, first 50. All right, so we'll stop at 50, I guess. Maybe we'll do the rest tomorrow. Point is, let me stop this here for 1 second because this is kind of annoying me. I don't know why the chat keeps disappearing every time I press the. Let me press this, and then chats. All right, whatever. I'm just gonna have to keep looking up if one of you talks. Okay. So what is probability? It's the mathematical means of sort of understanding uncertainty, understanding how things can happen random chance. The slides with your keyboard. Yeah, the problem is when I click on the chat, it doesn't give me control of the slides. I can press the keyboard, it doesn't give you anything. When I press on the slides, it gets rid of the chat, but I can now use it. It's just whatever. I'll ignore it. It's fine. So the probability is understanding uncertainty, and that is important because sometimes there are things that happen in medicine by chance, yada, yada, yada. So let's try and understand what probability is by using basic examples so that then we can apply more complex examples. So what is probability? The mathematical means of studying uncertainty. All right, that's bare bones definition. An experiment is a well-defined procedure that you need to do that will lead to certain outcomes. So for example, tossing a coin is a procedure, it's an experiment. And it's well-defined with clearly defined outcomes. It's either heads or it's tails, right? The sample space are all the different outcomes that could happen. So the experiment is tossing the coin. The sample space is, for example, heads and tails, right? So those are all definitions. We still didn't really get into the meat of the lecture. They could be simple events, for example, only one outcome, or they could be complex events. For example, what's the chance of getting a heads and, for example, spinning the spinner and getting the color red? So although these are two different, technically events, we want them to happen at the same time. So therefore, it's a complex event. And, he doesn't really talk about complex events, but this is the general rule of it. So consider tossing a 6-sided die. Is this an experiment? Yeah, we're saying it's a well-defined procedure. We're going to throw a 6-sided die, and we have a good sample space. We have 1, 2, 3, 4, 5, 6. So now what's the chance of getting a 3? The chance of getting a 3 is 1 out of 6 because there's only one of these, right? And then we count all of them, 1, 2, 3, 4, 5, 6. So it's 1 out of 6 out of all the possibilities that could happen. Right, so he gives you other examples. So for example, getting an odd number, let's go back to it. So there's 1, 2, and 3. So it's 3 out of 6, which is basically half. If you're getting the number 2 is like getting the number 3, so it would be the same, so it'll be 1 over 6. So you get the picture. He probably played this game with you, the birthday game, and you were surprised to find out that if you just have, 23 people, just 23 people, there's a half chance of 2 of the people in this 23, group that they have the same birthday. So that's surprising. So probability is not really that intuitive. You sometimes have to understand probability by using formulas and by understanding what exactly it's trying to say, as opposed to just trying to understand that, oh, hey, probability. Like I'm sure the majority of you, when you thought of this birthday game, maybe most of you picked somewhere around here and here. With your batch of around 100 people, the answer should be around here, right? There are easily like 68 people here. So if I go to 68, notice how it's around here. It's close to 100. So there's a very, very likely chance that 2 out of the 68 people that are in this call right now, there's an extremely likely chance, almost 100% chance that the 2 people will have the same birthday out of these 68 people. So probability can be sometimes non-intuitive, but we're going to keep the example simple and then ramp it up from there. So let's go to it. Before we tackle on very, very hard examples, I have a few formulas that we need to discuss. So the first one is A intersecting B, and the next one is A with something called union B, right? So what does this mean? I used to always forget which one's intersecting, which one's the union. So this is my own mnemonic. Feel free to use it. Imagine there's a spider in here in the center, right? And there's a spider here. Now, if the spider is stuck inside the cup, it is stuck between both A and B. So it's stuck there. It has to be between A and B. So it's an intersection between A and B. If the cup is just open and the spider's inside, it can jump to either A or B, right? So that's how I remember it. Both A and B, when it's stuck between the cup, when it's stuck inside the cup, it's stuck between both A and B, both A and B. But A, UB, right? AUB, the U is opened to up, the union is opened to up, so the spider can jump to either A or B. That's how I remember it. Now, what does union intersection mean? Basically, if I give you a question, here's the typical question that he might give you. Let's say he tells you, you have a bag. I want some of you guys to answer here. I want to keep the chat open after. Let's say we have, for example, a blue ball, a green ball, a yellow ball, and a red ball, right? He tells you, what's the chance of getting either, actually, let's just make it even simpler. Let's say we only have the green ball and the red ball. What's the chance of getting either the green ball or the red ball? So just put the answer in the chat. All right. So look, some of you said half. Some of you said 1, which is 100. Now those who said 1, they're absolutely right. The reason is because when we say either, we don't mean just like if I ask you what's the chance of just getting the green ball, then yeah, the chance would be half. But I'm telling you, what's the chance of getting either the green or red ball? So regardless, let's say you put your hand into the bag, regardless of what you pick, it's either going to be a green ball or a red ball. So no matter what you pick, it's always going to satisfy the outcome. So the answer should be 100%. Now, how do we get 100%? It's simple. When I say either, we basically mean either or. The spider is open. When you have the spider, it's open, you can go to either or. You do this formula. The probability of A plus the probability of B. The probability of A happening here is half. The probability of B happening here is half, right? So you add them, it's going to be 1 or 2 over 2. It's going to be 1 basically. So it's going to be 100%. And that should make sense to you. Look, again, when I say this question, the majority of you think, oh, what's the probability of getting either the green or the red ball? Yeah, 50%, because if you grab it, it's either 50% for the green or either 50% for the red. No, what I'm saying is if you put your hand into the bag and pull out a ball, what's the chance that it'll be green or red? It's 100%. You're going to grab one of them, and one of them will either be green or red. So I really hope you understood this principle. So the answer is 100%, because when it's union, the formula is that you add them, right? Now here's an important question. What is the chance of going into the bag and grabbing, and you can only grab one ball, what's the chance of grabbing both the green and the red ball? So what's the chance? I'm just trying to see if you guys understand. All right. Oh my God. All right, yeah, here we go. 0. Everyone said 0. Exactly, because you can't grab both at the same time. So all of you already are understanding probability a lot better. So I hope you all understand why it's 0, because you can't grab both the red and the green ball at the same time. These things are said to be mutually exclusive, meaning they can't happen at the same time. Right? So when that happens and you want them both to happen at the same time, it's impossible. It'll be 0. Now, what's the mathematical term for it? Basically, it's going to be you multiply the probabilities, but there's another reason. Basically, you can't multiply the probabilities if they're going to happen at the same time but can't happen at the same time, right? And you know, I'm making it a bit more complex, but this lecture is a very long lecture. I'm just giving you a brief overview. Let's take another example. Let's make it easy. You have a bag and it's filled with a green ball and a red ball. So green, red. What is the chance that when you go into the bag, you'll pick first a green ball, then you return it, then you pick the green ball again? What's that chance? Now, what I want you to think is that it's going to be, remember, I'm telling you this and then this. So I want them both to happen at the same time. So what's going to happen is this. The first chance is half, right? Because you want to pull the green ball. So the first chance is half. And then the second chance, you want it happening again. You want it happening together. So you're going to do half times half, right? And it's going to be half times half, because you want to get the green ball the first time. And then the second chance is half, and you want them happening together, you know, one after the other. So it's going to be the intersection, and with the intersection, you multiply the probabilities, and it's going to be half times half equals 1/4. If you didn't get this, we're going to keep repeating it a million times with a million different examples. But I hope you understand why it's 1/4. And a lot of you are saying 1/4, and I hope you understand why. So probability of green and probability of green times probability of green. Whoever put plus is probability of green times probability of green, right? So that's why we say it like that, instead of just saying, for example, probability of green plus probability of green. The main point is that if it's intersection, if you want both happening at the same time or both happening one after the other, so on and so forth, you do times. You multiply the probabilities together. If you want one happening or the other happening, you just add the probabilities, okay? So I'll give you another example. What's the chance when you roll a die, you know, the one die with 1 to 6 faces, you're going to get an even number or an odd number? So remember, an even number, what's the chance of getting an even number? Here's what I want you to think. What's the chance of getting an even number? It's 3 out of 6. What's the chance of getting an odd number? It's 3 out of 6. It's either or, so we're going to do the union, and the union is plus. So we're going to do plus. So it's going to be 6 out of 6. And that should make sense. What's the chance of getting an odd or an even number? If you throw the dice, you're going to get one of them. You're going to get either an even number or either an odd number. So again, all of you are answering, I didn't get it. All right, so this is usually the lecture that takes a lot of time for me to explain. It's fine. Look, what I want you so far just now to know is just that if I want two things happening at the same time, I should multiply the probabilities together. If I want both events happening, you know, doesn't matter which one, this one or this one, or this one, that's the keyword, or, then you add them together, right? Union displays or, so either or. Intersection, where the spider is stuck between both, means that you have both need to happen at the same time. We'll do more examples. If you didn't get it, it's fine. Now, complement is something else entirely. Complement is the exact opposite of what you're trying to get, for example. So for example, if the probability of that you're interested in is the probability of getting heads, then the complement is the probability of getting tails. So you see, so it's the exact opposite. It's the probability of getting everything except what you're interested for. So for example, if let's say a die, you're going to throw a die, and you're interested in getting the number 2. And the complement is everything other than 2, like 1, 3, 4, 5, and 6. Yeah, so this is the complement, this is the probability. This is the probability. This is the probability. There we go. Yeah. Multiply. If it's union, you multiply. If it's union, you add. Sorry. If it's I'm getting distracted by my brother. If it's union, you add. If it's multiplication, if it's intersection, you multiply. All right. So I hope that so far is clear. Don't worry, we'll keep building on more and more onto it. So that's what I want you to know so far. Now, when he gives you an idea of what an intersection looks like. So for example, this would be an intersection. Color's not really that good, but this would be basically intersection, and this would be union, right? So this basically either this circle or this circle, doesn't matter. But here you're only interested in the connection between the two circles. So this is just another way to look at it. But let's keep going. I'm sure you're going to understand it as we take more examples. Okay, so sorry about that. I have no idea what that was. It's kind of falling apart right now. Point is, Right. So remember when I told you that the probability, if you have, for example, 1, 2, 3, 4, 5, and 6, remember how we said if we're interested in 2, we take that 1 and basically we just count all the rest? That's exactly how we do it. It's just that we give these terms as m and n. So m is the number of things you're interested in. Note I say the number of things, not the actual number, the number of things. Here we're just interested in one thing, so that our m equals 1. And how many things do we have all together? Our n, we have 6, so 6. So that's how we find the probability. You just find what you're interested in, our m, and then our n, which is in this case all the observations, all the things in your sample space, which is basically 6. Right? So that's the main gist of it. All right. So let's do some examples. A living creature dies someday. Forget what I told you in the second lecture that everything's possible. A living creature will definitely die someday. So this is A, right? So it's 100%. It'll always happen. You don't have to take the BEP 235 cash course. No, you definitely have to. So for that reason, it's a 0. So this is going to be B, right? If you flip a coin, the outcome is head. That's going to be half, right? So because you only have heads and tails and you're interested in 1, but you have 2 outcomes, so 1/2. That's going to be 1/2 right here. This is going to be C. And then if you have a choice between red, yellow, blue, or green, you'll choose red. So again, red is 1 outcome we're interested in, and we have 4 different outcomes, which are red, yellow, blue, and green. So it's going to be 1 out of 4, our M over our N, and this is our D. So that's going to be the exact same choices that I said. Another way of doing it is the same way that I'm showing you, is basically list out all the sample space. For example, if we have a die, just write out 1, 2, 3, 4, 5, and 6, and then just find out how many events you're interested in. So for example, if you're interested in 2, then that means that this is 1 value, so you have 1/6. So this is just another way to do it. You don't have to do M over N. You can just write out the sample space, write out all the possible outcomes, and then you can just find out how many you're interested in, and then put that number on top, and then find how many there are overall, and then put that number on the bottom. So tossing a fair coin twice, all right? So is this an experiment? Well, the answer would be definitely yes. It's a clearly defined experiment, and we have a perfect sample space. So what are the outcomes? We have heads, heads, tails, 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 heads, and then, this is tails. Tails, heads, and then heads, tails. So we have 1, 2, 3, and 4 different possible outcomes. And he's asking, what is the probability of the following event? What's the probability of the following event? Heads appearing on both tosses. So this is the only one. So we have 1 as our M, and then our N, our denominator, is going to have 1, 2, 3, 4, because that's all the possible outcomes. So 1/4. So the answer should be 1 out of 4. Right? And that's the exact answer. So do you all, this is extremely simple. Do you all get this part? Every single part of this, heads, heads, tails, 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 heads, everyone is an independent event. Everyone is a single event, and each one is an event. Here we have 4 events, but we're only interested in 1 event from this experiment, which is the heads, heads. So the chance should be 1 out of 4. So all of you understand this. All right. Now he makes it a bit more complicated just by using worse numbers. Basically, here's what he uses. He says, if for example you have 99,149 people who are surviving, and you have 100,000 out of all of them, then basically he's telling you how many are dying. So you can just flip it by finding the complement. So what's the complement? It is 100,000 minus this number, and you can find the probability, right? So he makes it a bit more complicated by just using big numbers, but this is how you're supposed to do it. So find the probability of surviving. The probability of surviving is simple. It's this value, which is our M, over this value, which is our N. So it's going to be 99149 over 100,000. Now, if he wants the complement, you just do 1 minus this value, right? Or this value, rather. So once you do that, you're going to get the complement, which is basically, it's going to be in the, I think it's in one of the later slides, but basically you all get this idea, right? So here in this particular example, he's asking just for the probability of surviving, which is this probability. But later on, you'll see he brings you the same example, but asks you for the complement. The complement is just, you do 1 minus it, because remember, let's say, for example, you have the chance of getting heads is 50%. What's the complement? Is 50%. It's just 1 minus that probability. If the chance of anything happening, for example, is 25%, And the complement is 75%. It takes that other sort of gap. You know what I mean? So complement, and I hope the number of subtracting is the complement, right? The number of subtracting is the actual probability that we're interested in. So in this case, the probability of surviving is 149 over 100,000. This is the probability of surviving. The complement will be the probability of not surviving, for example, in the first year of life. So how do you find that out? You do 1 minus the actual probability that you had earlier. That way you find the rest, the actual rest of the missing percentage from 99, 149 over 100,000. So I hope you guys are somewhat getting the idea of what's yeah. All right, so people are understanding it. All right, some people are asking, but I'm not even seeing the question, so I just have to. I'll just stop one more time, just because I really need to see if this is going to work or not. Does it work? Oh, there we go. Now it works. Okay, so now I can see the chat. So let me just tackle a few questions that are happening. They aren't mutually exclusive. We'll get to mutually exclusive later on. We'll talk more about it. But do you all understand this? Do you all understand why in this example the probability of surviving is 99, 149 over 100,000? If you understand that, then it's perfect. That's the yes. Okay, so you all understand that. So if they were to ask you the complement, we'll see that example soon. If they were to ask you the complement, this is going to be 0.99149. We're interested in the opposite of that, which is going to be 1 minus this thing. That will give us the actual probability complement of this thing, right? So that will give us the probability of not surviving the first year of life, right? So he gives you another example. For example, if you have 14 students who had one, for example, course, what will be the probability of randomly meeting one student who's done one course? It will be 14 out of 35, right? And he does this probability for every single one. It's 7 out of 35, 14 out of 35, 10 out of 35, 4 out of 35, and he lists them all here for you. And he gives you a bar chart that basically shows you that the highest probability is with 1, which makes sense because it's the highest probability. This is 40%, 20%, 29%, 11%. So this is just another example, shows you how to calculate probability. This makes sense to all of you, I hope. If not, feel free to ask a question at any point. Now, you probably already noticed we're only considering values from 0 to 1, right? 1 means it is going to happen. In other words, it's 100%. And 0 means it's not going to happen. It's, there's no chance of it happening. Sometimes things aren't just, black or white, 100 or 0. They're, shades of gray. There are things in the middle. So for things that aren't certain or impossible, you have all these things in the middle where, the chance could be, for example, 50%, 25%, so on and so forth. All right. For example, the probability of an event that cannot happen, February 30 days is 0. He keeps it very simple, right? But in my opinion, this could happen. February of 30 days, this could someday happen. Maybe in like 20 years from now, we have February 30th. I don't know. But the idea, just keep it simple and just understand that for the exam, answer 0. But when it comes to the final crash course, whenever I ask you if something's possible, just say, no. Just say, yes, it's possible. But here, for example, no. The chance of February 30 now is definitely 0. Probability that Friday comes after Thursday. Yep, Friday always comes after Thursday, so that's a 1. The probability of receiving an A in the BP 25 crash course in the actual course is between 0 and 1. So yeah, that's a nice way of showing you how things could be impossible or, for example, certain or in between. Now this is what I was saying. Now he really introduces a lot of concepts here really quickly. Basically, probability of A happening. Didn't we say that the probability of A is a certain event and the complement is everything opposite to that event? So when we want both event A and its complement happening together, in other words, intersection, in other words, we want to multiply them to see what happens if they happen together. Nope, it can't happen together. There's a 0% chance of it happening together. For example, what's the chance of rolling one die and getting 1 and 2? That's it, and getting 1 or getting 2. And getting 2, sorry. So the chance should be 0 because you can't get 1 and 2. You can only get one number. So, although 2 isn't the complement of 1, in fact, I can make it the complement. What's the chance of getting an even number or an odd number? There you go. That's exactly the probability of an even number is going to be, for example, 3 over 6. Probability of an odd number is going to be 3 over 6. So what's the chance of getting an even number and an odd number? It can't happen because you're only going to get one of the two. So again, if you have a probability and you try and find the intersection, in other words, multiplying the probabilities, but they can't even happen together, then it's impossible for you to say that there's a probability of them happening together. Always, if you have probability of A, and the probability of its complement, the probability of the event A's complement, it should always be 0. It should never be anything other than 0. Now, what I mentioned here isn't exactly complement, right? Because the complement of 1, of getting 1, is 2, 3, 4, 5, 6. The complement of 1 being all those numbers is not the same as 1 versus 2. These are said to be mutually exclusive, meaning they aren't really complements, but they still can't happen together. They still can't happen together. And for that reason, even if I tell you that the probability of A, which is of getting 1, and the probability of B, which is of getting 2, what's the chance of them happening together? You should immediately say 0, because there's no way we can multiply them if they can't even happen together. There's no point calculating anything if they can't happen together. So what I'm trying to say, at the end of the day, if you're comparing a complement to the same event, the other event, the opposite of its event, or the event and its complement, you should always answer that the probability is 0. However, also if they're not complements, but they're still mutually exclusive, meaning if one happens, the other can't happen, then you should also still say 0, right? So whether it's complement or mutually exclusive, the probability of them happening together in an intersection is always going to be 0. So I hope that really makes sense. All right, so if you have any questions until this point, feel free to ask. Now here they mentioned the rule that I told you. If you have any probability, to find its complement, you just do 1 minus that probability. You'll find the complement instantly. So for example, if the probability is 1 over 6, then the complement immediately is 1 minus this, which equals 5 over 6. Right? So that's important, and I hope you can realize the importance of that. So that's how you calculate complements, and we're going to talk about them a lot in this lecture. So for example, what's the chance of rolling a 5 or a 6? That's going to be 2 out of 6. Now, how did I get 2 out of 6 so quickly? Basically, they said or, so I know it's union, so I know I have to add. So what's the chance of getting a 5? It's 1 over 6. What's the chance of getting a 6? It's 1 over 6. So it'll be 2 over 6, right? Yeah, complements are always mutually exclusive. That's the definition of complements. But not because things are mutually exclusive, that means they're complements, right? So what's the complement of this one of rolling a 5 or a 6? It's rolling any other number, like 1, 2, 3, or 4, right? So what's the chance of rolling, for example, 1 and 6? It just doesn't make any sense. It's going to be 0. So I hope that makes sense. Right, and here he just showed it. So he showed you how he did it, basically. So he's telling you, what's the probability that you roll a 1 or 2? Let me just move the chat here. Yeah, what is the complement of AC? What is the probability of rolling 3, 4, 5, and 6? What's the probability of both this and this? Basically, you see, he shouldn't have said and. He should have said or, but I don't know why he said and. Basically, what I'm trying to say is that if he asks you what's the probability of A happening, or the probability of the complement happening, A in superscript C, you should always answer 100%. Because if he tells you or, not and here, I don't know why he mentioned and, just forget about and. If he tells you or here, what's the probability of A or AC? It's 100%. It's definitely going to happen. It's definitely, you're either going to get the probability that you have or the complement, the other side of the board. But what's the probability of getting this and this? It's impossible. You can't get this and this. So I hope you can appreciate this small little nuance. So once again, if he says and, it should always be an intersection. Therefore, you should always multiply. In the case where they're mutually exclusive or complements, then the probability just immediately becomes 0. If he says or, then do you pretty much add them, and they're going to be 1 pretty much. There you go. So I hope that makes sense. And really, just ask him about this, because the probability of getting A and AC, maybe what he means is not together, getting this and this. No, I think you need to ask him about this. I think this is a typo. I think you really need to ask him about this because the probability of getting A and AC, or the complement of A, it's impossible. You can't get this and this together. So I think what he means here is really just saying or. So just ask him about it this on Sunday if you can. But I hope so far all of you are sort of understanding what probability is. When you have union, you should add. When you have, he said 0 in the next line. Yeah, he has one part of it about mutually exclusive events. So if they can't co-occur, basically they're going to be 0. That's basically what he's trying to say. That it's impossible, yeah. Perfect, okay, then if that's what he means, then perfect. Yeah, exactly, he says it here. Probability of these both happening together is 0. Note that A and AC are mutually exclusive. So you all understand this. This is the entire thing that I've been trying to talk about, that the complement and the event of A happening together, or happening, and A and AC, it's just impossible. It's just, there's no way, right? Because if you're here, if you're at event A, you can't be at its complement. If you're at the complement, you can't be at A. So again, don't forget this. And it doesn't just go for complements, anything that's mutually exclusive. For example, being less than 6 feet tall or more than 6 feet tall, right? You can't be more than 6 feet tall or less than 6 feet tall. It's either one. So what's the chance that you're more than 6 feet tall or less than 6 feet tall? It doesn't make sense, right? Because I'm comparing one probability with its complement, and it just doesn't make any sense when I say both together. If I say what's the probability of being 6 feet tall or more than 6 feet tall or less than 6 feet tall, then it's 100%, because we're not using intersection, we're using union, and when we use union, we add. So again, I just keep repeating the same thing over and over again because, I really want to emphasize this point. Again, he gives you the same example. What's the chance of being less than 2,000 or between 2,400? If they happen at the same time, what's the probability of both happening together? It's 0. What's the probability that you fail and pass? What's the probability that you live and die? Exactly what I mentioned in this example. So yeah, the probability is 0 because they can't happen at the same time. Now look, remember how I told you union is, you just add them, right? You just add probability A and probability B. Well, look, there's a little thing that I need to add. Basically, I'll explain it like this. I'll explain it using a die, okay? So, and I'll give you another example with a deck of playing cards. So with a die, what's the chance of getting 2, or, I want you all to answer this, or even? Now, based on what we've seen so far, it's fine, answer if you want. Based on what we've learned so far, it should be 1/6 plus 3/6, which gives you 4 out of 6. This is wrong. This is wrong. The reason this is wrong is because, look, let's say we have this. This is probability A, and this is probability B. All right. Now, look, let's say we want probability A to happen, so we're going to color it all in, and we're going to call in this intersection. Then we want probability B to happen, right? So we're also going to color it all in, but we're going to color in this section again. So we're counting this intersection. We're counting this intersection twice. Can you move your, okay, sorry. I'll move it. There we go. So the basic idea is that we're counting this area twice. We're counting it once with this circle, and we're counting it once again with this circle. We're counting it once in this probability. We're counting it once in this probability. So if you try and, for example, figure out the probability by just adding, you're gonna get a problem because you're gonna count something twice. The truth is, what you should do is you should find the probability of the first one, which is 1 out of 6, add it to the probability of the second one, which is 3 out of 6, but then any intersection between probability A and probability B, you have to minus it. You have to minus it away from them. So here the intersection 2 is an even number. So is there any intersection? Is there, for example, a probability of A and intersection B? Yes, there is. There's a 1 in 6 chance of it happening with 2, because 2 is also an even number. So what's going to happen at the end? It's going to happen in this 1/6 plus 3/6 minus 1/6 equals 3/6. And 3/6 should make sense. The chance of getting a 2 or an even number it's all the same. So look, 1, 2, 3, 4, 5, 6. A chance of getting a 2 or an even number. So what's our sample space? It's all of these 6 values. And what's our outcomes of interest? It's 2, 2 again, and then 4, and then 6. So look, we have only 3 values. We have only 3 values. So it's 3 out of 6. How do we get 1 out of 6 as an intersection? It's simple. What's the probability of getting 2 and an even number? If you can answer that question, that's the intersection, right? What's the chance of getting this and this? It's 1 in 6. It's by getting 2. By getting 2, it's the only even number that is also 2, right? So I hope I'm seeing a lot of questions. Can you explain the Venn diagram? All right, guys. I'll repeat this point. This point is really important. Okay, I told you that union. Whenever you see union, you add the 2 probabilities. Correct? Now, this is only if they don't happen together. Okay? If they happen, if there is some sort of intersection between them, then you have to change it up a bit. You have to actually add a little piece of the formula. Just this part. This part needs to be added. Now, why did they make this part? I'll give you the reason. First, let's explain the Venn diagram because people have been asking for it. Okay, so look. This is an example of probability A and probability B. Let me find if I can switch them. Okay, this is an example of probability A, probability B. The difference is that in this example, this is intersection, but this is union. Okay, this is union. So here, when we consider just the union parts, sorry if you can see the L, but if you consider the union part, we're only considering what's happening between these 2. For example, what's the chance of getting heads and heads? So you can get heads here and you can get heads here, but we want them happening together, so it's going to be 1 out of 4. That's the Venn diagram way of doing it. With union, it's a bit more complicated. And intersections are simple because you only count that intersection once. But with union, it's a lot more difficult because let's say we count probability of A once. In other words, it's 1 out of 6, right? And then we count B once. In other words, it's 3 out of 6. Well, guess what? We actually counted this area that they intersect. We counted it twice. So that's wrong. We should only count it once. So how do we solve that? We have to minus the intersection of probability of A intersection B once, right? We have to minus it from the addition of A and B probabilities, right? Because we can't keep adding these twice. We have to add them only once. If we add them once, then okay, we're golden. We're good to go. But unfortunately, when we count probability A and probability B, unfortunately, we're going to be going into this problem where we're going to be counting the intersection between them twice, and that's a mistake. Let's use a different example. Let's take playing cards. I said playing cards earlier. So let's take the example of a playing cards. I'll keep explaining this. Just stay with me for just 1 second. We have 52 cards in a deck. 13 are diamonds, right? Diamonds. 13 are spades, which are like, I don't know, like this. Right? And then 13 are hearts. And then 13 are clubs, which is like the flower thing, right? Okay. Now, let's say I told you, what's the probability of getting a diamond or a king? Or a king. So we want diamond or king. Now, we have a problem. There is an intersection between them. One of the kings is a diamond. So what do we need to do? What's the chance of getting a diamond? It's 13 out of 52 because we have 52. Because we have 13 diamond cards and we have 4 kings. But hold on, one of the kings is a diamond. So we have an intersection between them. What is that intersection? It is going to be, it is going to be 1 out of 52, right? So it's going to be 13 plus 4, which is what it's going to be 17. And then minus 1, it's going to be 16 over 52. Right? So 16 over 52. So do you get this? I really need you to understand this because I think the playing cards one really, keep moving back. Okay. So this is why 1? All right, because one king, there's one king that's a diamond. There's one king that's a diamond. So what is the intersection between the kings and the diamond? We have 1 king of hearts, 1 king of spades, 1 king of clubs, and 1 king of diamonds. So why are we counting the king of diamonds here 1 time, and then the king of diamonds here 1 time? Like again, we are saying, okay, I'll show you the problem. when you add, you don't want to count things twice, okay? So I'm going to count to you every single thing that we're counting into the sample space. You have all the cards, forget the sample, you have all the cards, but here are the outcomes we're interested in. Ace of diamonds, 2 of diamonds, 3 of diamonds, 4 of diamonds, 5 of diamonds, 6 of diamonds, 7 of diamonds, 8 of diamonds, 9 of diamonds, 10 of diamonds. 10 cards, you can all agree with me, no intersections, right? Nothing, they're all just cards. They're laying out in front of us. So we have 10 of those cards that are right now counted. We have the Jack of diamonds, that's number 11, and the Queen of diamonds, that's number 12. When we say the King of diamonds, remember this. I mentioned the King of diamonds here when we were talking about the diamonds. When we were talking about the diamonds, I mentioned the King of diamonds. We have 13 in this first probability for diamonds, correct? You're all with me right now, right? Just say yes so I can know. All right, you're all with me. So you all agree that this is 13 out of 52. And remember, when I was counting the diamonds, I counted the King of diamonds once. Now let's count all the kings in the deck. All the kings, you have King of spades, you got kings of clubs, you got hearts, and you got diamonds. Why did I call it again? I already counted it here. So how do we fix this? I count it once here and once here, but I minus it once because I'm counting it twice. So what's going to happen is we're going to have 13 diamond cards over the entire deck, which is 52 cards, plus 4 kings out of 52. But since I'm calling the King of diamond twice, that's an intersection. The king can be a diamond. So for that reason, I do minus the intersection, which is 1 card. Only 1 card is an intersection between the kings and the diamonds, which is the King of diamonds. So I do minus 1 over 52, which gives me the final goal of 16 over 52. Did everyone understand that? Everyone understand that? Everyone get that? Yes, clear. All right. You didn't? Let's do a different example. Let's do with die. I don't get the 1 over 2. There's no 1 over 2. That's the problem. You mean 1 over 52? Yes.
Khaled,
yes.
I think the issue with the cards is not everybody's familiar with the cards.
Yeah.
I think that's the issue, but I think we get the main concept.
Yeah, we'll do it just one last time with dice. I think I agree with your conclusion there. So the thing we subtract. Okay. So okay. Let's do this example again. Okay. Now I told you that if we have probability of A and we do union probability of B, I told you to add, right? Add them. Add these probabilities. Okay. Now the problem is sometimes you count things more than once. Sometimes there's an intersection between them. Okay. This is the best way I can explain it. Okay. Here's the question, and he might give you this in the exam. This is a bit, a tricky question, but like still, what's the probability of getting an even number or an even number? Are you just going to say it's 3 out of 6 plus 3 out of 6? Then it's going to be 6 out of 6? No, this is wrong. This is wrong. Because there's an intersection between them, It's 3 out of 6 plus 3 out of 6. Since they're all even, you have to, what's the intersection between even numbers and even numbers? All the even numbers. So if you have all the even numbers, what do you minus it from? 3 out of 6. So it's going to be minus 3 out of 6, and you'll end up with the same answer, 3 out of 6. Right? This is a bit of a complicated one. I hope you kind of understood it. Yeah, so half. So the answer ends up being half. Let's do it again. Another example, again, die. But this time, instead of even and even, let's do 2 and an even number. 2 and an even number. And then let's do 3 and an even number. You'll see the difference here when I do 3 and an even number and 2 and an even number. Yeah, you can't have the number twice, exactly. So that's why I was saying, when we say even and even, I counted all the even numbers, 2, 4, and 6, and then I counted them again, 2, 4, and 6. So I have to minus them all again. So it's going to be 3 over 6 plus 3 over 6 minus 3 over 6, which equals 3 over 6. Sorry for all the 3 over 6s, but now it'll be easier. 2 and an even number. So it's going to be, forget the cards. I see people talking about cards. Forget the cards. Let's talk about die. Now, what's the chance of getting a 2? It's 1 over 6. What's the chance of getting an even card? That is going to be the 3 over 6. Is 2 an even card? Yes, so there's an intersection. So we do minus 1 over 6 because that's the one intersection that's present in an even deck, in an even die, or an even outcome. You get it? So if you have 1 over 6 plus 3 over 6 minus 1 over 6, you're going to get 3 over 6, which is the answer, because if we go to the sample space, it's going to be 1, 2, 3, 4, 5, and 6. If we go to the sample space, what's the chance of getting a 2 or an even number? So 2 again, and then 4, and then 6. So why are we counting 2 twice? We have to minus it once. We can't just, Doctor, can you give us an example we can do real quick? Yeah, I'll now give you an example. We'll switch it up a little bit. Let me just do 3 and even. So look, 3 and even, there's no intersection. 3 is an odd number. So here, you don't do minus 1 over 6 because 3 isn't counted twice. Here, the sample space is simple. It's 1, 2, 3, 4, 5, 6. And the outcomes we're interested in are all the even numbers. So 2, 4, and 6. And sorry, I circled 5. But 2, 4, and 6. And then what are we interested in? We're also interested in 3. So we count 3 and 1. So here it's going to be simple. You just add everything because there's no intersection. We're not counting anything twice. We don't have to subtract anything. So you just add them together. It's 1 over 6, and then even 3 over 6. You add them together, you'll get 4 out of 6, right? So that's why here, notice how it's 4 out of 6, but here it's 3 out of 6 because there's an intersection between 2 and even. It's an even number. But here, 3 and even, no, there's no intersection. 3 is an odd number, and if you count all the even numbers and the odd number, then pretty much you're gonna get 4 out of 6. So that's pretty much the idea behind it. So I'll give you one example. Let's do this. And if you know the answer, there's no need to put it, but just leave it for the people who actually want to try. What's the chance of getting a 6 or an odd number? So what's the chance of that happening? A 6 or an odd number? So 6 plus odd. Yeah, okay, so go ahead, answer. 4 out of 6. The answer is 4 out of 6. There's no intersection between 6 and an odd number, so the answer should be 4 out of 6. Let's do another one. I'll make it a bit trickier. Okay, what is the difference between, or what's the chance of getting 4 and an even number? This is a little bit trickier. So 4 is an even number. There's an intersection between them. 3 out of 6. So it's 3 out of 6. Does everyone understand that? It should be 3 out of 6 because 4 is going to get counted twice when you count it as 4 and an even number. So you have to minus it once. All right. Now let me just give one quick, just to see if you're all awake or if we need a break. Okay. So 6 is and an odd number is 4 out of 6. Yes, Tala. 6 and an odd number is 4 out of 6 because there's no intersection. So let me give you one last question, and if you guys answer this, I'll be really happy. All right. What's the chance of getting 6 and an odd number? 6 and an odd number. Take your time with this. 6 and an odd number. All right, Hamza already got it really quickly. Thank you very much. It's 0. Do not say part lean. Do not say part 6. I said 6 and an odd number. So 6 and an odd number can't happen together. It's either 6 or an odd number. So since it's 6 and an odd, yeah, exactly. So you got it there. So it's 0. So since they're mutually exclusive, you should say 0. So yeah, I'm happy you all got it. It's good. Everything's good. And yeah. Technically, this isn't complement. You get the picture. They're mutually exclusive, but technically this isn't complement because complement. I need to tell you 6 and 5, 4, 3, 2, 1. Right? So that would be complement and its actual probability. So yeah. Can you give an example only of intersection? Yeah, sure. So getting an even number and 2. So what's the chance of getting an even number and 2? Or what's the chance of getting an odd number and 1? It's the same thing. It's the same answer. So what's the chance of getting an odd number and 1? What do you guys think? I'm looking at the chat, no one's answering yet. 3 out of 6, exactly. It's 3 out of 6 because 1 is an odd number, so you have to minus it. You get it? So I hope a lot of you really get this because this is sort of an important concept. So do you guys get it at all? Should I move on, or do you guys want to do a bit more? Okay, can you repeat? All right. We'll do the last part. So I'll do it using, all right, let's first see Huda's, yeah, I said and it means intersection. That's why I want people saying 0 because you can't have 6 in an odd number. So we'll repeat, just let me listen to Huda's question. So yeah, sure, unmute, it's no problem.
I wanted to know for mutually exclusive events, when we wanna, there's no any chance for both events to happen. That's why when we multiply, we get a 0, and the same applies for the probability of an event and its complement, right? But the union or the union, which is either A or B, we add, and the probability is going to be equal to 1, right?
Yeah,
this
if you
case.
take the probability and complement, it'll be 1. If you take, for example, the probability of 1 or 2 happening, then it's going to be 2 out of 6. You get it? Because it's 1 over 6 plus 1 over 6. Did you get this point?
No. Can you please repeat?
Okay, so what's the okay, we have a die. Let's take this. Let's all do this example. If we have a die which has 1, 2, 3, 4, 5, 6, what's the chance of getting 1 or 2? Or, so I'm using union, so you add them, right? So what's the probability of getting 1?
It's 1 over 6 plus
1 over 6
1 over
plus
6.
1 over 6 equals 2 over
1
6.
over
The exact same answer here. So that's how you, if it's the probability of the event and the complement, for example, the probability of 1 or 2, 3, 4, 5, and 6, then the probability is definitely going to be 100, right? Because if the chance of 1 is 1 out of 6, the chance of all the rest is 5 out of 6. Add them together, 6 out of 6, 100%. So I hope that answered it. So we're going to repeat this example. You're welcome. We're going to repeat this example, right? So forget the Venn diagram. Just screw the Venn diagrams. Look. Okay. Look. Here's what I'm. Forget the formula. Forget the formula. Okay. We have a die. 1, 2, 3, 4, 5, 6. Forget any type of formula. I don't want to see 1 over 6 plus this. Just answer straight away. What's the chance of getting 2, 4, and 6? Half, right? Half, 3 out of 6, all you're right. Okay, I'm gonna ask you this again. Forget any formulas. What's the chance of getting 2 or 4 or 6 or 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 any even number or any even number or any even number or any even number or any even number? Why is it 3 out of 6? Shouldn't you keep adding and adding and adding and adding and putting 3 out of 6, then 6 out of 6, then 9 out of 6, then no, because I keep repeating the same things, we keep naming the same things, we shouldn't keep adding them. Instead, we should minus them as we keep adding them. So it shouldn't be any different if I say, what's the chance of getting 2 or an even number? Because when I say that, what I'm telling you, the only thing I'm telling you is, what's the chance of getting 2 or 2 or 4 or 6? It's still 1, 2, 3 over 6. You get it? So the intersection, when I say 2 or even, the intersection here is 2. We're counting it twice. We're counting it once here, and we're counting it once when we talk about the even numbers. So that's not good. That we don't want to do that. We absolutely do not want to do that, because then if we do that, the answer will be 4 out of 6, which makes no sense. Absolutely makes no sense. I'll give you another example. What's the chance of getting an even number or an even number or an even number or an even number? What's the answer? 3 out of 6. Why is it 3 out of 6? Because here's what you're doing. You don't know that you're doing this, but this is what you're doing. You're doing 3 over 6 plus 3 over 6 plus 3 over 6 plus 3 over 6. But oh wait, no, I counted it 3 more times. So I'm going to do minus 3 over 6, minus 3 over 6, minus 3 over 6. And here you go. Now it's back to 3 over 6. So did this make it clear? Just because there's intersections doesn't mean we should add them. Intersections mean the exact opposite. Intersections mean that I'm counting something multiple times. So because I'm not counting something multiple times, it's not fair to just add the probability up, right? If I say 2 or an even number, 2 is an even number. So why are we adding it? Why are we saying 2 and then 2? And what's the chance of getting an even number and 2? Oh, okay, this is nice. All right, yeah. So chance of an even number and 2. Okay, so you made it like 5 times more complicated. So first off, we have to make sure. Are they complements? Are they mutually exclusive? The answer is no. 2 can happen and even can happen. So how would you answer this of getting 2 and an even number? Well, look, what you should do is going to be, what you should do is 1 over 6 times 2 over 6. But this is wrong. Okay? I don't know why, but the answer should be 1 out of 6, right? Because the only way that you get 2 and an even number is by getting 2, right? So forget formulas. If he brings you a question like this, here's what you do. It's very simple. You do the sample space, which is 1, 2, 3, 4, 5, 6. What are you interested in? 2 and an even number. The only outcome that can be 2 and an even number is 2. 4 is not 2. 6 is not 2. The only number that can be 2 and an even number is 2. So that's the only outcome that you can possibly have. So 2 is the only one, so that's going to be our m, 1 over all of them, which is 6. So the answer is 1 over 6. So that's a bit more complicated. I can't prove it through formulas and that stuff, but like you get the picture, right? You get the picture. So yeah, I hope a lot of you understood this. Did you guys understand this? Now look, here's the best part. Here's the best part. If we say for example, let's say the two events were mutually exclusive. They can't happen together. So for example, I tell you, what's the chance of getting an even number or an odd number? So since there's no intersection, you don't need to bother with this portion of the formula. So as a rule, when two events are mutually exclusive, then you don't need to even consider this. Just add them straight away. It's going to be 3 out of 6 plus 3 out of 6. It's 6 out of 6. It's 100%. When they're mutually exclusive, you don't need to minus. When they're not mutually exclusive, when there's an intersection between them, you need to find that intersection. You need to quantify that intersection. You need to minus that intersection from the actual probability. So did that make sense? I need to see some yeses, or if I just see one no, I think we need to like revise it or something. But yeah, so a lot of you are, yeah, so I'm seeing a lot of yeses. All right, perfect. So let's move on. So see, I could have just like not took any questions and just moved on and just been like, okay, so this is multiplication rule, blah, blah, blah. But like, no, it doesn't make sense for me to go further if you guys aren't understanding this, because it only gets harder from here. So here we go. All right, so multiplication rule. So what is the multiplication rule? If there's an intersection between two things, for example, what's the chance of getting heads, and what's the chance of getting 1 out of the die? So 1, like I forget 1. 2, what's the chance of getting a 2 on the die and heads on the coin? So you do half times, because you want them happening together. You know, you want to have it together. So you do half times 1 over 6, which is going to be 1 out of 12, right? So it makes sense that the probability is even harder because you're putting more and more conditions, right? You're putting coin and die, and if we add another thing like a bag, it should be even a lower and lower probability. So the multiplication rule is really important. Now, he mentioned something here that sometimes the probability of B gets affected by A. So for example, let's say we have a bag, all right? And let's say you have a blue ball, a green ball, a yellow ball, and a red ball, all right? Let's say the first time you go in, you'll grab a ball and then keep it outside. So the next time you go in, you'll only have 3 balls inside. All right. So now it's different. You're not just doing the first one times the second one. The second one got changed because of the first one. So how do we write that? We say probability of A times probability of B, such that this line means such that A already occurred. Now again, if they're mutually exclusive, you don't have to care about A happening, because just because A happened doesn't mean B is going to happen. Just like how we did here, the coin had nothing to do with the die. But here, since we're going to take a blue ball, for example, and put it outside, now the next chance is going to be a bit different. So for example, here, I need to move this sharing screen thing. Okay, I'll do them for you both together. Let's do them both together and I'll show you how different they are. So when the I should have like said independent, non-mutually exclusive. Point is, look, let's say we're tossing a coin. I'm going to ask you all this and let's all do it together. The chance of tossing a coin and getting a 6 on the die. So what's the probability? So you're going to do P A times probability of B. And we don't care such that A happens. We don't care because these events, they don't affect each other. They're independent. You know, just because we got heads on there doesn't mean we're going to get like 6 or 5 or something, or something's going to happen to the die. So these are independent, so we don't need such that A happen. So this is going to be 1 over 2 times 1 over 6, which is basically going to equal to 1 over 12. All right. So this is the probability of the first one. What if the events were dependent on each other? In other words, they actually change one another. So, for example, we have a bag with a blue ball and a green ball and a yellow ball and a red ball. So what's the probability of first getting the green ball and then keeping it outside and then going in again and getting the red ball? So the first chance is going to be 1 out of 4, and then we're going to multiply it by the probability of event B such that A happened. So A happened, the ball is outside. So it's going to be 1 over 3 times 1 over 3. It's going to equal 1 over 12. And I completely did not plan on these two being the same answer, but it's a nice little coincidence. So does this make sense? You see, if the events are independent, then you can just do probability A times probability B. If they're not independent, they're dependent on each other, then you do probability of A, the first one that's going to happen, times probability of B such that A happens, right? But here it doesn't care because, you know, A is not going to affect B in terms of the coin and the thing. So does this make sense to all of you? Good. Now, independent does not mean mutually exclusive. Independent means they don't affect each other. But we can still multiply them and they're still going to give us an answer. If they're mutually exclusive, what's the chance, for example, what's the chance of getting 6 and a 5 by rolling one die? Or what's the chance of getting heads and tails? What's the answer to all that? I'm waiting for, yeah, 0. So mutually exclusive means they can't happen together. Independent means that one can happen and does not affect the other. It doesn't mean that they can't happen together. So you should learn to sort of differentiate between the two. So this is an example. Let's do it. Assume that in a specific population, the probability of an adult between ages of 18 and 40 does not have health insurance. Probability to not have health insurance is 0.123. That's the probability, right? We randomly selected a 22-year-old man, 37-year-old man. They're all between the ages, so it's all good. What is the probability that both individuals are uninsured? Now, I want you to all answer this. You don't need to give an answer. Just say what you're going to do. So if you're all thinking of 0.123 times 0.123, that's perfectly the exact same answer that I want you to do. Because, again, are they dependent events? Is this guy, for example, when he gets insurance or doesn't get insurance, this guy's not going to get insurance? They are independent events. So I'm just going to multiply them and it doesn't matter. One is not going to affect the other. So I'm going to use the same probability. What is the probability that both individuals have insurance? Now he's asking the complement. So what's it going to be? It's going to be 0. Whatever. Like I actually can't do the math right now. 9. I actually can't do the math. Like 87. I don't know. Like it should be 77, right? 977 times 87. Whatever. 87. 987 and times 0.987. It's not 9. Yeah, it's 987. You're confused? Why are you confused? Okay. Basically, this is the same exact principle. Didn't we just say that? Okay, I want Sarah and Samiha to answer this. Don't no one else answer this. What's the chance of getting a heads and getting 1 out of 6 on the thing? The one I already gave you the 1 out of 6. Okay. What's the chance of getting heads on that and, for example, 1 on the die? 1 out of 12. So I don't know why Marwan is like getting into this. All right, it's fine. Do you understand? Does Sarah and Samiha, do you understand why, like, the answer is 1 out of 12? All right, so you understand. Now, this is no different. We're doing the same thing, but instead of the numbers being easy, like 1 over 2 times 1 over 6, the number is 0.123. That's the probability you're working with. He tells you, what's the chance of both of them being uninsured? The probability of being uninsured is 0.123. So what's the chance of both of them being uninsured? The first chance is 0.123. You multiply it by the second chance, which is 0.123. This is the probability of both of them being uninsured. Okay? The chance of both of them being insured is the complement. So what's the complement? You first flip this. You do 1 minus this value, 1 minus this value. You're going to get like 0.9, So that's the probability of being insured, right? Yeah, you can do 1 minus 0.123 times 1 minus 0.3. But yeah, if you do 1 minus, you're going to get this value. That's the probability of being insured. So what's the chance that they're both insured? Remember, they said both, so it's an intersection, so you have to multiply. So 0.987 times 0.987. So does that make sense to everyone? I need to see some yeses, otherwise I'm like repeat this over and over again. Yeah. All right, yeah. Perfect. So remember, sometimes I see some people, they rush, they see that, yeah, 0.987 is insured. Because look, he told you here that the chance for someone between 18 and 40 to not have health insurance is 0.123. So what's the complement of that? That'll be your, for example, after subtracting. Yeah, 0.877, whatever. My mind can't do math right now, okay? So the point is just find the complement and then, do that using your calculator and everything. So I'll just do it. I'll just do it here. 0.9, right, 0.123 minus 1. Yeah, 0.877, all right? So that's the complement. You do 0.877 times 0.877, and that's the probability of both of them being insured. Sometimes I see people rushing. We'll have to use the exam software. Yeah, you'll have the exam software calculator, inshallah, don't worry. Point is, I see some people rushing. This is the probability of being uninsured, not having health insurance. So if he asks you, what's the probability of both of them being insured, don't do this. Don't do 0.123 times 0.123. Find the complement of this, which is the same number, and then just multiply them together. You'll get, for example, 0.877 times 0.877. Read, please read. Have your morning coffee for the exam and just focus on what the question is saying. Because again, 1 mark is probably going to be 1 mark out of your final grade. So don't, lose a mark just because you didn't read it properly. All right. So he gives you the solution. What's the probability of both of them being uninsured? So the probability of being uninsured is 0.123. So it's 0.123 times 0.123, which gives you this value. This is the value of both of them being uninsured. All right. So what's the probability of both being insured? Or no. Here, what's the probability of one being uninsured and one being insured? So what's it going to be here? It's going to be the probability, you're going to take 0.123 times 1 minus 0.123. 1 is going to be the actual probability, 1 is going to be the complement. And, if you want, for example, both insured, or is this both insured? Yeah, but he wants both insured. Yeah, so both insured. You just do the complement, which is times the complement, you get 0.769. I hope everyone finds this is clear. And yeah, do you all find this is clear? I just need someone to tell me yes, because yeah, all right. So everyone finds it clear, alhamdulillah. Let's go. Okay, so I want everyone to answer this. Does rolling a dice, so rolling this dice and spinning the spinner, right, which has like different colors, are they independent? Independent, exactly. So they are independent, right? So I'm seeing so many yeses. Okay. So they are independent, right? And the reason is because if you get a 1 here, it doesn't mean you're going to land red here. It's not going to affect it. These are independent. It's because what happens here doesn't mean what happens here. Same thing with this guy. Just because he gets insured doesn't mean this guy, he's not going to choose not to get insurance or his probability will change or something. No. Probabilities stay the same because they're independent. So yes, it does. Yeah, they are independent. Yeah, mutually exclusive means that B cannot happen if A happened. No, notice how they give the notation for it. The probability of B happening such that A happened, assuming that they are both mutually exclusive, in other words, they can't happen together, is completely going to be 0. But the probability of B happening such that an independent event called A happened, yeah, there is a probability. It's going to be the same as it just being B, because it's independent, it's not going to affect it. So independence is different from mutually exclusiveness, right? And this is an important principle. I skipped this slide. Okay, so conditional probability. This is basically conditional probability is this, such that. So probability of B happening such that A already occurred. This is termed as conditional probability, and this is what he is talking about here. Okay, so does the knowledge that A happened prior to B happening, does it change B? If not, then they're independent. If they are, then that means they are dependent on each other. So yeah. So for example, what is the probability that a 65-year-old will potentially survive to age 70, and then assuming that this man is diagnosed with lung cancer, yada, yada, yada. He basically tries to give you the idea that we can't do the probability of him reaching 70 and having lung cancer until we deal with the earlier probability. So these are conditional probabilities. This is just another example. What's the probability that you'll get an F in this course, given that you have not attended a person? Okay, so again, this is a nice example of a conditional probability where you can't really say that one will happen if you haven't been doing the other, or if the other event hasn't been happening. All right. So here, I think we reached slide 50. All right. So fortunately, every single time it just leaves. So yeah, tomorrow. Look, I don't know if you guys want to do. I don't know if you guys want to do relative risk and odds ratio. Tomorrow we'll pick up from here. We'll see if the majority of you want us to do it. If we do it, it's going to take like 30 minutes. It's a really long part, and even though it's like 18 slides, it's up to you guys. I don't mind doing it. And in case some of you want to see it, you can go to the 11th batch YouTube videos, and there's a video where I explain it, and you can just go to the end of that video and see all the things about it. But I don't mind if we go over it. If it's not included, it's not included. It's fine. We don't need to cover it. But with that, we're done. If someone has a question, I think it's Tada. So, Tada, go ahead. If you want to unmute or if you want to ask it here, go ahead. Yeah, unmute, go ahead. If you guys have any questions now, I think this is the perfect time for us to have questions.
Doctor, the last example you gave us, sorry, Khaled, the last example you for the uninsured, insured, can you go back to it?
Sure, just one second. I am like stuck. Let me close this. And all right, you can see the slides?
Not the example slide.
Yeah, which one?
No, I think it's 44. Yeah, 44.
44. Okay, this one.
Yeah, over here. So for instance, if they give us uninsured, okay, we would just multiply the two numbers, the 0.123, right?
Yeah, if they said what's the chance of both of them being uninsured, you do 0.123 times 0.123.
Yeah, but for the insured, we would get first of all the complement of the probability, which is minus the probability, 1 minus the probability, right? And then we multiply the 1 minus probability with the 1 minus probability, right?
Yes, yes.
Okay, thank you.
You're welcome. I don't know if we're still doing them. Yeah. So we're going to do the rest of the lectures tomorrow, inshallah. There's not, if you guys have questions, if you guys feel a bit burned out and want to ask the questions tomorrow, I think we're going to finish tomorrow relatively early. Today we took an extra hour because, I wanted to make sure everyone is understanding what we're saying. But yeah, so if you guys have any questions, so tomorrow, inshallah, we'll meet at 2 p.m. We might finish around 4 or 5 p.m. And yeah, if it's independent, we just multiply. Yeah, you just multiply. Am I the only one who did these concepts in school? Not you guys. I don't know what to say. All right. So are you all? You're all welcome. Oh, thanks. All right. Are you all like good with this? All right. So I'm just gonna give 5 more minutes. If just anyone has any more questions, you're free to ask. All right. You're more than welcome. And again, just a little shameless. Yeah, I forgot to tell you guys. Let me just share my screen one more time. All right, just in case you didn't, all right, I am trying to be a sort of miniature Dr. Mike on YouTube. So where is this goddamn thing? How do I share screen? Yeah, okay. So you all can see this, right? Yeah, so just in case you want to study for biostats for step 1, just in case you want to find out why the hell we dream, or why the hell our heart doesn't stop, or why we have things called illusions, or what smoking does to your body, things like that. And if you want to stay in tune, because I'm going to make more videos as soon as I'm done with step 2, because it's a hell of a grind. Point is, please subscribe. There we go. All right. So no more questions. And by the way, if you search, I should do this, youtube.com/Dr. Khaled, and you're gonna find this. So yeah, thank you everyone. I think there are no more questions left, and we can just pretty much call it a day. Go relax, have dinner, or your evening coffee. Don't have your evening coffee, but I'll see you all inshallah tomorrow at 2 p.m. Yalla guys. All right. Have a pleasant evening and good night.